So there are many reasons why you might study logic. One would be you're just in a course, so you have to, but let's look at some positive reasons behind why someone might independently try to learn more about logic. The first one is that you've noticed that natural human reasoning, that is, people you talk to, people you interact with, maybe yourself, sometimes people reason incorrectly. So there's certain problems associated with it. It's not a skill that you have that is perfect, so you want to improve that skill. So you want to know how you ought to reason. And so you think, oh, maybe logicians who are trying to tell you what follows from what or what's the correct way of reasoning can give you some guidance. The other would be that, hey, human reasoning you might think is just limited in a certain way. We can only hold so much information in our head, or we have difficulty calculating certain inferences. So maybe we can employ some mathematical tools to reason better or reason more effectively. Another aspect, and this is one that I think is my favorite, is that reasoning or like thinking through an argument or analyzing something to see if it's a good argument is exhausting. And who wants to do all of that work? It's similar to calculating some equation. You might try to do it all by hand, but maybe there's a way that you can determine if an argument is good in a mechanical way, such that you don't have to do all the heavy lifting yourself. Another reason, which is the fourth one here, is that a lot of times people will say logic is important for doing philosophy. And so you want to understand, let's say, some philosophical argument that has to do with the fundamental aspects of reality. And that argument employs certain logical reasoning or is put forward in a formal or symbolic way. And so understanding logic will be a way for you to access a whole new body of literature that's really directed at understanding how the world works or its fundamental aspects. And then the last thing, and I've noticed that there's quite a few students who have taken courses in symbolic logic. They say that this is the part that they like the most, and they're interested in understanding aspects of their language more. So they want to know about the structure of their language, and they're not terribly interested in taking a course in, let's say, grammar or syntax. They're interested in trying to be more precise about certain terms or using it in a more effective way. And so they view taking a course in symbolic logic as a sort of road to that. And I think that is right. Since logicians are so interested in how words or terms or symbols function, you can definitely learn more about your own language, its structure, by studying logic. So let's dive into symbolic logic, which is logic is investigated in a formal way or using an artificial language. So the language of propositional logic is the first logical language we'll introduce, and this is a formal or symbolic language. It's composed of a couple things. First, it's composed of a set of symbols. You can think of this as like characters or alphabet of the language. The next part is its syntax. You can think of as like grammar. This is, okay, you have all these symbols. Now, how do you put those symbols together in the correct or grammatical way? This grammar is really simple in comparison to the language that you speak. There's only a small set of grammatical rules known as formation rules that tell you how to take those symbols and put them together in the right way. The third part is the semantics of the language. This actually tells you what all those symbols mean or what the formulas mean or the syntactically correct units mean. So the language itself is composed of these three features: the symbols, the syntax, and the semantics. So let's look at our language. Again, our language that we're going to look at, we're going to abbreviate it as PL, but all this stands for is the language of propositional logic. So we're going to look at the symbols or the alphabet or the basic characters that you use that are found in the language. So it consists first of an infinite number of propositional letters. And in our case, the propositional letters that we'll use are going to be uppercase Roman unbolded letters with or without numerical positive subscripts. So if you had the letter A, the letter B, the letter C, and so on, all of these uppercase Roman letters, all of these would be considered the propositional letters. These would be the first type of character in the language. Since we don't know how many we need, we're also going to allow for subscripting integers. So we could write a sub 1, a sub 2, a sub 3, and this ensures that we have an infinite number that will never run out. The next thing that we're going to have is, in terms of our symbols, or the second type, are 5 what are called truth functional operators. There's this little V here. There is this right arrow. There is this double arrow. There is this sign here, which is a sign for negation. Sometimes you'll see it written as a tilde. It's a little squiggly line. And there is this caret here, the symbol for and. We'll talk more about these symbols in a second. But the thing that you want to know now is that the second type of symbol in the language are these 5 truth functional operators. Now, the last thing that we use are brackets or braces or parentheses. They have a particular role. They're going to indicate scope, but we're going to use, what's important now is, since we're just introducing the symbols, is the left parenthesis and right one. And those would be the third and last type of symbol in the language. So that is fantastic. You know, our language, all the symbols, all the characters that we'll use are right here. The propositional letters, the truth functional operators, or operators for short, and then the parentheses. So I'm going to make a couple of other quick points. The positive integers, the reason we're subscripting these to the propositional letters, once again, the only reason is just to make sure we have an infinite number. For practical purposes, you almost never see these on the characters themselves. You'll just use the letters A, B, C, and so forth. There's other ways of doing this. You don't actually have to use the letters. You could use like binary if you wanted, but we're just going to use these uppercase letters because it's a really simple way of doing things. I wanted to make a little brief mention about these truth functional operators because sometimes they're hard to actually refer to. I want to talk about which type, especially when you're just talking about the symbols. Here, this little sign right here, which sometimes we use this, as I mentioned, the little tilde. This is the sign for not or negation. So we can call that. We can say, oh, that's the sign for not or negation. The next symbol we want to take a look at is this wedge here. So this little caret here. In some languages, you will actually use a different symbol. You will use the and symbol, and sometimes you'll even see just a dot. So this is the symbol for and, or what we'll call it the wedge or the and. Here we have the V, this little V here. It's sometimes called the V, sometimes it's called the or, symbol for or, and pretty much universally you see just this V. It's found in most logical textbooks. The fourth truth functional operator is this right arrow. Sometimes you'll see a different symbol in a particular text. The most common one you'll see besides the right arrow is this horseshoe. But they both stand for the same thing. It's just a different character that's used, but we'll use this right arrow. And then the last symbol that we'll make use of, this last truth functional operator, is what we'll call the double arrow. It looks like the double arrow. Sometimes it's called the left-right arrow. Sometimes people refer to it as if and only if. And in some textbooks, you'll see, instead of that, you'll see something like the triple horizontal line. I think there's another one, but I can't think of it offhand. So these are our 5 truth functional operators: the not, the wedge, the V, the right arrow, and the double arrow. So let's quickly test our knowledge of this material. I'm going to write down some symbols, and you can tell me if they are a symbol in the language of propositional logic, and if so, what type. So let me start by writing this sign right here, this $sign. And if you look at it, you'd say, no, it's not part of the language of propositional logic. Well, let's put an X there to say it is not. Remember, this is just not found in the 3 kinds. What about P? The answer to this would be yes, this is a propositional letter. What about Q sub 1? Yep, this is a propositional letter, so it would be part of the language. What about this right arrow? Yep, this is the right arrow. Sometimes you'll see it as the horseshoe. What about this one, this arrow pointing up? For this one, the answer is no, this is not a symbol in the language. Even though it is an arrow, we don't have an arrow that points up. Let's look at 2 more. What about this one, this left parentheses here? The answer would be yes, we have parentheses. This is part of the symbols in the language. What about this caret? The answer to that is yes, this would be a symbol in the language of propositional logic, and it would be a truth functional operator. It's the sign for and, or logical and, or we can just call it the caret. So if you answered all those correctly, then you are an expert, at least in 1/3 of the language of propositional logic. You know all the symbols. So the next thing to look at are the syntax and semantics. The next thing to look at with respect to the language of propositional logic is its syntax or grammar. So you can think about the syntax or grammar of the language similar to how you think about the grammar of your own language. You have various symbols in your language, and you can only put them together in certain ways. You can't just randomly throw the characters of your language in some random order, because as soon as someone does, you'd say, hey, that violates certain rules. What you say doesn't make sense based upon how you have put all those characters together. So in the language of propositional logic, the grammar is known as the formation rules. These formation rules, in calling them formation rules, they tell you how to take those symbols, all the symbols that we looked at, and the formation rules will, let's just abbreviate it as FR. The formation rules will tell you how to take those and create a grammatically correct unit, which is known as a well-formed formula, which we'll abbreviate as WFF, and we'll just call them WOOFs. Because if you say well-formed formula a bunch of times, it's exhausting, it's tiresome, and it's just more fun to say, oh, that's a woof, or putting those symbols together creates a woof. It's just more fun that way. So what is a well-formed formula or woof? Well, a well-formed formula or woof is any formula, so it's any combination of characters that is capable of being created or constructed or generated by some combination or use or application of our 7 formation rules, which are our grammatical rules. So the next question you might have is, what are these formation rules? What are these rules that allow us to take various symbols and put them together to create these woofs that we are interested in? Well, let's look at them. Here's the first one. Every propositional letter is a woof. Now, this is a very easy grammatical rule here. All you need to do is simply write a propositional letter and boom, you have a well-formed formula or woof. So if you wrote the letter A here, you would create a woof, a well-formed formula, a syntactically appropriate or correct sentence. Here's our second rule. If you had a well-formed formula, and we'll call it phi, so that's what this little symbol is right here. This phi here is just a variable or a placeholder for something that we're going to say we already know it's a woof. And then you can take that formula, that well-formed formula, that woof, and you can put parentheses around it and the negation to the left of it, and it is a well-formed formula or woof. So in an example, let's say we have the letter A, which we know by rule 1, since every propositional letter is a woof, we know that A is a woof. Well, rule 2 says that you can take this well-formed formula, A, and you can put parentheses around the whole thing and a sign for negation, one of our characters to the left of it. And this negation, parentheses, A, close parentheses, is also a well-formed formula or woof. So that's the rule 2. Let's kind of keep moving and look at the next one. So rule 3 states that if you have a formula phi and a formula psi, so these again are placeholders or variables, they're just kind of a spot that we could put in a well-formed formula. So assuming that these are woofs, then you can take them, write them down, and put between them the symbol for and, or this caret, and put parentheses around it. And the result would be a well-formed formula. So let's say we knew that A is a woof and B is a woof. And we know this because of line 1, right? Or rule 1. It says every propositional letter is a well-formed formula or woof. Well, we can take those 2 formulas and put A or B. See, I'm putting this symbol for the caret between them. And then the rule says we need to put parentheses around the whole thing. And the result, this open parentheses, A, caret, B, close parentheses, is also a well-formed formula or woof. Let's keep moving. Let's say we had phi and psi, so both of them are well-formed formulas. We already established this. Then just like before, just like in the case of the caret, we can write both of them down, put the sign for the V between them, this particular caret, this truth functional operator, and put parentheses around the whole thing. And the result is also a well-formed formula. Now I'm going to load on you 2 more formation rules. And notice we only have 7, but you'll notice a pattern in the formation rules for 3 through 6. So 5 and then 6. So notice the pattern here. What we have is in each case, we have if something is a well-formed formula and something is a well-formed formula, then you can take those 2 formulas, put a particular operator. In line 3, it's the and or caret. In line 4, it's the V. In line 5, it's the right arrow. And in line 6, it's the double arrow. And you could put that operator between those 2 things that are formulas and put parentheses around the whole thing, and the result is a well-formed formula. So in the case of 5, we have phi and psi. You take those, write them down, put the right arrow between them, parentheses around the whole thing, and the result is a well-formed formula. In the case of line 6, we have phi and psi. Write both of them down, put the sign for a double arrow between them, or if and only if, put parentheses around the whole thing, and the result is a well-formed formula. So that is 6 of our formation rules. The rules that tell us how to construct well-formed formulas. Let's take a look at the last one, and the last one is the easiest one to think about. It just says that everything else that is a well-formed formula can be constructed using rules 1 through 6. And it's also saying that nothing else is a well-formed formula. So there's no other combination of symbols that would be a well-formed formula unless it can be composed using these 6 formation rules. So that's it. In case of language of propositional logic, this is the entire grammar of the language. These are all of the grammatical rules. In natural languages you speak, you got grammatical rules for past tense or past perfect or subjunctive, but this is it for the language of propositional logic. And besides some terminology thing, if you have a clear understanding of how to use these formation rules to construct well-formed formulas, then you basically understand the entire syntax or grammar of the language. And since you understand the symbols, and you understand the syntax, you understand 2/3 of the language. The only thing that's left is the semantics of the language, or saying what all these different formulas and operators mean. So I want to finish with 2 things with respect to these formation rules or the definition of a well-formed formula. The first thing I want to do is look at some just examples of formulas that are well-formed formulas. And then also look at some examples of formulas that are, or combinations of characters of the language of propositional logic that are not well-formed formulas, or they're not woofs. So here we have 4 different formulas. P right arrow Q, we have this negation, these 2 parentheses, P, V, not, and then the open parentheses, a Q, and then the triple right parentheses. And both of these are well-formed formulas. Similarly, line 4 here is a well-formed formula. The reason I'm putting these out there is just so you can kind of look at a formula and say, I feel comfortable that this is a correct combination of characters. And the way you learn this is just to look at a bunch of examples. Let's look at some examples of formulas or combinations of characters that are not well-formed. In the case of line 1 here, we have P and then the negation. So there's no way to form this rule using the formation rule, because the formation rule says that if you have a formula like phi, then you can take that formula and write down the negation, put parentheses around it, and this is the result. There's no rule that says you can take the formula and then say, which would be P in this case, write the formula and then put the negation to the right. And since we can't form this particular formula, this line 1 here, this rule 1, or this formula 1 here, using the formation rules, then it is not a well-formed formula. Let's look at number 2. Number 2, you notice that there's just 2 propositional letters, P and Q. Well, remember that every propositional letter is a well-formed formula. So P, Q, R, all of those are well-formed formulas. But there's no rule that allows us to say, well, P is a well-formed formula and Q is a well-formed formula, so I could take them and I can smash them together, conjoin them, or write them next to each other. And so the result of combining those 2 together is not a well-formed formula, because there's no rule that would allow you to take propositional letters and put them next to each other. Let's look at number 3 here. So number 3, there's a whole bunch of stuff going around with it, but the main thing is that we have this V here. Now, if you look at the rule associated with V, or sometimes called disjunction, it says that if you have two formulas, phi and psi, well, you can take those two formulas that are well-formed and you can conjoin them together by putting this phi or this v between them. And this would be a well-formed formula. And so since there's no way to create a formula that puts the v to the left, this would also not be a well-formed formula. And then lastly, for number 4 here, one thing to notice about the rules for the formation rules is they require you to add parentheses. So for example, let's take the rule for the caret here, or for and. That rule says that if you have a formula and another formula and both of them are well formed, then you can take them and put the and symbol or caret between them, and then you have to put parentheses around the whole thing. But here we notice that there are no parentheses, whereas the rule requires parentheses. And so this would not be possible or to be created using the formation rules, and so it would not be a well-formed formula. As a final exercise, since learning the formation rules is so important, it's worthwhile to just construct some formulas using the rules step by step. So let's do that. Let's take some simple formulas and construct them using the formation rules. So the one we'll start with is not Q. And so I'm going to show you how to construct this formula using the formation rules. The first thing I would start with is just to write down and say Q is a well-formed formula. So this is a well-formed formula, and the rule that you would use is rule 1, which says that all propositional letters are well-formed formulas. And the next thing I would do is say, well, since I know that Q is a well-formed formula from line 1, I can say that not Q is a well-formed formula. And the reason I can say this is because Q is a well-formed formula, and there is a rule, let's just call it rule 2, which says that if you have a formula phi, then you can take that formula and put a negation down and parentheses around it, and the result is a well-formed formula. So what I've done essentially is use the formation rules to essentially prove that not Q is a well-formed formula. Let's look at 2 more examples. So let's do something slightly more complicated. Let's look at not P and Q. So let's show that this is a well-formed formula. The first thing I would do as in constructing any formula is start by saying, hey, here are all the propositional letters and they are all well-formed formulas by themselves. So I would say that P is a well-formed formula. I would also say that Q is a well-formed formula. And then the next step I would do is to say, well, if I know that P is a well-formed formula, and I have this not P right there, I can prove or construct not P from P. So my next step would be to say that not P is a well-formed formula. And this would be using line 1 and rule 2. So line 1 says that P is a well-formed formula, and rule 2 is, again, the rule that says if you have a formula, then you can take that formula and put a negation around it and parentheses around it, and the result is a well-formed formula. So now I'm off to try to construct the entire formula. So here's how it's done. I'm going to be a little bit more explicit here. So I already know from line 3 that not P is a well-formed formula. So I know that this is a woof. And something else I know is that Q is a woof. And I know this from line 2. Line 2, I've shown that since every propositional letter is a woof, Q is a woof. So from this, I can reason to the fact that not P, which is a woof, and Q, or this caret Q, is a woof. And the reason I can do this is because of line 3 plus line 2 plus rule 3. And rule 3 essentially says that if you have a formula phi and you have a formula psi, you can take those two formulas and put them together with this caret between the two. So I have that at line, I have not P, which is a woof, Q is a woof. So those are my two formulas. And then I can take those two formulas and put the caret between them, parentheses around the whole thing, and the result is a well-formed formula. So again, what I've done is shown that you can construct this formula, this not P and or Q, or not P caret Q. And since I can construct it using the formation rules, it is in fact a well-formed formula. Let's look at one more example. If you don't really think you need this, you can kind of move on. But if you're still struggling, I just want to give you one more example to kind of sink your teeth into. So here's one final example. Let's say we had P and Q, and it was VR. So I'm going to show that this is a well-formed formula, and I'm going to do this using the formation rules. So the first thing I would do, just like with every construction, is to say all of the propositional letters P, Q, and R, all of these are well-formed formulas. I'm just consolidating this all on this single line, and the reason for that is rule 1. Since all of these are propositional letters, P, Q, and R are well-formed formulas. The next thing I would do is to build this parentheses P and Q. And so I would say, well, since P is a well-formed formula and Q is a well-formed formula, it follows that P and Q is a well-formed formula. Again, the rule is that if you have two formulas, phi and psi, you can take those two formulas and you can write them down, put the caret between them, parentheses around the whole thing, and the result is a well-formed formula. And so that's all I did at line 2 there. Now my last step is to say, well, I know that P and Q is a well-formed formula. I established that at line 2 right here. And I also know that R is a well-formed formula. I established that at line 1. So what I'm going to do is I'm going to take those two formulas and then I'm going to put them together. I'm going to take P and Q, and then I'm going to take R. I'm going to put the V between them and parentheses around the whole thing, and the result is a well-formed formula. So why can I do this? Well, the reason I can do this is because of if you have the rule, if you have a formula phi and a formula psi, you can take those two formulas, write them down, put the V between them and parentheses around the whole thing, and the result is a well-formed formula. So notice that P and Q here, this is my phi right there. That's one formula that is a well-formed formula. And notice that this R here is my psi. And so I'm just taking those two formulas, plopping them down, putting the V between them and parentheses around the whole thing. So hopefully this helped you be able to understand what a well-formed formula is, as well as identify well-formed formulas, identify formulas or combinations of characters that are not well-formed formulas, and if you're unsure, how to construct well-formed formulas. All right, so the next thing to look at are 3 different types of formulas. So we have a notion of a well-formed formula, but we also want some terminology to talk about different types of formulas. So the first one is an atomic well-formed formula. So what is that? So an atomic well-formed formula in our language of propositional logic is just a type of well-formed formula. And it's a type of well-formed formula that consists of simply a single letter. There could be P, R, S, D. Another example would be, let's say, A sub 1 or B sub 5. So if you have just a letter all on its own, nothing else, then you have an atomic well-formed formula. So here's some more examples. We have P, Q, A, B sub 12, because we can subscript positive integers to letters. And since it's just a propositional letter, it would be an atomic formula. In contrast to an atomic well-formed formula is what's known as a complex well-formed formula. And it's pretty easy to define. A complex well-formed formula is simply a well-formed formula, or WOF, in propositional logic, and it needs to contain at least one. It can contain more propositional letter and a truth functional operator. You can really shorten this down to it's a well-formed formula that contains at least one truth functional operator. So let's look at a couple examples. So here would be a bunch of examples of things that are complex well-formed formulas. We have not P, P and Q, P right arrow, and then you have this negation A, and then A sub 1 right arrow, B sub 8. Notice in each example there is at least one truth functional operator. So you can see that in some cases there are more, but provided it has at least one truth functional operator, then it's considered complex. Now, one thing to note is that the atomic well-formed formulas and the complex well-formed formulas are mutually exclusive. If something is atomic, then it will not be complex. And if something is complex, then it won't be atomic. Because complex well-formed formulas have at least one truth functional operator in them, but the atomic well-formed formulas are just the letters. So it would just be P or Q or R. Now, the last type of formula that I want to talk about is a literal well-formed formula. A literal well-formed formula is a little bit different. It is either an atomic well-formed formula or a negated atomic well-formed formula. So if it's an atomic well-formed formula, it would just be a letter. So P, Q, R, S. All of these would be atomic well-formed formulas because they're just the letters. But if it's a negated atomic well-formed formula, then it would be something like not P or not Q or not R and so on. Now, in this case, here we have atomic because it's just a letter, and here we would have complex. But both of these would be literal well-formed formulas. In other words, something can be a literal well-formed formula, and it might be complex if it's negated, or it can be an atomic well formula. So you have these literals that are sometimes atomic or sometimes complex, depending on the type of literal well-formed formula that you have. So again, some quick examples of literal well-formed formulas. We have P, it's just a single letter, so it's a literal well-formed formula. We have not P, it's a negated atomic well-formed formula or negated letter, so it is a literal. We have Q, and then we have not Q sub 1. All of these are examples of literal well-formed formulas. The next thing to talk about are the fact that we can refer to the parts or the formulas that build up increasingly complex well-formed formulas. So one thing to note is that when we use our formation rules, these rules that allow you to create well-formed formulas, we're always taking well-formed formulas and using those to build up more and more complex well-formed formulas. And sometimes we want to talk about the parts of those formulas or the subformula, what are sometimes called the subformulas of those formulas. So let's give a definition of a subformula here. And so what we have is that a subformula of, so we're going to call it the subformula psi here, of a formula phi. So we're saying, hey, here is a subformula, a kind of part of this larger formula phi here, is any well-formed formula that occurs as a part of phi. So including, this is the important part, including phi itself. So the strange part is we're saying that this formula is a subformula of this one, provided this formula is a part of this one. And so this kind of leaves us with a feeling like we don't really understand what the definition is at all, because we don't really understand what does it mean for one formula to be a part of another one. So here, we'll define what that means as a part. So we'd say a formula psi is a part, and in this case, we're referring to proper part of a formula phi. So we're saying this formula psi here is a part of this one, phi, if and only if psi here, which is our part, is a well-formed formula that needs to be or must be constructed or made or built up using our formation rules to construct the phi. So we're saying this formula psi here is a part of this formula phi here, provided we have to actually make this formula psi in order to make phi. But in our case, since we're defining a part, we're not saying phi itself. So we're saying, the smaller elements that we need to construct in order to make this larger item phi here, but not phi itself. So here we have a formula not P, and we want to talk about its subformulas. So the subformulas would be all of the parts of not P, including not P itself. So the part of not P is any formula that we need to make in order to construct not P, but not including not P. So the only proper part of not P is just P. So this is the formula that we'd have to first make. We'd have to say, okay, I want to make this formula not P. The first thing I would do is say that P is a well-formed formula. Then what I would do is say, well, now that I know that P is a well-formed formula, not P is a well-formed formula. So this right here would be the part, and both of them would be the subformulas, because remember, the subformulas are all of the parts, including the formula itself. So it would be all of the parts, which is P, including not P. Let's look at the second example here. See, here we're looking at P or Q. And so the subformulas would be all of the parts, including the formula itself. So you immediately know that the formula itself is going to be the subformula, but it would also include all of the parts. And these would be all the formulas that we need to make in order to make this formula P or Q or PVQ. And that would be P and Q. And then we need to include the formula itself, so it would be P or Q. Here we have a more complicated formula, which is not P or Q. And so the subformulas would be all of the parts, all the formulas that we need to create, including the formula itself. And that would include P, not P, Q, and then the entire formula. And then lastly, we have not P, right arrow Q. Technically, this should be this formula. There should be 2 parentheses, but for all intents and purposes, it doesn't really matter. We have all of the parts, including the formula itself. So this would be P, Q, P or P right arrow Q, and then the formula itself. So syntax isn't the most interesting aspect of logic, but it is helpful. And some of the concepts that are defined syntactically or considered grammatical concepts are really useful for defining important other ideas that are more interesting. Now, so one such idea is the notion of an occurrence of an operator. What we mean is, and even though this sounds pretty like fancy, all an occurrence of an operator is just a particular token or operator in like space and time. So, the example would be, let's look at this formula here and notice that there are 2 negations. Now we might say, hey, there's a negation in this formula and it's just not kind of clear. Yeah, there is a negation, but we want to talk about like one specific one. So when we're talking about a specific instance of an operator, what we are talking about is an occurrence of an operator. So this is just the terminology that will be made use of just to talk about specific single operators that occur in a specific location. A lot of times you won't need to really use this terminology. You could say, oh, just the leftmost negation or the negation next to the P. This will work for whatever purpose that you might have, but this notion of an occurrence will be useful for defining other ideas. So let's look at the definition of a scope of an operator. So when we're talking about the scope of an operator, we are talking about the scope of an occurrence of an operator. So we're talking about the scope of a specific operator located at a particular place. And when we're talking about the scope of an operator, we're not talking about it in the abstract. We are talking about it in terms of its place in a particular formula. So when we're talking about the scope of an occurrence of an operator, we're talking about what is the scope in this particular formula phi, which is just some random formula. And so the scope of that occurrence of an operator is the smallest subformula of phi, so of the formula that we're talking about here, that contains that occurrence of that operator. So this particular definition looks kind of crazy to me. So let's kind of unpack it a little bit. Now, I think the way to unpack it is through some illustrations or some examples. So let's take a look. So here we have 2 formulas. We have the formula not P. And we want to talk about the scope of, let's say, this negation. Now, we can define it in terms of the smallest subformula that contains that occurrence of that operator. So in building up this formula, we have 2 subformulas. We have P and not P. So of the formula not P, there are 2 subformulas. Now, when you look at this, you could say, well, what is the smallest subformula that contains this negation, that contains this operator that we are asking about its scope? Well, P does not even contain an operator, so that can't be it, because the scope of that operator is the smallest subformula that contains that occurrence of that operator. And so it must be not P. So the scope of this negation, this particular occurrence of this operator, is the entire formula, or we could just say not P. So yeah, that's what it is. The scope of that negation is not P. Let's look at another example. So here we have P V Q. So we have this formula and we want to ask about what's the scope of that V? Well, it's the smallest subformula that contains that V. So when we look at our subformulas, the formulas that we would need to construct in order to build that formula, including the formula itself, we would see there's P, there's Q, there's also P, V, Q. So the smallest subformula here that contains that V would be the entire formula. So the scope of this V is the entire formula. Let's look at one more example. This one's a little bit more complicated. So in this case, what we have is this formula, not P, V, Q. And so now we might, run into some errors, but we also can ask two different questions. We can ask the question about what's the scope of this V, and we can ask this question, what's the scope of this negation right there? So I think the one I'm interested in is what's the scope of this V here? Well, it's going to be the smallest subformula that contains this V, that occurrence of that operator. And so when we look at our subformulas, if we were to build up that formula, we would see that the smallest subformula that contains V is the entire formula. So the scope of V is the whole thing. Now, when we look at, let's say, the scope of this negation here, this not symbol, we come to a different conclusion. The scope is not the entire formula. Instead, we're going to look at the smallest subformula that contains this not. And in this case, it would just be this not P. So the scope of this not P isn't the entire formula, like in the case of V, but is just this not P there. So the next thing to note is that some operators have more scope than others. That is, they include those operators within their scope. And we saw an example of this when we looked at not P, V, Q. One thing that we saw was we had the operator of negation, which only applied to this not P, and we had this operator V, which had the whole formula in its scope. And one thing that you'll notice is that the operator for V contains the negation here in its scope, contains this not in its scope. So this builds to the idea of the notion of a main operator, the operator that has all other operators, all other occurrences of operators within its scope. I'll give a definition of the main operator. I'll look through some examples, and then we'll go through a procedure for being able to identify the scope of an operator, as well as how to identify the main operator by building up the formula itself. So the main operator of a formula in propositional logic is the truth functional operator with the greatest scope. It's the operator that contains all other operators within its scope. In our first example, the answer is pretty trivial. When we're asking what the main operator of this formula is here, we see that we have this not P. The main operator is the only operator that is present, which is that negation right there. When we look at the second example, we have P caret Q. We don't really have to kind of debate too much about what the main operator is because there's only one operator. The operator with the most scope is the only one that's present, and that in this case, it would be this caret. In this example, though, we have a potential, we might make a mistake about identifying which operator is the main operator. We have the negation, and then we also have the V, but this is one that we've kind of looked at before. The operator with the most scope, the one that contains other operators within its scope, is this V here. And the reason for that is because the scope of that negation is just the P. But you'll notice that the scope of the V is the entire formula. So it includes this subformula within it, or as a part of it. And then the last example, we have negation or not, and then we have some parentheses, P, right arrow, Q. The main operator here is the negation. It has its scope is the entire formula, and so it includes within its scope this right arrow there. One of the most fundamental skills in logic is being able to identify the main operator of a well-formed formula. In this video, we'll talk about how you can identify that main operator using the formation rules or constructing the well-formed formula. So here's the basic idea. If you want to be able to identify the main operator of a well-formed formula, all you need to do is build it up using the formation rules of logic, or the grammatical rules, or the rules that allow you to take the symbols and create the formula. The main operator will be the operator that you introduce at the end. That is, when you apply the last formation rule to create the formula itself, that operator that you introduce will be the main operator. Let's take a look at some examples. So we'll start with the simplest possible example. Let's say we have a formula and the formula is not P. So we want to know what the main operator is. For many people, this is going to be comically simple, but just bear with me for a second. Let's construct this formula. Well, if we were going to construct the formula, we would say, well, P is a well-formed formula, and we would cite the formation rule R1 or rule 1, which says every propositional letter is a well-formed formula. The next step would be to say, well, if P is a well-formed formula, then not P is a well-formed formula. And the rule that would justify this is R2, which says you can take any formula and negate it. Technically, we should put parentheses around this particular proposition, but in this case, the parentheses don't really matter. So now we've built the formula. We've built this formula not P. And so we can ask ourselves, when we applied the last formation rule, what was the operator that we introduced? If you take a look here, the operator that we introduced was this negation. And so this negation is the main operator of the formula. It is the operator that has the greatest or most scope. In other words, it's the operator whose scope is the entire formula. Let's look at some more complicated examples. In our next example, we'll look at the following formula. It's P and Q or R. And so here we have a sort of non-trivial decision in the sense that there are two operators and we have to decide which one of these is the main operator, which is the operator with the most amount of scope. Again, one way you can determine this is to simply build the formula, and the operator that you introduce at the end of its construction will be the main operator. So let's build this formula. We would start by saying, well, all these propositional letters, P, Q, and R, are well-formed formulas. There's a formation rule that says that. So P, Q, and R are well-formed formulas. Then what we would say is, well, since P is a well-formed formula and Q is a well-formed formula, then their conjunction is a well-formed formula. So the second step would to say, since P is a well-formed formula and Q is a well-formed formula, since both of these are woofs, it would follow using, I think it's rule 3, that P and Q, the conjunction with parentheses around it, is a well-formed formula. So our last step is to add on this R here. And so what we would do is say, well, we've established from line 2 that P and Q is a well-formed formula. And we also know from line 1 that R is a well-formed formula. So both of those are woofs. Well, there's a rule that says you can take these two well-formed formulas and put them together by placing a disjunction between them. So we would say that P and Q, that's the first formula, and then also R, we can put the disjunction between them, parentheses around the whole thing, is a well-formed formula. And so we have constructed the well-formed formula. Now, our goal here isn't to build formulas. Again, it's to identify the main operator. And as we said, the main operator of this particular formula will be the operator that's introduced in the last stage of construction. So what's the operator that we introduced in the last stage of construction? Well, it is this V here, or the sign for disjunction. So the main operator in this formula here is that V, or sign for disjunction. Now let's take a look at another example. In this case, we'll take a look at the following formula, which is not parentheses, parentheses, P or Q, close parentheses, close parentheses. Now, I would say pause the video here, give it your best attempt by constructing the formula first, and then identifying what the main operator is. Okay, so hopefully you have paused the video, but again, our process of determining the main operator here by constructing the formula is the same. We would start by looking at the propositional letters that are found in this formula. So we'd have P and Q. Both of these are well-formed formulas. The second step would be to construct this disjunction. Since we know that P and Q are both well-formed formulas, it would follow that P or Q is a well-formed formula here. And then the last step would be to say, well, since we know that P or Q is a well-formed formula, we establish this at line 2. So we could write, well, P or Q is a well-formed formula. Another formation rule says you can take any formula and then put a negation in front of that formula. So it would follow that not, we need to put parentheses around the whole thing, P or Q is also a well-formed formula. So again, we can ask ourselves, what is the main operator of this particular formula? Well, it is the operator that we introduced in the final formation rule. Well, the operator we introduced was this negation. And so the main operator of this particular formula here is that negation on the leftmost side. Let's look at one more example. And so the example we'll take a look at here is not P or not Q. So here would be the formula if we constructed it using the formation rules, but I'm going to simplify it a little bit because all of those parentheses are a little bit difficult to look at. So we could simplify this as not P or not Q. So again, we have a couple different options. There's two different negations. There's a sign for disjunction, and we might be asked, what is the main operator of this formula? What is the operator that characterizes the formula or has the most scope or has as its scope all of the formula? And so to determine this, we can just build the formula. So we would start again by saying, well, P and Q are well-formed formulas because all propositional letters are well-formed formulas. We got this P and this Q. And then the next step would be to create not Q as well as not P. So if P is a well-formed formula, then it would follow that not P is a well-formed formula. If Q is a well-formed formula, this Q we've already established from line 1, then not Q is a well-formed formula. And so now we've established that not P is a well-formed formula, not Q is a well-formed formula, and we can take those two formulas and put them together, placing this sign for disjunction between them. So since we have not P is a well-formed formula and not Q is a well-formed formula, then it would follow using the formation rule that allows you to create disjunctions that not P or not Q is a well-formed formula. So we built the formula, and now we have a way of identifying the main operator in this formula here. It is the operator that we introduced at the end. This would be the sign for disjunction, or that V. And so the main operator of this formula here is that sign for disjunction. Now, for all practical purposes, you are not likely to construct the formula every time you want to identify the main operator. Eventually, you'll become comfortable with identifying the operator or seeing how the formula would be constructed and not have to walk through it step by step. But I think learning about this connection between the main operator and the construction of the formula is both helpful at the beginning for learning to identify the main operator, and then also it will be important in other aspects of your learning of logic.
Hi ladies and gentlemen, here's another video on the language of propositional logic. This time I'll talk a little bit more about the syntax of the language of propositional logic. In particular, I'll talk about 5 different complex well-formed formulas, what it means for a formula to be a literal negation of another, and 3 conventions for simplifying the presentation of well-formed formulas. So first off, in an earlier video, I talked about a distinction between an atomic well-formed formula and a complex well-formed formula. This distinction was that an atomic well-formed formula is a single propositional letter, whereas a complex well-formed formula is any well-formed formula with at least one truth functional operator. Now, these complex well-formed formulas can be further classified according to their main operator, that is, the operator with the most scope. And so, well-formed formula with a negation as the main operator is a negated WOF. A well-formed formula where the caret or the sign for and or the operator for and is the main operator is known as a conjunction. Where the V or operator for or is the main operator is a disjunction. Where the right arrow is the main operator is a conditional. Where the double arrow is the main operator is a biconditional. Now, some of the components or subformula of these 5 different complex well-formed formulas have their own names. The conjunction, where the and is the main operator, is composed of 2 conjuncts, P and R. The 2 sides of the conjunction are known as conjuncts. The disjunction has 2 parts, and those 2 parts are known as the disjuncts of the disjunction. Now, the conditional is a little bit different. In the subformula to the left of the right arrow is known as the antecedent of the conditional, whereas the formula to the right of the right arrow is known as the consequent of the conditional. Next, I want to turn to a discussion of what it means for a formula to be a literal negation of another formula. Now, one way of thinking about this is to say, well, how do I take a formula and form its literal negation? And the way you do this is to simply put parentheses around the formula in question and add a negation to it. If you remember the formation rules, of which I talked about in an earlier video, the way you'd form a literal negation of a formula is to apply formation rule 2, which forms a negation of a formula. It's important to note that when we are talking about the literal negation of a formula or a proposition, we're talking about the negation of the entire formula and not just some smaller subformula of it, some part of that formula. So let's look at a couple of examples of how we form the literal negation of certain formulas. So if we take the formulas on the left-hand side as our example, and the right-hand side will be the negations of those formulas. In the first example, we have P, and to form the literal negation of it, we simply put parentheses around it and add a negation. In the case of 2 here, we have a P right arrow R, and we could put an additional set of parentheses on there and then add a negation, but for all intents and purposes, here we can simply write the negation because there's no ambiguity as to how that negation is operating. It's negating the whole formula rather than just part of it, that is, rather than just P or just R. Likewise, in the third example, we have not P and R. We want to make sure we negate the entire formula and not just the not P or not just the R. And so we can put a negation on the outside, and it's clear that the scope of this leftmost negation is applying to the whole formula. So I want to talk now about 3 conventions concerning parentheses. So these conventions are introduced, and they're not necessary, but they're introduced to make the formulas a little bit easier to read. The first convention involves removing a set of parentheses if the scope of the negation operator is a single propositional letter or is just a negated propositional letter. So here are a couple of examples. On the left-hand side, you see not, and then there's these open parentheses, P, close P. The convention says, well, if the negation is just ranging over a single propositional letter, it's not any kind of confusion as to what it's applying to. It's just applying to that P, so we can drop out the parentheses. In the second example, or the second row, you see the same thing. It's not open parentheses, P, close parentheses. We don't have any confusion of what that negation might be negating. Is it negating a larger subformula or a smaller subformula? We know it's just negating P. Similarly, at line 3 or row 3, we have a set of negations and a set of parentheses. What we see this formula as saying is not P, and there's not any confusion about what that outermost negation, the leftmost negation, is negating. So we're going to simply drop out all the parentheses because there won't be any confusion about the scope of those operators. The rightmost negation is applying to the P, and the leftmost negation is applying to the not P. Second convention involves when we are looking at formulas with lots and lots of parentheses, we might want to make use of different scope operators or scope symbols or characters to kind of more clearly offset the scope of different operators. So we can introduce square brackets and curly braces if we don't want to make use of lots and lots of parentheses, instead want to make use of different types of parentheses to kind of clearly see what the scope of different operators. So let's take a look at two examples. So in the first row, you see there's on the right hand side, you see there's a lot of parentheses, and it might be kind of confusing. And so you might say, well, to make this easier to read, I'm going to drop out one set of those parentheses and add square brackets for their in their place. In the second row, we see a formula with a number of parentheses. One way to more clearly see this is to swap out certain parentheses with either square brackets or curly braces to make the formula more legible and to make the scope of the various operators easier to identify. A third convention is employed when a set of parentheses doesn't serve to disambiguate the scope of an operator. This occurs most often when an open and closed parentheses has another and open and closed parentheses within it without anything else. So for example, in the case of not open parentheses to open parentheses, P, right arrow Q, close parentheses, you see that the outermost set of parentheses has immediately within it another set of parentheses. And so it's easier to see the formula, and there's no confusion about the scope of the operators if we drop one of those set of parentheses out. Hi everyone, in this video I'll talk about the semantics of the language of propositional logic. In the previous video I've covered the symbols and syntax of this language. In this video I'll talk about the semantics, or how the various symbols and formulas in the language of propositional logic are assigned truth values. So thus far, the language of propositional logic as it's been articulated is just a set of symbols or an alphabet and rules for putting those symbols together in well-ordered ways. But with this said, these symbols and the formulas that result from applying these grammatical rules or formation rules are meaningless. They don't have any significance. So the way that these single symbols, as well as the combination of these symbols, get their meaning is by being interpreted. That is, they have a semantics which gives them their meaning. But before talking about the semantics of the language of propositional logic, it's helpful to introduce the general notion of a function. And here I'll do that in a somewhat casual way. So what is a function? A function is a specific kind or type of relationship between two types or groups of things. The first group of things is known as the function's domain, and it's composed of objects or members known as the function's inputs or arguments. The second group of things that is found in this relationship is known as the range, and it's composed of the objects or members known as the function's outputs or values. The relationship of the inputs to the outputs is such that each input is related to one and only one output. So the notion of a function is just a type of relationship between two sets or collections of things, the inputs and the outputs, such that each input is related to one and only one output. So let's look at some examples to get a clear sense of what a function is. So let's consider a function called the lightning color function. This function says that take any color as an input, we'll relate it to an output, which is simply a lighter version of that color. So we can think of, let's say we had a color gray as input, the output would be light gray or a lighter version of gray. If we had brown as the input or argument of that function, the output would be light brown. One thing to keep in mind is a function need not only have one input, we can have a set or group of inputs, but what's important is that set or collection of inputs is related to one and only one output. Just to repeat this point, a function can have 2 or 3 or any number of inputs, but this set or collection can only be related to one and only one output. So let's consider an example, and let's call this the color emotion function that takes 2 colored items. You can imagine, let's say, pieces of clothing, and these colors are the inputs, and it relates it to one and only one output. Let's say it's an emotion, and just to kind of keep the emotions, the number of emotions constrained, let's just say it relates it to either happy or sad. Let's define this color emotion function a little bit more specifically and just take the domain of items as blue and red and the output emotions as happy or sad. And so this color emotion function will say, if the color input of both of the color items from the domain is blue, then the output emotion will be happy. If the color input of either of the colored items is red, then the output emotion will be sad. So here's a couple examples, and I've kind of filled in part of the function already. If we had 2 colored inputs and they're both blue, then the output would be happy. If we have one kind of color input which is blue and the other that is red, then the output is sad. In addition, if we have 2 color inputs, one's red and one's blue, according to this color emotion function, then the output will also be sad. And if they're 2 red, we said that the color emotion function says that if either of the color items is red, then the output is sad. So the output emotion here again will also be sad. Let's look at one more general example of a function before we talk about functions in the language of symbolic logic. So let's take a function that takes 2 colored and pattern rectangles as input. It'll take any kind of combination of colored and pattern rectangles as input, 2 of them, and produce a single rectangle as output. And this output will simply just be the overlay of the 2 inputs. Since there are a number of, if we let the domain be any kind of possible colored and pattern, there'll be an infinite. So we'll just focus on some specific ones here. So here's an example. We have 2 colored pattern rectangles. One is a blue square like looking figure with horizontal lines. The other is a square with red vertical lines, and so those are the inputs, and the output is the sort of taking those 2 squares and putting them on top of each other. In this second example, we have again 2 squares as input. The first has green diagonal lines, and the second has red stars. Now these 2 inputs, or this collection of 2 inputs, is related to one and only one output, and that's the overlay of the 2 patterns, where there is a square with red stars as well as green diagonals. So what does this have to do with logic, and more importantly, what does it have to do with the semantics of logic? So the semantics of the language of propositional logic involve 2 important functions. The first function is what's called the interpretation function. Now this function takes propositional letters, single propositional letters as input, and assigns truth values to these propositional letters. So it'll take a propositional letter and relate it to one and only one truth value, either true or false. But we'll talk more about this in a second. The second function is known as the evaluation function, and this assigns a truth value to a well-formed formula depending upon the truth value of the propositional letters and the operators that compose that well-formed formula. So essentially this one takes the truth value of components of a formula and relates it to one and only one truth value as an output. Let's look at each of these. Now the interpretation function is a function that takes propositional letters as input and assigns them a single truth value, true or false, and we'll abbreviate this as T or F as output. To symbolize this interpretation function, we could simply write I, P equals T. This is to say that the interpretation of the argument or input P has a value or output of T, which is true. Another way to read this is P, the propositional letter P, is true under the interpretation I. Now, propositional letters can be interpreted in one of two ways. It can be interpreted as a single propositional letter can be interpreted as true, and under a different interpretation, it can be interpreted as false. So if we had a different interpretation, let's say it's I sub 2, then P could potentially be false under this interpretation. Now, it's important to realize that an interpretation is an assignment of truth values to every propositional letter that is under analysis. Now, there might be an infinite number of propositional letters in our language, but just when we go to analyze an argument or look at a set of formulas and kind of assess that, we can just simply indicate the interpretation of each propositional letter we're interested in by simply writing IP equals true or IQ equals true and so forth and so on. So one question we may ask ourselves is, how many interpretations are there for n distinct propositional letters? That is, if I'm looking at an argument or a formula, how many different ways can I assign truth and falsity to the propositional letters found in that formula? Well, the answer to that is determined by the formula 2 to the n, where n is the distinct number of propositional letters. So for example, if there's one propositional letter, let's say it's P, there's two ways to interpret it. We can interpret P as true, or we can interpret P as false. For two propositional letters, let's say P and Q, there's 2 to the 2 interpretations. That is 4 interpretations. That is, we can interpret P and Q as true, we can interpret P as true and Q as false, we can interpret P as false and Q as true, or we can interpret both P and Q as false. We'll talk a little more about this later, but I just wanted to point this out that we can use this formula to determine how many interpretations are required to give an exhaustive set of interpretations. Now I want to talk a little bit about the second important function involved in propositional logic semantics. If the interpretation function is used to determine the truth values of the different propositional letters, the valuation function assigns a truth value to well-formed formulas on the basis of the truth values assigned to the propositional letters and the operators that are found in this well-formed formula. So let's look at how this is done. So for any interpretation, and we'll just say that this is I, we can define a valuation function of a well-formed formula in the language of propositional logic. And this is a function that assigns one and only one truth value to each well-formed formula in such a way. So let's look at some of examples. Now, if R is interpreted in a particular way, the valuation function doesn't change anything about this. It says if R is interpreted as true, then R is evaluated as true. Recall that the single proposition is a well-formed formula, and so for the valuation function, it leaves the truth value of the propositional letter alone. So if R is true, then under a particular interpretation, then the valuation of R is going to be true. If R is false, then the valuation also will be false. Where things get a little bit interesting is when, let's say we have a formula that is a negated formula. So let's say we have not P. Now this is defined that if the valuation of P is false, then the valuation of not P will be true. Next, how about the valuation of P and Q? Under what conditions is this the case? What's the case if the input is such that both of the conjuncts P and Q are both true? That is, the valuation of P caret Q is true if and only if the valuation of P is true and Q is true. The valuation of P or Q, that is P VQ, is true if and only if one or the other or both of the disjuncts are true. That is, the valuation of P or Q is true if P is true or Q is true. Next, and we'll talk a little bit more about this one in another video, the valuation of P right arrow Q is true if and only if either P is false or Q is true, or both. That is, if you have a formula where the valuation of P is false or the valuation of Q is true, then the valuation of the complex well-formed formula P right arrow Q will also be true. Finally, the valuation of P double arrow Q is true in either of two cases. In the case where both P is true and Q is true, or in the case where the valuation of P is false and Q is false. So if the interpretation function assigns truth values to all of the propositional letters, the valuation function does what we might say the rest of the work by taking the assignment of truth values to those propositional letters and using them with various valuation rules to assign truth values to the well-formed formulas. And so you can think about it using this diagram. We have an interpretation, and what does it do? It takes every single propositional letter that we're interested in and assigns it a value true or false. Then we have the valuation function, and it will take those interpretations and use them associated with various valuation rules to assign a truth value, T or F, to every complex well-formed formula in the language. Now, in a previous video, I talked a little bit about the notion of evaluation and interpretation functions in the semantics of the language of propositional logic. Here, I'll talk more about the interpretation and valuation function, but I'll do it in a different way and in a more conventional way, I think. So our presentation of the meaning of the symbols and well-formed formulas in the language of propositional logic has essentially involved specifying two functions. The first function is an interpretation function, and this function assigns truth values T or F to the propositional letters, while the valuation function takes those interpretations and uses them to assign truth values T or F to complex well-formed formulas. Now, a second and equivalent way of presenting the meaning or the semantics of well-formed formulas is to make use of truth tables. Now, a truth table is simply a graphical display of the interpretation and valuation function. So consider that any propositional letter can be interpreted in two ways. On one interpretation, P can be assigned a value of true, and on another, it can be assigned a value of false. Now, we can use the truth table to display these different interpretations. We can simply write P on a line, and then below it, write two separate rows that indicate that on one interpretation, P can be assigned a value of true, and on another, it can be false. And we can do this for any number of propositional letters. We simply need to take into account all the different ways that these propositional letters can be assigned truth values, that is, the different combinations. So if we had two propositional letters or a formula that involved two, we would need to take into account the four different interpretations, the four different ways that P and Q could be assigned truth values. And so we could have a interpretation that assigned P a value of true and Q a value of true, an interpretation that assigned P a value of true and Q one false, one that assigned P false and Q true, and one that assigned P false and Q false. So this would cover all of the different ways that we could assign truth values to P and Q. Now, what about negated formulas or negated well-formed formulas? Now, we know that a negated formula is true if and only if P is false, and a negated formula is false if and only if P is true. That is, so if there are two ways of interpreting P is true, and another way, P is false, we can use the truth table to indicate the conditions under which not P is true. So if we interpret P as true, then not P will be false, and if we interpret P as false, then not P will be true. How about the valuation function for conjunctions? Now, the valuation function for a conjunction said that a conjunction is true if and only if P is interpreted as true and R is interpreted as false, and it's false in all other cases. So we can cover the 4 different ways that P and R can be interpreted, and we can use the truth table to display the conditions under which P and R are true. So if we look at the first row where P and R are true, they're interpreted as true, then the conjunction P and R is also true. In the other cases, let's say P is interpreted as true and R is interpreted as false, as in the second row, then the conjunction P and R is false. And the same thing with the third and fourth row. Since a conjunction P and R is true if and only if both of its conjuncts P and R are true, only the first row is the row where P and R will be evaluated as true. In all other cases, it will be evaluated as false. In the cases of disjunctions, a disjunction P and or R is false if and only if both P is false and R is false. Another way to put this is to say that P or R is true, provided one of the disjuncts P or R is true. And we can use a truth table to display, given the different combinations of interpretations, how P or R will be evaluated. So if you look at the truth table here, you can go row by row. In the first row, both P and R are interpreted as true, and the result for the truth value for the disjunction P or R is true. In the case of rows 2 and 3, notice that either in row 2, P is true but R is false, but the evaluation function for P or R says that provided one of the disjuncts is true, then the whole disjunction P or R is true. And the same thing is the case for row 3. Now in the case of row 4, here is an interpretation where P or R comes out as false because neither of the disjuncts P or R is interpreted as true. In the case of conditionals, P right arrow, R is true, if and only if P is false or R is true. So we can look at the different ways that P or R and R can be interpreted and go row by row and see that given some interpretation of P and R, this will determine whether or not P right arrow R is true. So in the first row, P and R are both interpreted as true, and the result is that the evaluation function says that P right arrow R is true. In row 2, P is interpreted as true and R is interpreted as false, and the evaluation function for conditional says that the resulting conditional is false. In the case of rows 3 and 4, given the interpretation specified, the evaluation function says that the resulting complex well-formed formula P right arrow R is true. Now we'll come back to what P right arrow R means, and I just want to kind of point out that these third and fourth row, especially the third row, is somewhat controversial, but I'll cover this in a later video. What's important here is to see what the evaluation function is and how a truth table can be used to display both the interpretations and the valuation under specific interpretations. In the case of biconditionals, a biconditional P double arrow R is true provided both P and R share the same truth value. That is, so it's true provided P and R are true or P and R are false. The truth table can display this as follows. In the first row, notice that P and R are both true, and so the valuation rule for biconditionals says that since P and R are both true, then P double arrow R is also true. Notice that the fourth row, P and R are both false, and the biconditional valuation rule says that the resulting biconditional is also true. However, in the second and third row, notice that P and R don't share the same truth value. In the second row, P is true and R is false. In the third row, P is false and R is true. And so the valuation for biconditional rules, as it's displayed here by the truth table, says that the resulting biconditional, given these interpretations, is false. Hi ladies and gentlemen, in this video I'll talk about the relationship between the language of propositional logic and a natural language like English. Specifically, the focus of this video will be on how to translate from one language into the other. Before we get started though, it's helpful to get a quick overview of what a formal language like the language of propositional logic is. Essentially, it's a set of symbols, a syntax or rules for how these symbols can be put together, and a semantics, a set of rules for telling us what these symbols and their combinations mean. In terms of the language of propositional logic, these interpretations assign truth value to propositional letters, and what are called valuations assign truth value to complex conjunctions or formations of these symbols. Essentially, we have two languages at our disposal. We have an abstract, truth-functional language like the language of propositional logic, a set of symbols that are interpreted in terms of truth and falsity and their functions, and a natural language like English. So one way that these languages can be understood in relationship to each other is in terms of translation. That is, we can look at some English sentences or propositions and see how they might be expressed in the language of propositional logic, and vice versa. So let's begin with a simple, single English proposition that consists of a subject or multiple subjects and a predicate. So for an example, let's take the sentence that expresses a proposition, John is kind. It consists of a subject, John, and a predicate, is kind. In addition, we can think of John will go to heaven, or Sally is nicer than John. These are simple sentences. Each simple single English proposition can be translated into the language of propositional logic by using a single propositional letter. So for example, we can represent or symbolize or abbreviate John is kind with a J, John will go to heaven with H, and Sally is nicer than John with S. In translating English propositions into the language of propositional logic, the choice of letter you choose to translate into is open. It's arbitrary, it's up to you. However, once you choose a letter to stand for a specific English proposition, you can't again use that letter to stand for another English proposition. In other words, you can't have a single letter in the language of propositional logic do double duty. Translated John is kind as J, we couldn't translate John as friendly using J. We would have to pick another propositional letter. The general guide to choosing a letter is we look at the English sentence or proposition and kind of pick a letter that is most prominent in the sentence itself. So for example, in the case of John is kind, we use J because John begins with J. In the case of John is friendly, since J is already used, we'll use F to represent John is friendly. So simple sentences in English can be interpreted in two ways. We could think of these simple sentences as true or false. John is kind is either true or false, depending upon whether or not he's kind or not. Similarly, atomic well-formed formulas or single propositional letters are interpreted or evaluated in one of two ways. Either they're T or F, standing for true or false. Next, what about propositions in English that make use of not or expressions similar to not, like it's not the case that, it's false that, it can't be the case that, so forth and so on? How about John is not kind rather than John is kind? Or it's not the case that John is friendly. These propositions can be said to have the form of not P, where P is a simple proposition. That is, where P, in the case of John is not kind, simply stands for John is kind, and the not as stands for not. These propositions are true when the simple propositions that compose them, the propositions without the not or it's not the case that, are false. So, for example, John is not kind is true if and only if John is kind is false. And similarly, it's not the case that John is friendly is true if and only if John is friendly is false. So, not P propositions are true and false in the same cases as negated woofs in the language of propositional logic. So this suggests that we can translate English propositions of the form not P as negation P. So for example, we can translate John is not kind as not J. And we can translate it is not the case that John is friendly as not F. In this video, I'll discuss how to translate certain simple and complex sentences in English that involve the use of the term and into the language of propositional logic. So in English, simple and complex sentences are often conjoined together, either in a list or by the use of the term and. So, for example, the two simple sentences, John is kind and John is friendly, is conjoined into one sentence that reads, John is kind and John is friendly. Similarly, Mary is successful and elephants are large. This sentence can be seen as two simple sentences. First, Mary is successful. Second, elephants are large, and conjoined into one sentence through the use of the term and. Also, Frank killed the man and was found guilty. This is two separate sentences. Frank killed the man is one, Frank was found guilty is the other, and both of these are conjoined together by the use of the term and. These propositions seem to have the following form, where P and Q are simple sentences, or they could be complex. They have the form P and Q. These types of propositions are true provided all of the propositions that compose the complex proposition are true. The expression P and Q is true just in the case that P is true as well as Q is true. So for an example, John is kind and John is friendly is true if and only if John is kind is true and John is friendly is true. Similarly, and you could do this for the third example as well, Mary is successful and elephants are large. This whole sentence is true, or the proposition expresses is true, if and only if Mary is successful is true and elephants are large is true. Propositions of the form P and Q are true and false in the same cases as conjunctions in the language of propositional logic. Now, if you need a refresher on this, you should check out the video on semantics posted on this channel. So we can translate English propositions of the form P and Q into the well-formed formula P wedge Q, that is, into conjunctions. So for an example, John is kind and John is friendly can be translated into the language of propositional logic as J wedge F, where J stands for John is kind and F stands for John is friendly. Mary is successful and elephants are large can be translated into M wedge E, and Frank killed the man and was found guilty as K wedge G, where K stands for Frank killed the man and G stands for was found guilty, and the wedge expresses the truth function for also expressed by and. In this video, I continue a discussion about how to translate certain sentences in English into the language of propositional logic. In English, simple and complex sentences are often combined by the use of or. People say, you can have Pepsi or Coke. In addition, they say, John is kind or friendly. Notice both of these sentences are the combination of two simple sentences, and that larger complex sentence is formed by the use of or. That is, in the first example, we can say that the two sentences are, you can have Pepsi, and the second is, you can have Coke. And so we combine these two sentences into this sentence, you can have Pepsi or you can have Coke, or more briefly, you can have Pepsi or Coke. The same thing can be said of the second sentence, John is kind or John is friendly. There's the simple sentence, John is kind. There's the simple sentence, John is friendly. And then there's the complex sentence composed of those two simple sentences and the use of the term or. These propositions have the following form, where P and Q are simple sentences or complex sentences, P or Q. These types of propositions are true provided either of the simple propositions that compose these propositions are true. So for example, if someone says you can have Pepsi or Coke, this sentence is true provided you can have one or the other or both. So if someone said you can have Pepsi or Coke and it was true that you could have Pepsi, then we would say that this sentence is true. If you could have Coke, then again it would be true that you can have Pepsi or Coke is true. And if you could have both Pepsi and Coke, we would say that if someone said, you can have Pepsi or Coke, this again would be true. The same thing is the case with John is kind or John is friendly. If John is kind, this sentence is true. If John is friendly, this sentence is true. And if John is both kind or friendly, then again, this sentence is true. So provided one of the simple sentences that compose this expression is true, then the whole complex sentence is true. So propositions in English of the form P or Q are true and false in the same cases as disjunctions, well-formed formulas of the form P, V, Q. And so we can translate English propositions of the form P or Q into the language of propositional logic as P, V, Q. So for example, if someone said you could have Pepsi or Coke, we could translate this as P, V, C, where P stands for you can have Pepsi, C stands for you can have Coke, and the V represents the truth function expressed by or. Same thing is the case with John is kind or John is friendly. We'll let J stand for John is kind, F stand for John is friendly, and the V stand for the truth function expressed by or. But wait, it seems to be that not all uses of or are captured by the truth function for disjunction. In some cases, we mean one or the other of these sentences is true, makes the proposition true, but both cannot be the case. So for example, if someone said Messi or Ronaldo is the greatest football player, we mean one or the other, not both. Same thing is the case with you can purchase a car in your choice of red, black, blue, or green. Here we mean that provided you can pick one of these four options, then this sentence is true. But if someone said, well, you said I could purchase a car in my choice of red, black, blue, or green, and interpreting this as a disjunction, I assumed that I could get it in all of the colors, both red, black, blue, and green. But that's not what's meant here. What's meant here is that you can choose between one of the colors, but not all of them combined. The same thing is the case with Galen or Farah will win the race. If we're talking about a race where there's only one winner, we think this sentence is true provided one or the other sentences that compose it is true, but not if both are. That is, if Galen or Farah will win the race is composed of two sentences, Galen will win the race or Farah will win the race, we think that only one of those sentences makes the whole proposition true, not both. So what these examples express are propositions that involve the use of the term or that are true if one or the other of the constituent propositions are true, but not both. Now this is in contrast to some uses of or which say that the proposition is true provided one or the other or both are the case. So what this seems to show is that there are two different uses of or in English. There's the use of the or that expresses the truth function for disjunction, and that's the one where a proposition is true provided one or the other of the propositions are true or both. And this is the inclusive sense. And this inclusive sense is captured by the V, the symbol in the language of propositional logic. And then there's another sense of or that we could say expresses a truth function, and it expresses a truth function where the complex proposition is true provided one or the other of the component propositions are true, but not both. And so this is the exclusive use of or. So one thing we might ask ourselves is how do we translate the exclusive use of or into the language of propositional logic? We already have a way to translate the inclusive use of or through the V, but what about the exclusive use of or? There are at least two options we could pursue. The first is to introduce another symbol to represent this distinct truth function. That is to express a truth function that captures when exclusive disjunctions are true. That is when one or the other, but not both of the component propositions are the case. So we could write, let's say, V circle cross Q is true if and only if one or the other are the case. So we could say, provided P is true or Q is true, but not both. Or we could try to leverage the existing symbols and the truth functions they express to translate exclusive disjunctions. We could translate P exclusive OR Q as P v Q, and then find a way to express but not both P and Q. This second way is the way that it will be pursued in a later video. And so what I want to kind of point out here is that we won't need to introduce a new symbol into the language of propositional logic. What we can do instead is use the existing set of symbols to express the exclusive use of OR. In this video, I continue a discussion of how to translate certain statements into the language of propositional logic. In particular, I'll discuss how certain sentences of if-then or implies structure gets translated into conditionals in the language of propositional logic. In addition, I'll talk some about problems associated with translating statements of the form if-then or statements that have the word implies in it into a condition. In English, we frequently reason and utter sentences of the form if P then Q or P implies Q. How do we translate these types of statements into the language of propositional logic? According to some, the way that these expressions should be translated is in terms of the conditional, also known as the material conditional, that is, the formula with the right arrow as the main operator, or, to put this in a different way, a statement of the form if P then Q should be translated into language of propositional logic as P right arrow Q. The rationale behind this is that statements of the form in English if P then Q are true and false under the same conditions as the conditional in the language of propositional logic. That is, if P then Q is true and false in the same situation under which P right arrow Q is true and false. To see this a little bit more clearly, or to get a sense of why this is the case, it's helpful to look at one type of conditional, known as a conditional promise. This approach is developed by Mark T. Nelson in a very short and easy to read article called Promises and Material Conditionals. If you have a chance, it's worth taking a look at it. The basic idea is that we can look at a type of conditional known as a conditional promise. A statement like, if I attend your birthday party, I promise to bring you a present. We can look at these types of sentences where if a condition holds, an individual attests that some scenario or event will come about, and think about under which situations is the promise fulfilled, broken, unbroken, and use it as a case to draw a parallel to the truth and falsity of a conditional. So let's take a look at a specific example. Suppose the Almighty makes the following promise to you. If you are kind, then you will go to heaven. Now we can think about under what scenario, under what states has God kept his promise? And so one way to think about this is as follows. We would say that God's utterance is false if his promise is broken. And we would say that God's utterance is true if the promise is unbroken. So suppose you are kind and you do go to heaven. We would say that God's promise here is unbroken. In fact, God fulfills his promise. Given that the promise is unbroken, we would say that God's utterance is true. So the conditional, if you are kind, then you will go to heaven, is true. Well, the same thing is the case for the material conditional in logic. If P is true and Q is true, then the whole complex conditional is true. How about you are kind and you don't go to heaven? Here we would say that God's promise to us is broken. God promised us that we would go to heaven if we were kind. But we were kind and God sent us straight to hell. And so we would say that God's promise is broken and his utterance here is false. Well, the same thing holds true in symbolic logic. If P is true and Q is false, then we say that the complex conditional is also false. The third case is you are not kind, but you go to heaven anyway. In this scenario, God has not broken a promise to us. That is, God said that if we were kind, then we would go to heaven. What he didn't say is what he would do if we weren't kind. And so we would say, given that God hasn't broken a promise to us, his utterance here still remains true. And so the same thing is true in symbolic logic. According to some logicians, if the antecedent of the conditional P is false and the consequent is true, then the whole conditional is true. Lastly, suppose you are not kind and you don't go to heaven. Here again, we would say that God has not broken a promise to us. God said on the condition that we are kind, then we'll go to heaven. And so what God has said here is true. The same thing holds true in symbolic logic. If P is false and Q is false, then the whole complex conditional is true. So here we have a parallel between conditional promises remaining broken and unbroken and the truth and falsity of the complex conditional. So the extension is that all conditionals behave like this. If John is charged with a crime, he will be convicted. We can translate it as J right arrow C. If I am in Toronto, I am in Canada, T right arrow N. If the sun shines today, Jane will be happy, S right arrow H. So one thing to note is that not all if P then Q statements are conditional promises. So even if we assume that conditional promises, statements of the form, if something happens, then I will give you X, can be translated into the form of a conditional in the language of propositional logic. Not all if P then Q statements are conditional promises. Sometimes we utter if P then Q statements, but we're not promising anything. So can these two be translated into the language of symbolic logic? So there's some skepticism as to whether or not this is the case. So one thing to note is that in the case of the material conditional, that is a formula of the form P right arrow Q, the truth of this conditional depends wholly upon the truth and falsity of the antecedent and consequent and the truth function for the right arrow. The key thing to note about this, though, is that the truth of this conditional does not depend upon any meaningfully relevant relationship between the antecedent and the consequent. In other words, P and Q need not have anything to do with each other in order for the formula P right arrow Q to be true. So the point to emphasize here is that a conditional P right arrow Q can be true even if there is no relevant relationship between the antecedent P and the consequent Q. This creates a number of counterintuitive results, and these results are known as the paradoxes of material implication. So to see these counterintuitive results, it's helpful to look at a couple examples. So first, let's start with the assumption that I do not wake up on time this morning. I wake up extremely late, and let's say I wake up so late it's 3 p.m. when I needed to wake up at 8 a.m. So given this condition, the following conditionals are true if we assume that they're true and false under the same scenarios as the conditionals in the language of propositional logic. If I wake up on time this morning, then loop quantum gravity is a better alternative than string theory. If I wake up on time this morning, then Liverpool FC, a soccer or football club, will win the Champions League. And if I wake up on time this morning, then the president will pass some important legislature. Now you might find all of these statements strange. One thing to note about them is that the antecedent, my waking up on time this morning, is not meaningfully related to the consequent. In the first example, the consequent is this situation about loop quantum gravity being a better alternative than string theory. The second one, Liverpool, some football team winning the Champions League. And the third, the president passing some important legislature. And in all these cases, the antecedent and consequent don't seem to have a causal connection to each other or even be relevantly related. Nevertheless, if we treat these statements as being true and false under the same conditions under which a conditional is in the language of propositional logic, then they're all true. That is, each one of these sentences is true in virtue of the fact that the antecedent is false. So since my waking up on time this morning is false, each one of these conditionals or if-then statements is true. So at this point, we might find the valuation of the conditional strange, or we might put up with it and say, well, it doesn't really capture the majority of our uses of if P then Q or P implies Q in daily life. But there are at least two reasons for putting up with this strangeness, or to see these two reasons, consider that there are 16 different ways that the conditional might be evaluated. Now let's narrow down these 16 different ways. The first two rows are relatively uncontroversial. If P then R or P implies Q is true if both P and R are true, and false when P is true and Q is false. What is controversial, as we saw, or where certain questions we have emerge, is when the antecedent P is false and then R is either true or false. Now, one reason for evaluating the fourth row as true is because when the antecedent and the consequent are the same proposition or propositional letter, we think that the conditional is true. That is, we think statements like P implies P or R implies R should be true no matter whether P is true or false. That is, statements like, if rain is made of spaghetti sauce, then rain is made of spaghetti sauce should be true independent of whether or not rain is in fact made of spaghetti sauce. We think that P implies P should be true independently of whether P is true or false. So this just really leaves row 3. That is, statements where P, the antecedent, is false, but Q, the consequent, is true. So with respect to row 3, there are two options. First, we could say that P implies Q is true when P is false and Q is true. This is the standard way of evaluating the conditional. Or we could say that when P is false and Q is true, the complex, well-formed formula P implies Q should be false. There are several reasons why people want to say that P implies Q is true when P is false and Q is true. Here I'm going to give you two. So the first reason are well-formed formulas of the form P and Q implies P should be true even if P and Q is false. So you can imagine Q being false, and if that were the case, then P and Q would be false. But we still think that P and Q should imply P in virtue of the fact that P implies P. So even if P and Q is false, P and Q nevertheless implies P, and so the conditional P and Q implies P should be true. A second reason for keeping the conditional as true when the antecedent is false and the consequent is true concerns validity. Validity is a property of arguments such that it's impossible for the premises of the argument to be true and the conclusion false. So what happens if we allow conditionals to be true when their antecedents are false? Let's take an argument like P right arrow Q and P, and these two are the premises, and then a conclusion of Q. So if we say that the conditional P right arrow Q is true when the antecedent P is false and the consequent Q is true, it will never be the case that we come across an invalid argument. That is, it won't ever be the case that it'll be possible for the premises to be true, P right arrow Q and P, and the conclusion Q to be false. So the point here is that if logic is concerned with validity or truth preservation of arguments, there's nothing lost in allowing the conditional to remain true when the antecedent of the conditional is false. Thus, if we treat if P then Q statements as true when P is false and Q is true, even if we find this result sometimes a little bit counterintuitive, it will never be the case that doing this will yield invalid arguments. Hi everyone, in this video I continue a discussion of how to translate certain expressions in English into the language of propositional logic. In this video I focus on biconditionals. So in English, simple and complex propositions are often combined or joined together by the use of the term or expression if and only if, or IFF for short. That is, there are propositions that we utter and use to argue that have the following structure or form. P, if and only if Q, where P and Q are placeholders for other simple or complex expressions. So for example, John will go to heaven if and only if John is kind. John will be convicted if and only if there is clear evidence that he committed the crime. And the Green Party will win the election if and only if they adopt a more conservative approach. Notice that in each of these examples, there's a complex expression formed of two simpler expressions. And this complex expression is created by the use of the expression if and only if. So for example, in the first sentence, John will go to heaven if and only if John is kind, we have two simpler sentences. John will go to heaven and John is kind, and these are conjoined together by the use of the expression if and only if. So propositions of the form P if and only if Q, where P and Q are placeholders for other expressions, are true if and only if P and Q have the same truth value. In other words, P if and only if Q is true if and only if P and Q are both true, that is, they both have the value of being true, or P and Q are both false. So here's an example. Suppose we want to know the conditions under which an expression like John will go to heaven if and only if John is kind is true and false. Let's consider various scenarios and then assess whether or not the expression John will go to heaven if and only if John is kind is true or false. What this sentence asserts is that on the condition John is in heaven or will go to heaven, then John is kind. And on the condition that John is kind, then John will go to heaven. So essentially what it says is that if one of the conditions holds that John will go to heaven, then the other also will hold. And if one of the conditions does not hold, then the other does not as well. So essentially what it states is that we can't have one condition or state of affairs without the other. Suppose that John goes to heaven and John is kind. Well, if what the if and only if statement says is that John will go to heaven if and only if he is kind, and we have that John goes to heaven and he is kind, then this scenario would make the statement true. Second, we have the statement John goes to heaven but John is not kind. Part of what the if and only if statement asserts is that on the condition that John goes to heaven, then he is kind. But here we have a state of affairs where John goes to heaven, but he's not kind. He's a horrible person. And so we would say that this state of affairs would make the if and only if statement false. Third, there's a state of affairs where John is kind, but John does not go to heaven. This state of affairs would make the if and only if statement false. The reason is because part of what the if and only if statement asserts is that if John is kind, then he will go to heaven. But here we have a state of affairs where John is kind, but he does not go to heaven. Finally, we have the state of affairs where John does not go to heaven and John is not kind. This would make the if and only if statement true. So what we see here is that expressions of the form P if and only if Q in English are true under the same conditions that P double arrow Q are true in the language of propositional logic. In other words, we saw that expressions of the form P if and only if Q are true provided P and Q have the same truth value. That is, P and Q are both true or P and Q are both false. The same thing is true for the biconditional in the language of propositional logic. P double arrow Q is true provided P and Q are both true or P and Q are both false. Thus, in conclusion, we can translate propositions of the form P if and only if Q into the language of propositional logic as well-formed formulas of the form P double arrow Q. Hi everyone, in this video I continue a discussion of the language of propositional logic. In particular, I'll talk about some more complex translations from English into the language of propositional logic. Here we'll focus on the following kinds of expressions. Expressions where there are multiple uses of and, like P and Q and R. Expressions where there are multiple uses of or, like P or Q or R. Neither P nor Q. Not both P and Q. P only if Q. P even if Q. So let's get started. So sets of propositions connected by the truth functional use of the expression and or can all be translated using multiple instances of the wedge or V respectively. So for example, if we wanted to translate P and Q and R, or a sentence of the structure P or Q or R, like John is tall and Mary is happy and Frank is sweet, we could simply use the wedge operator multiple times with a letter for each one of the propositions we want to represent. We can put parentheses around the J and M or around the M and F. It won't matter with respect to the translation. In the case of I will go to the store, or I will stay home, or I will go to the party, this sentence has multiple uses of or, and you can translate each using the V. as follows. If S stands for I will go to the store, H stands for I will stay home, and P stands for I will go to the party, we can represent the whole sentence as S, V, H, V, P. Similarly, we could put the parentheses around the S and H rather than the H or P. In this case, it won't make a difference. One thing to note is that some propositions in English often don't make use of multiple uses of and. So we won't say John went to the store and he went home and he did this. Sometimes we'll use a comma instead and drop out some of those instances of and. This won't make a difference for how you translate it, whether the and is present or it's not present. So John is tall and Mary is happy and Frank is sweet gets translated as J and M and F, or J wedge M wedge F. Similarly, the same sentence where one of the ands is dropped out and we have John is tall, Mary is happy, and Frank is sweet, we'll translate it the same way. Moving on to statements involving neither P nor Q. So some sentences or propositions in English have the structure neither P nor Q. These particular statements are true just in the case that P is false and Q is false, that neither of the two are the case. So we could express this in a different way by saying what it means to say something like neither P nor Q is to say that not P is true and not Q is true. So we can translate expressions of the form neither P nor Q as negation P wedge negation Q. So for example, if we had an expression John is neither happy nor angry, what we're saying here is that John is not happy and John is not angry. And so we can translate that with negations and the wedge. Similarly, if we said the stock market will neither go up nor down today, so for example, we're predicting that the stock market will stay the same or there won't be any movement, we might write not U wedge not D. How about expressions like not both P and Q? So some propositions have the following form, not both P and Q. Propositions of this type, and it's important to note that they don't express the strong claim that not P and not Q is the case. This is expressed by neither P nor Q. What they express instead is that it's not both the case that P and Q are true. So you can think about this as saying that P and Q can't be true at the same time. One might be the case, the other might be the case, but they're both not the case. So one way to translate this or think about translating it is to notice that P and Q is true just in the case that both P and Q are true. And so to say that not both P and Q are the case is to negate this whole expression, to write not open parentheses P and Q close parentheses. So we can translate this as saying not P and Q, or if you prefer, you could say that it's not P or not Q. So for example, if we said that John is not both happy and angry, so what we're saying here is that he could be one or the other, but what he definitely isn't is not both of these. We could write this as negation open parentheses H wedge A close parentheses. Similarly, if we said that John is happy or angry, but he's not both, we could write HVA to express John is happy or angry, and he's not both happy and angry. So we'd use the negation open parentheses H wedge A. So a discussion of not both takes us back to an earlier video where I talked about two senses of or. The first sense is the inclusive sense. This says P or Q, this expression is true if P is true or Q is true or they're both true at the same time. But there was another sense of or, which was the exclusive sense. This sense said that P is the case or Q is the case, but it implied that they're not both the case. So we saw that the inclusive sense of P or Q could be translated with the V. We could simply write PVQ if someone was expressing the inclusive sense of the or and uttering a sentence like P or Q. So what about the exclusive sense? Well, in an earlier video, I noted that there were two options. The first option is to introduce a whole new operator, this O plus operator, and to define the semantics of it as saying, well, this P O plus Q equals true if and only if P is true or Q is true, but not when both of them are true at the same time. But I noted that there was a way to use the existing set of operators to express this exclusive sense of or. Now, the way to do this is to express an or statement, but tack on the additional statement of not both. So if someone said Kobe or Michael is the greatest basketball player, what they're saying is that one or the other is the greatest, but not both of them. So we could translate this by writing K or M, Kobe or Michael is the greatest, and not both. We saw that we could express not both by writing negation, open parentheses, K wedge, M close parentheses. Next, some propositions have the form P only if Q. These propositions express the case that P is not the case if Q is not the case. In other words, they state not P if not Q, which can also be expressed as if not Q, then not P. So when someone says P only if Q, what they're essentially asserting is that if not Q is the case, then not P is the case. Because P will only be there, or some proposition will be there, if Q is there. And so if Q is not there, then P won't be there. So we can translate expressions of the form P only if Q as negation Q, right arrow, not P. So let's look at a quick example. So we might say, well, John will go to the party only if Mary goes. So what this is asserting is that if Mary does not go to the party, then John will not go to the party because he's only going to go to this party if Mary goes. And so we could translate this as not M for if Mary doesn't go to the party, then not J. And the not J stands for John will not go to the party. Or we might write John will be found guilty of a particular crime only if he committed the crime. And we could translate this as not C to express if John did not commit the crime, right arrow for then, not G for John will not be found guilty. Lastly, and I think this is the easiest one, some propositions have the form P even if Q. What these propositions say is that P will be the case regardless of the truth or falsity of Q. And so what this means is, or what is being asserted here, is that P even if Q is simply saying P independent of Q, so the truth or falsity of Q won't matter here. So we can simply translate what's being asserted. We can capture the conditions under which this is true by simply writing P. We can translate P even if Q as simply P. And so to look at an example, we might say John will go to the party even if Mary goes. Now it doesn't matter for the truth or falsity of the statement whether Mary does go to the party or she doesn't go to the party. All that will matter here is whether or not John goes to the party. And so we can translate John will go to the party even if Mary goes as simply stating P. Similarly, the stock market will go up even if no one buys stock. We can translate this as S for the stock market will go up.
When you calculate the truth value of a complex, well-formed formula, what you do is take truth values that are assigned to the propositional letters, which is the interpretation of those propositional letters, use those truth values to determine the truth values of the subformulas in that complex, well-formed formula, and then use the truth values of those subformulas to determine the truth value of the entire complex, well-formed formula. In other words, the truth value of a complex, well-formed formula is always determined by the parts of the formula. Now, sometimes people run into difficulties. They have the truth values assigned to the P's and Q's of the formula, but they're just not quite clear or certain, or they don't feel confident about sometimes which step to take, which subformula whose value we should determine first. Okay, I'm going to give you a tip about how to do that, and this tip is related to construction of the formula. So let's look at an example because I find it easy to learn a lot of these things just through some example. Let's say we had the formula, not P and Q. And we're asked to determine the truth value of this particular formula. And let's just use one assignment of truth values to P and Q. So we know that the truth value of P is true. So let's write true underneath P. So let's write true under there. And let's just say the truth value of Q is also true. Okay, now we want to determine the truth value of not P and Q. Now, the first step, I think, is that most people get is to write the truth values that are under these letters, that is, the truth values assigned to the propositional letters, under the propositional letters in the truth table. So we'd say that if P is true, then P is true in the formula. And if Q is true, then Q is true in the formula. Where people sometimes have difficulties now is, well, what do I do next? Do I take this truth value T and determine the truth value of not P and write a truth value under here? Or do I take the truth value of Q and P and write it under this sign for negation? You might not have difficulty with this one, but maybe in the process of determining some formula, you run into some issues where you are just unsure which truth values to use to take the next step in determining the truth value of the formula. So here's the tip. The tip is simply to construct the formula, because the order in which you assign truth values to the parts or the subformulas, in other words, the order in which you evaluate the formula, is the same or corresponds to the order in which you would construct or build the formula using the formation rules. Again, that's a mouthful, so let's just look at an example. My suggestion is simply to build this formula. So let's build it. So what we would say is, well, we have this formula, not P and Q. We'd start by saying, well, P is a well-formed formula and Q is a well-formed formula. That would be our first step. Then what we would say is, well, since P is a well-formed formula, not P is a well-formed formula. So since P is a well-formed formula, then not P is a well-formed formula. And then our final step would be to take not P right here, see this not P here, and Q, and say, since we've established they're both formulas, we can take them and put them together and put the sign for conjunction between them. So we would say that since Q is a well-formed formula and not P is a well-formed formula, it would follow that not P and Q is a well-formed formula. All right, so remember, the order in which we assign truth values to subformulas is the same as the order in which we construct the formula. So in this case, what do? Well, we have P and Q. And so if we were trying to determine the truth value of this complex well-formed formula here, the first thing we would do is get the values for P and Q. And we have already done that here. We know that P is true and Q is true, and so we've determined the truth value of these parts, P and Q, in the formula. And we signify this by writing true and true under that P and Q in the formula. So our question then was, well, what do we do next? Do we do the not P or do we do the conjunction? Well, look at our construction. Line 2 here says, well, if P is a well-formed formula, then not P is a well-formed formula. So what this is telling us is we're going to take the truth value of P and use it to determine the truth value of not P. So our next step here, let me use a different color. Our next step here would be to take the truth value of P and use it to determine the truth value of not P. So we should try to determine the truth value of not P here. Well, if P is true, then not P will be false. And we're almost done. But we might say, well, when we're looking at this formula, well, which truth values do I use? Do I use the true under P or the false under not P? Do I use this true over here? Which ones do I use? Well, the construction gives you a clear sign of what you should do. It says that when we built the formula, not Q is a well-formed formula and not P is a well-formed formula. And so the conjunction of those two is a well-formed formula. So we're going to assign the truth value to this conjunction. And what we're going to use to do that is the truth value assigned to Q, which is right here, and the truth value assigned to not P, which is underneath this negation. So we're going to use this false and this true here to determine the conjunction. Now, a conjunction is true just in the case that both of the sides, both of the formulas it connects are true. But so since we have a false here and a true here, the truth value we'll write is false. And this false tells us that when P is true and Q is true, this entire formula, not P and Q, is false. So again, the sequence or order in which we flesh out the truth table or evaluate the formula or take the truth values that are assigned to subformulas and use those to determine the truth value of the complex well-formed formula is or follows the order in which we construct the formula. In this video, we'll talk about how to set up a truth table. So the basics of a truth table is you usually have a formula or set of formulas that you want to create a truth table for. So let's take some formula that we want to evaluate. So let's have our formula not P and S, and then let's add one more part to it. Let's make it or P. So here's our formula right there. So step one you can take to be just write down the formula. Step two is to identify the number of distinct propositional letters that are found in the formula. In other words, we look to see, and at this formula we see there's a P and then there's an S and then there's a P, but there's only two distinct propositional letters. There's P and S. So step two is to identify the number and then to write that off to the left. So let's go ahead and do that. Let's write P over here and we'll write S. The next step is to identify the number of rows that we'll need in our table. So we're going to need a certain number of rows that go under P and S in the formula. And so we need a way of determining that. The way we determine that is we just take the number of distinct propositional letters, which in our case is 2, and plug that into n for the following formula, 2 to the n. So if we only had one letter, we would need 2 rows because 2 to the 1 would be 2. In our case, we have 2 to the 2 where n is equal to 2. And so we're going to need 4 rows. If we had 3 propositional letters, let's say we had P, S, and R, then we would have 2 to the 3. And so we would need 8 and so forth. So whatever number of propositional letters you have, you'll input that number into n, and that will tell you how many rows you need. So in our case, remember, we're going to need 4 rows here. Now, step 4, which is the final step in setting up the table, is to write a bunch of T's and F's in those rows. And so what those T's and F's stand for are distinct ways we can assign the value of true or false to those propositional letters. And all 4 rows together will represent all of the different or distinct ways we can assign truth values to P and S. These are known as interpretations. An interpretation is an assignment of a truth value, T and F, or F, but not both, but not neither, to P and S. So we need to fill out all of the ways of assigning truth values to P and S in this row. Now there's a couple different ways you can do this. One way could be just to try to randomly write them out, but we're going to take a systematic approach. So here's our system. Whatever number of rows we have, let's say it's 4, we will take half of that. So this would be 4 over 2. We're taking half, which is 2. And so this tells us the number of trues we will have in our first column, followed by the number of falses we will have. So we'll have 2. So 2 trues and 2 falses. So let's put that in under P right here. So this will be true and true. And then we'll have false and false. The next step is to take half of this number and half of this number. So if we had 2 trues, we would have 1 true because half of 2 would be 1. And if we had 2 falses, half of 2 would be 1. And then we'll repeat this pattern for the rest of the table. So let's take a look at that up here. So we'd have true, 1 true, followed by 1 false, Then we're going to repeat the pattern, one true followed by one false. And in doing this, we ensure that every way of assigning true and false to the propositional letters is covered. There is not another way of assigning the values of true and false to this P and S, because you see that, well, they could both be true. One could be true, the other could be false. One could be false, the other could be true, or they both could be false. There's no fifth value, and we didn't duplicate or leave any out. Now, in the case that we looked at, we had 2 letters, and that told us that we're going to need 4 rows. But let's say we had 3 distinct propositional letters, and so in this case, what we would need is 8 rows. Well, we're going to do the same thing. We're going to take 8 over 2, and 8 over 2 would give us 4 trues and 4 falses. So our first column here for our first letter would be 4 trues and 4 falses. For the next one, we would take 2 trues, which is half of 4, and then 2 falses. And then we would repeat that pattern. So this would be our second column. And so we're going to need one more column for that third letter. And so we would take half of 2. So half of 2 is 1. We would say 1 true and 1 false. And so we would repeat this pattern for our third column. So you can see for each column, we're simply just taking half of the previous column, and then we are repeating that pattern. So as an exercise for you to try to set up the truth table for the following formula. This is P, right arrow, Q, or S. Pause the video, take a moment, and try it for yourself. Okay, now that you're back, what you would want is in this first column, as we mentioned, it would be 4 trues followed by 4 falses. 1, 2, 3, and 4. Then we would have 2 trues followed by 2 falses. And then we would repeat that pattern. So we'd have true and true, false and false. And then for our third column, we would just alternate true, false, true, false, true, false, all the way down the line. We're just repeating this pattern of 1 true and 1 false. And this would give us 8 columns. And these 8 columns each one would represent an interpretation, a way of assigning truth values to propositional letters. And all 8 collectively would represent every way that true and false can be assigned to these propositional letters. So that's how you set up a truth table. In this video, I'll talk about how to complete a truth table. At this point in your learning, you should already know how to set up a truth table and how to determine the truth value of a well-formed formula given a truth value assignment or an interpretation to the propositional letters. Provided you know how to set up a truth table and how to determine the truth value of a well-formed formula given a single interpretation, all we really need to do is put these 2 skills together. And so the way to start would be, what do you want to construct a truth table for? In this video, we're going to look at just trying to construct a truth table for a simple single formula. And so let's pick a formula. Our formula is going to be not P and Q. So when we look at this formula, we see that there are these operators in here. And we also see that there are 2 propositional letters, a P and a Q. So what we'll need to do is we will create a table, and we're going to write P over here and Q over here. We have P, Q, and we're going to just rewrite any of the propositional letters that are found in the formulas we want to construct the table for. The next thing to do is in these columns under P and Q to write every combination of truth value that can be assigned to P and Q. So let me do that. I'm going to write true, true, false, false, true, false, true, and false. Now, these 4 rows are all the different ways that true and false can be assigned to P and Q. What they correspond to is what's called an interpretation, and we have at each row an interpretation. An interpretation is an assignment of a truth value to these propositional letters. Now that we have every way we can assign truth values to P and Q, the next step in building out our truth table is to, for each case of P, we'll take the truth value that is interpreted with respect to P and write it underneath P in the formula. In other words, we're going to take all the information that's found under this column and just directly write it underneath P in the formula here. So we see that P is true at row 1, and so we want to write true over here under the formula. We want to do the same thing for row 2. When we get to row 3, we see that, oh, right, P is false there. So let me write false. And at row 4, P is false. So I'm going to write false again. I'm just taking this information under P and writing it under P in the formula. Now we're going to do the same thing for Q here. You see that Q is true, false, false. And I'm going to do the same thing. I'm going to take this column and write it under Q over there. I'm going to write true because Q is true. Now at row 2, interpretation 2, Q is false. So I want to make sure I write false. Then we have true and false. So I'm going to write true and false. So what I've done here is I've taken this interpretation and I've assigned a truth value to the sub-formulas, the parts of this formula, P and Q. Now, the next step is often the most tricky for individuals who are first starting out with truth tables, and that is, what do I do next? Now, what you would do next is you would try to take these truth values that you have and use them with the valuation function associated with these operators to determine the truth value of the subformulas. In other words, you're going to write truth values underneath this negation and this sign for conjunction, and that's going to tell you, when you write it under negation, what the truth value of not P is, and when you write it under the conjunction, you're going to write it, it's going to determine what the truth value of the whole formula is. So the question that people commonly have is, well, what order do I do it in? Well, here is a trick. The trick is the order in which you compute or write down the truth value is the order in which you created the formula. So what's the order in which I would construct this formula? Well, I would start by saying that P is a wolf and Q is a wolf. That would be the first thing I would do. And then I would say, well, if P is a well-formed formula, then not P is a well-formed formula. So we have not P. And then if not P is a well-formed formula and Q is a well-formed formula, then not P and Q is a well-formed formula. So this is the order in which you would construct the formula, and it's the order in which you will assign truth values to the subformulas. We would first start by assigning truth values to P and Q, which we have already done in these columns here. Then we'll move to not P, and then finally we'll use not P and Q. So with that in mind, let's go ahead and fill out the rest of this truth table. We see that we have P here, and when it's assigned a value of true, what's happening is that this truth value, we are sending it to, let's say, the negation function and saying, well, we have a formula that is true. What does the negation function do to it? Well, it says, if you give me a truth value, the value you give me is true, then I'm going to output or push out a value that's false. In other words, if P is true, then not P will be false here. When we look at row 2, we're going row by row here. Row 2, it says P is true. And so again, we're giving this negation function a value of true as input, and it's going to spit out a truth value. And the value it's going to spit out is the value of false. If you give me true, I'll give you false. If you give me false, I'm going to give you true. That's how this negation function works. So when we get to row 3, we see, okay, now we're giving this negation function the value of false, and so the output will be true. And in the case of row 4, interpretation 4, where P is false, the negation function will say that not P is true. So what we have here under this column right here is we have the truth value of not P. So we've determined not only the truth value of P and Q as well as not P, but now we're going to move on to determining the truth value of the entire formula. So what do we do here? Well, this is another question. Well, which of these truth values do I look at when I'm determining what to write under this caret? We are going to write the truth value underneath this caret to indicate the truth value of the conjunction here. And what we'll look at is the two formulas that the caret connects, the two inputs that it's taking. So we're going to look under the column under the negation, as well as Q right there. So we can ignore the truth value assigned to P. What instead is going to the conjunction function is a value of false and true, the value assigned to the not P, as well as the value assigned to Q. So we want to focus on those two. When we look at the conjunction function, the conjunction is only going to be true if you give it two truth values. If you give it a false and a true, or a false and a false, or a true and a false, it's going to give you false. So it's only going to be true if there are two true values that's given to it. So what we have here at row 1 is false and true, and so the result is going to be false. At row 2, or under interpretation 2, we have false and false, and so the result will write false underneath it. Again, the conjunction will only be true if you give it two truth values. And if we give it false and false, it's going to give us false. At row 3, though, we see that we have true and true. This not P is true, and this Q is true, and so the result will be true. And then at row 4, we have true and false, and so the result will be false. So what we have here is a formula, and we have a representation of all the different ways that this formula can be assigned a truth value for each one of these interpretations. So we'd go about reading this and saying something like, well, if we interpreted P and Q as both true, then not P and Q is going to be false here. On the other hand, if we interpreted P as false and Q as true, then not P and Q is going to be true. So this was just one quick example of how you would walk through and do a really simple truth table for a single formula. In our second example, I want to look at a different formula that's slightly more complex. Let's take a look at P and Q or P. And let's not just determine this formula's truth value for a single interpretation of the propositional letters. Let's be bold and determine its truth value for all of the interpretations. Every way we can assign truth values to P and Q. So we would write P and Q over here, and let's write the truth values underneath here. So P could be true, Q could be true, P could be true, Q could be false. We could have a false and true, and then finally we can have a false and false. Okay, so these are all the different ways that we might assign truth values to these propositional letters. The next step is to fill out the truth table, to take the truth values that are assigned to the parts and use them to calculate the truth value of the entire formula. As we saw, one way to do this is simply to construct the formula and fill out the truth table in the same way we constructed the formula. So let's come over here and construct the formula, and we'll use that as our guide for fleshing out the truth table. So the way we would build this formula is to start by saying, well, every propositional letter that's found in it, Q and P, is a well-formed formula. So we'd say that P and Q are well-formed formulas. Now the next step would be to build this disjunction. We would say, since P and Q are well-formed formulas, that's established from line 1, it would follow that Q or P is a well-formed formula. And here's our last step. Since we've established that Q or P is a well-formed formula at line 2, we've established that P on its own is a well-formed formula, we can take those two formulas and put them together and put this sign for conjunction between the two, and the result is a well-formed formula. So here we'd say, since P is a well-formed formula and Q or P is a well-formed formula, it would follow that P and Q or P is a well-formed formula. So our construction here gives us a clear guide about how to complete this truth table. Let's take a look. And the first step, what we did was say P and Q are well-formed formulas. So what this would mean, if the order in which we evaluate the truth table is the same in which we constructed it, we should assign truth values to P, Q, and P, the propositional letters. So let's go ahead and do that. We would write true, true, false, false. And all I'm doing here is taking the truth value that's assigned to the P in the interpretation and writing it under the formula. I'm going to do the same thing for the second P over here. True, true, false, false. And now I'm going to do the same thing for Q, but I'm going to take the interpretation of Q in this column. Let's just put on the second column here. So we would say true in the first row, then false, true, and false. All right, so we fleshed out a lot of the table, but what's next? Again, the order in which we evaluate things is the same as the order in which we construct the formula. So what should we do here in terms of the construction? Well, we should take the truth values P and Q and use those to determine the disjunction, Q or P. And if we did that, we would take the truth value of Q and the truth value of P and use those with the function for disjunction to determine the truth value of this disjunction here. A disjunction is true provided at least one of the sides or both are true, and it's false only when both of the sides or disjuncts are false. So this would mean, I'm going to use a different color just to make things clear. This would mean that this disjunction is true in the first row. Here we have false and true. This would also be true. Here we have true and false. Remember, a disjunction is true provided at least one of the sides is true. So this would be true. And then we have false and false here. So this final row here would come out as false. Now this column under this V here tells us the truth value of this subformula Q or P. Now we're almost done. The last thing we have to do is to determine the truth value of the whole thing. And that will be indicated under this main operator, or this sign for conjunction here. Now, what do we do? Which of these many columns do we look at? Again, the way in which we constructed the formula gives us a clear guide as to how to go about assigning truth values underneath this sign for conjunction. Here it says, well, if P is a well-formed formula and Q or P is a well-formed formula, then you can take those and put them together and create a conjunction. So what we'll do is we will take P, truth value of P here, and the truth value of Q or P in this under the sign for disjunction over here, and then look at the function for conjunction, which says that the formula will be true provided both of the sides are true. So what we're going to do is take a look at the truth value of P, truth value of Q or P, and provided both of these sides are true, then the result will be true. So let's look. We have true and true, so that will give us true. We have true and true, so that will give us true. We have false here. We're looking under P, and we have true. This will give us false, because remember, a conjunction is false if either or both of the sides are false. And then we have false and false, so this will give us false. So now we've completed this truth table, or in other words, we've determined when this formula is true for every interpretation. And our guide in this process was actually constructing the formula. Let's look at one more example. And so for this example, we'll look at not P and not Q. Now, I think it's worthwhile for you to try to fill out the table on your own, pause the video and try to do it by yourself. And if you get stuck, again, remember the order in which you fill out this table is the same as the order in which you construct the formula. So I've started things out here by setting up the truth table and giving all of the possible interpretations to P and Q. Now, I might say to myself, well, I don't know what to do next. If I did, again, another strong hint is the order of evaluation is the same as the order of construction. So I don't want to make a mistake here. So I'm going to construct the formula and then use that as my guide to filling out this table. Again, pause the video, do it yourself, and then you can kind of check your work. Okay, hopefully you paused it and you're back and ready to check your answer. I'm going to go ahead and construct this formula. What I would start by doing is saying P and Q are well-formed formulas. Then I would say, well, if Q is a well-formed formula, which I have established it is from line 1, then it would follow that not Q is a well-formed formula. Then I would say, well, since P is a well-formed formula and not Q is a well-formed formula, so since P is a well-formed formula, I've shown this from line 1 over here, and not Q is a well-formed formula, then their conjunction would be a well-formed formula. So then P and not Q is a well-formed formula. So this would also be a WOOF. And then if this whole thing is a well-formed formula, then I can negate the whole formula and the result will be a well-formed formula. So since P and not Q is a WOOF, I can negate the entire formula, not P and not Q, and the result will be a well-formed formula. Okay, so now I just have the exact way in which I should fill out the truth table. I'm just going to go step by step. Line 1 here is determine the truth values for P and Q. And so I'm going to do that. I'm going to take the information under this column, which is the interpretation of P and Q, and write it under P and Q, which are subformulas in this complex formula. So I'll say, start with this first column, true, true, false, and false. Then I'll do Q. This would be true, false. I'm using this second column here, true and false. And so I've completed this first step. Next, what should I do? I'm looking at it. I'm not quite sure. I'm going to go back to my construction over here. It says if Q is a well-formed formula, then not Q is a well-formed formula. This is telling me take the truth value of Q and determine the truth value of not Q. All right, I'll do that over here. So since Q is a well-formed formula, since Q is here, we're going to use the truth value for this column and determine the truth value of not Q. So we're going to go each row. Well, Q is true here, so not Q would be false. Q is false here, so not Q would be true. Q is true here, so not Q would be false. And Q is false in the final row, and so not Q will be true. All right, I have completed the second step. Let's move on to step 3. Step 3 is telling me I should take P and not Q and use those to determine P and not Q. So what I'm going to do is take the truth value under P and the truth value under not Q, which is under this negation, and use those values and the function for conjunction to determine the truth value of the entire conjunction. So I'm going to look at these two columns and say, are they both true? If they are both true, then the conjunction is going to be true. But if one or both of them is false, then the conjunction is going to be false. I have true and false here, so this would give me false since they're not both true. I have true and true, and remember I'm looking under the sign for negation, so that would give me true. I have I have false and false. I almost made a mistake there. This would give me false. And then I have false and true, and this would give me false. So now I have the truth value of this conjunction, which is written under this sign for conjunction. And so I have completed step 3 here. Now finally, let's finish it off. Let's complete step 4. So step 4 says if you have a formula, which is P and not Q, and it's a well-formed formula, then you can negate it. And so what this is telling me is use the truth value of that conjunction and determine the truth value of the negation of this conjunction. So in other words, I'm going to take the truth value that is assigned to this conjunction, which determines this truth value of this whole thing under this conjunct here. And I'm going to use this sign for negation to determine the truth value of the entire formula. So I have false in the first row, and then if it's false and we're negating it, the result is true. I have true, and since we're negating the formula, the result is false. I have false. Again, we're looking under this sign for conjunction. Since we're negating it, the result is true. And I have false here. And since we're negating it, the result will be true. So I have completed step 4, and in completing step 4, I've also constructed the truth table. And so now I have a graphical or tabular representation of when this formula is true given an interpretation. Given all the different ways we can assign truth values to the letters, I can tell you if the formula is true under some specific interpretation. For all practical purposes, you are not likely to construct the formula every time you want to do a truth table. But it is an excellent way to learn how to do truth tables, and it gives you a foolproof method for if you ever get stuck about how to determine the truth values of the subformulas or how to complete the truth table.
Hello everyone, in this video I discuss the difference between truth tables and truth trees and talk a little bit about how to set up a truth tree. So the first place to start is to talk about how truth trees differ from truth tables. So one thing to note is what a truth table is. Now a truth table provides a mechanical means for determining whether or not a proposition, set of propositions, or argument has a particular logical property. So for example, we can use a truth table to determine whether or not a proposition is a contingency, tautology, or contradiction, or we could check to see if a set of propositions or utterances is consistent, or we could look to see if an argument is valid or invalid. Now, there are two shortcomings of truth tables. The first is that truth tables tend to be cumbersome when we're looking at arguments or sets of propositions or formulas that have more than two propositional letters. The reason is because truth tables become increasingly complex the number of propositional letters that are found in them. So for example, a truth table with 8 distinct propositional letters, A, B, C, D, and so forth, would require 256 rows. Now this would be a humongous truth table. Secondly, truth tables only work for logical languages that are truth functional. And so we won't be able to use truth tables to analyze logical languages that aren't truth functional. With this said, the advantage of truth trees is that 1, their complexity is not a function of the number of propositional letters in the formula being analyzed. If we have 8 distinct propositional letters in a set of formulas, it won't be the case that we have this hugely complex truth tree. In addition, and I'll talk about this in another video, that the truth tree method is capable of being adapted to more expressive logical languages that aren't truth functional. The next thing I want to discuss is how to set up a truth tree. So typically, truth trees begin with an initial setup involving 3 columns. The first column is a simple column for numbering. It's a column that we'll use to number each one of the formulas or propositions in the tree so we can refer back to it easily. The second column is for writing the propositions or stacking the propositions. These are where all the formulas are going to go in the truth tree. The third column, and this column is optional and won't necessarily be presented here, is for justifying each of the formulas or propositions. This column will indicate why a particular formula is on the line that it is. So let's take a quick illustration. Suppose we had the following 2 formulas or propositions, P wedge R and then also M wedge not P. So here are the 3 columns. The first column is simply numbering propositions that will be found in column 2, and column 2 consists of the formulas that we are putting into the truth tree. The third column is the justification of the formulas. It explains why those formulas are there, and in this case, these are the formulas that we want to analyze, and so we'll simply write P for proposition. So 2 quick notes about the presentation of truth trees here. In most introductory logic textbooks, there's special attention paid to the third column, which is the column for justification. In the presentation of the videos here, I won't pay too close attention to this third column, but I will state why each one of the formulas is on the line that it is. The second note is that although I've presented here how to set up the truth tree, it's important to note that the truth tree setup will vary depending upon what you are trying to analyze. So, for example, if you wanted to analyze a set of propositions to see if they were valid or invalid, or one entailed another, then you would have a specific setup. The same thing is true for consistency and inconsistency. If you wanted to test a set of formulas to see if they're consistent or inconsistent, there's a specific setup, as well as equivalence and contingency, tautology, and contradiction. How's it going, everyone? In this video, I'll discuss truth tree decomposition rules. So first off, what is a decomposition rule? Well, in propositional logic truth trees, a decomposition rule is just a graphical way to display the conditions under which a complex, well-formed formula or a proposition that's decomposable is true. So what the decomposition rule does is it sort of gives us a visual display of the conditions under which a well-formed formula is true. And it does this by making use of simpler formulas such that if those formulas were true, it would make the complex, well-formed formula true. Just a bit of vocabulary. Specific types of complex, well-formed formulas are said to be decomposed, and they're decomposed using decomposition rules. There are 9 different decomposition rules, and each one of these is going to correspond to a specific type of decomposable proposition. One thing to note is that each one of these decomposable propositions will have its own exclusive decomposition rule. So for example, conjunctions, which as we'll see, is a specific type of decomposable proposition, can only be decomposed using its specific decomposition rule, which is conjunction decomposition. Similarly, disjunctions can only be decomposed using disjunction decomposition. So let's take a look at all of the decomposition rules. So let's take a look at all of the proposition types that can be decomposed, their corresponding well-formed formula, and the decomposition rule. Notice that there are 9 proposition types that can be decomposed. These are the conjunction, disjunction, conditional, and biconditional, and the negated form of each, the negated conjunction, the negated disjunction, and so forth. And lastly, there is the double negated well-formed formula. In the far right column, there is an abbreviation for the decomposition rule that would decompose the corresponding formula. So a conjunction of formula of P wedge Q will be decomposed using the decomposition rule wedge D, which is an abbreviation for conjunction decomposition. So while there are 9 different proposition types, and there is a corresponding decomposition rule for each one, essentially there are 3 main kinds of decomposition rules. That is 3 main ways to display the conditions under which a decomposable proposition is true. There are stacking decomposition rules, branching decomposition rules, and branching and stacking decomposition rules. So let's take a look at an example of each in a really sort of abstract or general form. So when decomposing a decomposable proposition, and let's just call it P, but P could be any well-formed formula, a stacking rule will represent that there is one condition under which P is true. So if we had some random formula, let's say it's P hash Q, a stacking rule would stack formulas underneath P hash Q in order to represent the conditions under which that formula is true. So what this example illustrates is that P hash Q is true if and only if P is true and Q is true. A branching rule represents that there are 3 conditions in which the proposition P is true. So if we had a formula P hash Q, the sort of branching graphical display illustrates that P hash Q is true if and only if either P is true or Q is true. Lastly, a branching and stacking rule represents that there are 2 conditions in which P is true. Now, essentially, this is just a combination of the branching and stacking rule. But so if we take a look at the example P hash Q, what we see is that P hash Q is true if either P is true and Q is true, or if not P is true and not Q is true. So let's look at some examples of specific decomposable proposition types and their corresponding decomposition rule. Now, a conjunction is true if and only if both P and Q is true. That is, both of its conjuncts are true. And so we will stack the conjuncts. That is, we want to illustrate that this conjunction is true provided P is true and Q is true. And so we'll use our stacking procedure in order to do this. A disjunction is true if and only if either P is true or Q is true or both. So this gives us three different possible scenarios. And so we'll make use of the branching rule. That is, a disjunction of the form P v Q is true if P is true, or if Q is true, or if they're both true. A negated disjunction, by contrast, is true if and only if not P is true and not Q is true. So this gives us one scenario under which the negated disjunction not P v Q is true. That is, not P v Q is true if and only if not P is true and not Q is true. So the negated disjunction decomposition rule is a stacking rule. A negated conjunction, by contrast, is true if and only if either negation P is true or negation Q is true. Since there are three scenarios under which the negated conjunction is true, we'll make use of a branching rule. And so we'll illustrate not P wedge Q as being true if either not P is true or not Q is true. And the branching scenario suggests that both of these can also be the case. A conditional is true if and only if either not P is true or Q is true. And so this gives us three possible scenarios under which a conditional can be true. If either not P is true or Q is true, or they're both true. And so we can represent this using a branching rule. That is, P right arrow Q is true if and only if either not P is true or Q is true, or both. A negated conditional is true if and only if not P is true, and a negated conditional is true if and only if P is true and not Q is true. And so this gives us one scenario under which a negated conditional can be true. That is, when P is the case and not Q is the case. And so we stack the propositions underneath the negated conditional in order to indicate the conditions under which it's true. A biconditional is true if and only if P and Q are both true, or not P and not Q are true. So this gives us two scenarios under which a biconditional can be true. It's true if and only if either P and Q are true, or not P and not Q is true. A negated biconditional of the form not P double arrow Q is true if and only if P and not Q are both true, or not P and Q are true. So we can express the conditions under which a negated biconditional is true by both branching and stacking. That is, on one side of the branch, we write P and not Q. On the other side of the branch, we stack not P and Q. Finally, a negated well-formed formula, not P, is true if and only if P is true. So this gives us one condition under which the negated well-formed formula is true, and so we can stack. We can simply write P. Hi everyone, in this video on truth trees, I'll talk about truth tree terminology. So let's talk about some terms of vocabulary for talking about truth trees. The first definition is the definition of a branch. A branch consists of all the well-formed formulas obtained by starting from the bottom of the tree and reading upward through the tree. So for example, if we take a look at the following truth tree, we can identify two branches. There's the branch that begins with M on line 5, and we move upward to R, P, M or not P, and then finally P and R. In addition, there's the branch on the right-hand side, which consists of not P, R, P, M or not P, and then P and R. Let's take a look at this a little bit more closely. The following tree has two branches. If we start from the base of the tree, we see that the first branch, or the leftmost branch, consists of all of the formulas that are blue. This tree consists of M, R, P, M or not P, and then P and R. So to obtain the well-formed formulas in a branch, we simply start from the base of the branch or base of the tree and read upward, listing off all of the well-formed formulas found in that branch. The second branch can be found starting from the base of the rightmost side and working our way upward. This branch consists of not P, R, P, M or not P, P and R. Again, the procedure for identifying the well-formed formulas is the same. Next, a fully decomposed branch. A fully decomposed branch is a branch where all of the propositions in the branch or formulas in the branch that can be decomposed have been decomposed. That is, all of the decomposable propositions have been decomposed. In this example, we have two fully decomposed branches. This is because all of the formulas that can be decomposed have been decomposed. That is, lines 1 and 2, the conjunction and the disjunction, have been decomposed at lines 3, 4, and 5. A partially decomposed branch, or perhaps a better term, an undecomposed branch, is a branch where there's at least one proposition or formula in the branch that has not been decomposed. So in this example here, while line 1 has been decomposed at lines 3 and 4 using conjunction decomposition, line 2 has not been decomposed. That is, line 2 is a proposition that can be decomposed but has not been decomposed. In other words, we haven't given a full demonstration or graphical display of the conditions under which lines 1 and 2 are true. We've only sort of illustrated the truth conditions for line 1 by stacking P and R at line 3 and 4. What we haven't done is given a display of the conditions under which both lines 1 and 2 can be true. A branch is considered closed when it contains a proposition or formula P and its literal negation. Now, P need not be the letter P. In fact, it can be any well-formed formula. We illustrate that a branch is closed by placing an X at the base of the branch. In this example, if you take a look at the rightmost branch, this branch is considered closed. The reason for this is because in the set of well-formed formulas found in this branch, there's a proposition and its literal negation. In particular, there's a proposition P at line 3 and not P, its literal negation at line 5. What makes a branch closed is that there's a proposition and its literal negation. So for example, if you had not P right arrow Q and P right arrow Q, notice that these two formulas are literal negations of each other. And so if they were both found in the same branch, the branch would be considered closed. An open branch is any branch that is not closed. In saying that it's not closed, all that we're saying is that there's not a formula P and its literal negation, not P. So if you take a look at the tree found here, the leftmost branch is considered open. If you start from the base of the tree and work your way upward, you see that there is M, R, P, M or not P, and then P and R. Now, none of these formulas are literal negations of each other, and so the branch is considered open. Now, a completed open branch is a fully decomposed branch that is not closed. That is, it consists of a branch where all of the propositions that can be decomposed have been decomposed, and there's not a proposition P and its literal negation, not P. The leftmost branch here is considered a completed open branch. This is because all of the propositions in this branch have been decomposed, and if you'll notice, there's not a proposition P and its literal negation, not P. So the branch is considered a completed open branch. Now, a completed open tree is simply a tree with at least one completed open branch. Of course, it could have more than one completed open branch, but in order for a tree to be considered a completed open tree, all that's required is that there's one completed open branch. So if we take a look at the following tree, this tree is considered a completed open tree. Why? Well, it's a completed open tree because there's at least one completed open branch, which is the leftmost branch. And notice that in this branch, there's not a proposition P and its literal negation P, and so it's a completed open branch. So since this tree has at least one completed open branch, it's considered a completed open tree. Now, a closed tree is a tree where all of the tree's branches are closed. Under every branch of a closed tree, there'll be an X under it. So if we take a look at this example, notice that all of the branches here are closed. That if we start from the leftmost side, we have a proposition not are, and its literal negation are. And if we look at the other branch on the rightmost side, we have a proposition P and its literal negation not P. So here we have a tree where all of the branches are closed, and so this tree is considered a closed tree. Lastly, the descending decomposition rule is less a term for describing some part of the tree or condition of the tree, and more a rule for explaining how certain formulas found in the tree are decomposed. What the descending decomposition rule states is that when decomposing a proposition or formula P, it's necessary to decompose P under every open branch that descends from it. Just to highlight some features of this rule, first, when you decompose P, you only need to decompose it under every open branch that descends from P. So you're not required to decompose it under branches that do not descend from P, and you're not required to decompose P under closed branches, only the open branches. So it's helpful to take a look at an example involving the descending decomposition rule. In this example, we have two propositions, R or P wedge M, and then at line 2, C wedge D. Using the truth tree and decomposition rules, we want to see the conditions under which these two formulas are true. So first, line 3 is the result of disjunction decomposition, that is a decomposition of line 1, a disjunction, and then line 2 involves the use of conjunction decomposition. Notice that when we use conjunction decomposition on line 2, we obey the descending decomposition rule. That is, when we make use of conjunction decomposition on line 2, we decompose it under every open branch that descends from C wedge D. So we decompose it under both the branch that contains R, the leftmost branch, and the branch that contains P wedge M. Well, what about P wedge M? Here is a proposition that can be decomposed that has not been decomposed. Should we decompose it under both branches, just the left branch, or just the right branch? The answer is we decompose it under the right branch. The descending decomposition rule states that we should decompose a formula under every open branch that descends from that formula. The branch containing R, C, D, the leftmost branch, does not descend from the formula P wedge M. That is, we should only decompose P wedge M under every branch that descends from that formula, which is only the right branch. It's helpful to look at an example of conjunction decomposition that violates this descending decomposition rule. So here we decompose P wedge M under both branches. This would be an incorrect use of conjunction decomposition because it violates this descending decomposition rule. It decomposes P wedge M under a branch that doesn't descend from P wedge M. Hi everyone, in this video I talk about truth tree analysis. In particular, I'll talk about how to recover an interpretation from a completed open branch. So first off, the thing to note about analysis is that truth trees can be used or employed to check sets of propositions, single propositions, or arguments for various properties that we might be interested in. So suppose your friend makes an argument and you want to know whether or not his argument is valid or invalid. So you might try to imagine the premises being true and the conclusion false. But another way you could do this is to make use of the truth tree method, which is a mechanical method. Using truth trees, though, requires you to know how to do the following. First, you'll need to know how to set up the truth tree in a specific way to test for the property that you're interested in. That is, if you're interested in valid or invalid, as opposed to consistency or inconsistency, there's a specific way to set up the truth tree in order to test for this property. Next, you'll need to know how to decompose the tree. That is, you'll need to know how to make use of the various decomposition rules to display the conditions under which various formulas are true. Third, you'll have to be able to determine whether a tree is a completed open tree or a closed tree. And then finally, you'll need to know what a completed open tree or closed tree tells you about the set of formulas in the tree. That is, you'll need to know whether or not a completed open tree tells you that an argument is valid or invalid. Perhaps the most important idea with respect to truth tree analysis is what a completed open branch tells us. Another way to think about this is what can we get from a completed open branch? Well, what we can get from a completed open branch is an interpretation of the propositional letters that compose the well-formed formulas that are found in the branch. And this interpretation would make all of the well-formed formulas in the branch true. To put this in a different way, from a completed open branch, we can assign truth values, T or F, to the letters that compose all of the formulas in the branch so that all of those formulas would come out true. So how do we do this? How do we obtain an interpretation from a completed open branch? Well, the method is quite simple once the tree has been fully decomposed. What we'll do is isolate the formulas that cannot be decomposed. These are the literal well-formed formulas. We'll assign a value of T to the propositional letters that are found in atomic well-formed formulas, and a value of F to the propositional letters that are found in the negated atomic well-formed formulas. So it's helpful to look at an example. So imagine that P, Q, and not R are the literal well-formed formulas found in a completed open branch. We can obtain an interpretation by assigning true to the propositional letters that are found in atomic well-formed formulas and false to the propositional letters found in the negated atomic well-formed formulas. In other words, if we have P, Q, and not R in a branch, we'll assign P a value of true, Q a value of true, and R a value of false. So let's look at an example of this. Suppose we have the following tree. We have two formulas to start, and those formulas are decomposed at lines 3, 4, and 5. Once we fully decompose the tree, we see that one of the branches is a completed open branch. That is, it's a branch where all the propositions that can be decomposed have been decomposed, and there's not a proposition P and its literal negation not P found in the branch. The literal well-formed formulas in this open branch are M, R, and P, and we can assign these formulas truth values. That is, we can assign them an interpretation by assigning true to the propositional letters of atomic well-formed formulas and false to the propositional letters found in negated well-formed formulas. Here we only have atomic well-formed formulas M, R, and P, and so we can assign M, R, and P a value of true. Now once we've assigned M, R, and P a value of true, this interpretation would make not only M, R, and P true, but also lines 1 and 2 true. And so just to kind of test this, you could see that if P was true and R was true, then the conjunction P and R would also be true, because a conjunction is true provided both of the conjuncts are true. And since P is true and R is true, the conjunction is true. 2, we have a disjunction M or not P. And we know a disjunction is true provided either one of the disjuncts are true. And if M is true, like the interpretation says, then the disjunction M or not P is also true. So here we've assigned truth values to the propositional letters that would make all of the formulas in the completed open branch true.
Now that we have the definition of a completed open branch, as well as an understanding of how to break apart formulas in a truth tree to get either a completed open branch or a closed branch, the next thing to do is to actually utilize this truth tree method to tell us some information that we want to know. So one property of sets of formulas or sets of sentences is the notion of consistency. So sometimes we'll talk about a set of formulas or a set of promises that an individual makes as consistent or inconsistent. In logic, we say that a set of formulas, and here we're just calling them P, Q, R, Z, but these can be complex well-formed formulas. This set is consistent if and only if there's at least one interpretation. So an assignment of truth values to the propositional letters that would make all of the formulas in that set true. So provided there's one way we can assign truth values to the letters of various complex well-formed formulas to make all of those complex well-formed formulas true, then that set is consistent. More informally, provided all the propositions or sentences can be true, then we have consistency. So with this definition of consistency here, we can utilize our notion or understanding of what a completed open branch tells us. What a completed open branch tells us is that there is a way to assign truth values to the propositional letters that would make all of the formulas in the branch true. In other words, what it tells you is that there's at least one interpretation in that open branch where all of the formulas are true. So we can utilize this idea that there's a way of recovering an interpretation that would make all the formulas in the branch true to tell us something or to determine if a set of formulas is consistent. In other words, we're going to use this truth tree as well as the open branch to determine if the set of formulas that we are interested in are consistent or inconsistent. So here's our definition, or a way of using the truth tree method to determine if a set is consistent. We say that a set of formulas P, Q, R, Z, which is the same one we are analyzing up here in our definition, is consistent provided, or if and only if, that set, where you just kind of stack all of the formulas, produces a truth tree with one completed open branch. So in other words, we can take these formulas, put them in a truth tree, and if they yield a completed open branch, and that completed open branch tells us that there's one way of assigning truth values to the propositional letters that would make all of the formulas true, we know that the set of formulas is consistent. In contrast, we can define inconsistency, or say a set is inconsistent, if there is no interpretation where the formulas, in this case P, Q, R, Z, are all true. So if someone makes a bunch of promises and there's no way that all of those promises can be true, then we say, you've given me a set of inconsistent promises. And remember, if a truth tree does not produce a completed open branch, one thing that this is said to tell us is that there's just no interpretation. There's not at least one interpretation that would make all of the formulas in that tree true. So we can use this idea as a way of testing for inconsistency. We can say that a set of formulas, let's say a set of promises or sentences or propositions that someone asserts, is inconsistent, so can't all be true, if and only if our truth tree that consists of these formulas in the, let's say, initial stack produces a closed tree, which is a tree that doesn't have at least one completed open branch. So let's look at some examples. So suppose we have two formulas here, P or Q, and then Z or R, and we want to know, can these both be true at the same time? Can they be consistent, or is this set of formulas inconsistent? We start by setting up our truth tree, and since we're testing for consistency, we'll simply stack both of those formulas because we want to know, can both of those formulas be true? So here's our initial stack. We just write one right on top of each other. We're saying P or Q and then Z or Q. And we're wondering, in stacking them, we're kind of asserting that they're both true. And so then we decompose the tree using our decomposition rules. And this is the resulting decomposition here. So at line 3 here, what we did was decompose line 1. So the P went over here and the Q went over here. And we use this disjunction decomposition rule since the formula is a disjunction. And then at line 4 here, what we did was decompose line 2. Again, we see that 2 is a disjunction. So we use this disjunction decomposition rule. And we need to decompose line 2 right here under every open branch. So we need to decompose it under the left-hand side under this P. And we need to decompose it under the right-hand side. And so we're left with a tree that has 4 branches. Now, when we look at these branches, one thing that we know is that all of them are open. In other words, there's at least one completed open branch. And so we sometimes signify this by putting a little O for open underneath the branch. And so what this tells us, since there is at least one completed open branch, all you need is one. There's one completed open branch. There's at least one, that this initial set that we're looking at here, this P or Q, Z or R, let's say 2 promises someone made to us, this set here is consistent. There's at least one way of assigning truth values to the propositional letters that would make both of those formulas true. And if you remember about how to recover an interpretation, we can actually recover it by working from the bottom of the branch all the way up. and saying, okay, I can actually tell you when these formulas are all going to be true. So let's take a look at another example here. And there's a small little typo here, so I kind of smudged it out. So in this example, we're looking at two formulas, and we want to know, is this set of formulas, are these two formulas, is it consistent or inconsistent? The setup here involves writing the two formulas. We're just stacking them because we're testing for consistency or inconsistency. Line 3 is the result of using the double negation decomposition rule on line 2. We're just taking off those two negations, since not S or T says the same thing as not S or T. Line 4 and 5 here is the result of using the negation conditional decomposition rule. So we see that because line 1 is a negated formula. Notice the main operator here is that negation, and it is negating a conditional. So we would use the negated conditional decomposition rule. So now that we have everything decomposed except for line 3 there, so this was the only formula, this line 3 here is the only formula we have yet to decompose. What we are going to do is decompose it using a disjunction decomposition rule. Notice line 3 is a disjunction, and so we'll put not S under this left side and T under the right side. So this is the right disjunct, and this is the left disjunct. And then our tree is completely decomposed. So this is 3VD. Now when we go to analyze it, we start from the bottom of the tree, so the bottom formula here, and work up. And notice that there is S, and we also have not S. So there's a formula, not S, and S. So formula and its literal negation, and so this branch closes. On the right-hand side, we have something similar. We have T and not T. So a formula and its literal negation. So this branch is also closed. So since we have a tree with no open branches, that is, all of the branches are closed, the tree itself is closed. And so what this tells us is there's no way of assigning truth values to the propositional letters that would make lines 1 and 2 true. And so if there's no way for us to make lines 1 and 2 true together, the formulas would be inconsistent. We would say that, line 1 and 2 cannot be true at the same time.
Hi everyone, in this video I talk about how to use truth trees to test a proposition or a single formula to see if it's a contradiction, tautology, or contingency. So first off, a contradiction is a proposition or formula if and only if that proposition is false under every interpretation. That is, no matter how we assign truth values to the propositional letters that compose that formula always comes out as false given the interpretation and valuation rules. A truth tree will show that a particular formula P is a contradiction if and only if the tree of the stack that consists of P determines a closed tree. The idea here is that if P determines a closed tree, then there's no interpretation which would make P true. That is, there's no way to recover an interpretation or assignment of truth values to the propositional letters that compose P that would make P true. And so if there's no interpretation that would make P true, then P is false under every interpretation. Then P is a contradiction. Next, a proposition P is a tautology if and only if P is true under every interpretation. A truth tree will show that P is a tautology if and only if a tree of the stack that consists of the literal negation of P determines a closed tree. The idea here is that if the literal negation of P determines a closed tree, then there's no interpretation where the literal negation of P is true. That is, there's no way to assign truth values to the propositional letters that compose negation P that would make P true. And so, if there's no interpretation that would make negation P true, then what we know is that not P is false under every interpretation. That is, we know that negation P is a contradiction. And so, if negation P is always false, then the removal of that negation, that is simply P, is true under every interpretation. That is, if not P is always false, then P must be true under every interpretation. And if we know that P is true under every interpretation, then we know that P is a tautology. And so, in order to test a proposition P to see if it's a tautology, we simply begin the tree with negation P, and if it determines a closed tree, then we know that P is a tautology. Finally, a proposition P is a contingency if and only if P is neither false under every interpretation nor true under every interpretation. In other words, a proposition P is a contingency if it's neither a contradiction nor a tautology. A truth tree will show that P is a contingency if and only if P does not determine a closed tree and the negation of P does not determine a closed tree. In other words, a truth tree shows that P is a contingency provided a truth tree test of P does not show P is a contradiction and provided P is not shown to be a tautology. In other words, if P does not determine a closed tree, then we know it's not a contradiction. And if we test not P to see if P is a tautology and not P doesn't yield a closed tree, then we know that it's not a tautology. And so if P is neither a contradiction nor a tautology, then we know that it's neither false under every interpretation nor true under every interpretation. And so we know that P is sometimes true and sometimes false given the interpretation assigned to it. And so we know that P is a contingency. So let's look at an example of how to make use of the truth tree test for contradiction, tautology, and contingency. We'll just pick an easy to work with example, but we can substitute the formula that we'll test here with any formula that provided it's a well-formed formula in the language of propositional logic. So let's ask, is P wedge Q a contradiction, tautology, or contingency? The first step would be to decide which one of the two truth tree tests we wish to perform. We could test to see if P wedge Q is a contradiction or test to see if it's a tautology. If we're testing to see if it's a contradiction, we simply stack P wedge Q. If we're testing to see if it's a tautology, we stack the literal negation of P wedge Q, which is not P wedge Q. Let's test P wedge Q to see if it's a contradiction. The next step in the truth tree process would be to decompose the tree. We stacked P wedge Q and we've decomposed the tree. Once the tree is completely decomposed, if P wedge Q determines a closed tree, then we know that P wedge Q is a contradiction. If, however, P wedge Q determines a completed open tree, then what we know is P wedge Q is not a contradiction. If P wedge Q is not a contradiction, then it is either a tautology or contingency. But we can't tell from the truth tree test which one of the two it is, and so we'll need to make use of another test. So again, we're going to ask, is P wedge Q a contradiction, tautology, or contingency? We've already eliminated the possibility that it's a contradiction, and so it's either a tautology or contingency. So since we want to test P wedge Q to see if it's a tautology, we'll stack negation P wedge Q. We'll decompose this truth tree. If the tree involving the stack negation P wedge Q determines a closed tree, then we know that P wedge Q is a tautology. If, however, negation P wedge Q determines a completed open tree, then what we know is that P wedge Q is not a tautology. Here we see that the tree involving negation P wedge Q is not a tautology. Given our earlier test that shows that P wedge Q is not a contradiction, we now have two trees that show, one, that P wedge Q is not a contradiction, and two, that P wedge Q is not a tautology. And so if neither P wedge Q nor negation P wedge Q determines a closed tree, then we know that P wedge Q is a contingency. Our two truth tree tests have shown that P wedge Q is not a contradiction and it's not a tautology. Therefore, P wedge Q is a contingency. Hi everyone, in this video I discuss how to make use of the truth tree test to determine whether or not a pair of propositions are equivalent to each other. Let's begin with the definition of equivalence. A pair of propositions P and Q are said to be equivalent to each other if and only if P and Q are true and false under the same interpretations. In other words, whenever P is true, Q is true, and whenever P is false, Q is false. Why might we care about equivalence? Well, for one, we might consider two people uttering a proposition, but uttering it in different ways. For example, Jane might say, if John proposes, then I will agree to marry him. Where John might say, either I won't propose to Jane, or Jane will agree to marry me. Now, these two sentences look different. They have different structure. But according to a logical analysis, they say the same thing. That is, they're equivalent to each other. That is, they're true and false under the same interpretation. Whenever what Jane says is true, what John says is true. Whenever what Jane says is false, what John says here is false. So we care about equivalence to the extent that we want to know if what is being said in two different utterances is the same thing, except it's expressed in a different way. So we said that a pair of propositions P and Q are equivalent if and only if P and Q are true and false under the same interpretations. A truth tree will show that P and Q are equivalent to each other if and only if a tree of the stack not P double arrow Q determines a closed tree. Let's consider why this is the case. So if P and Q are equivalent, then we know that the truth value of P is equal to the truth value of Q. Whenever P is true, Q is true. Whenever P is false, Q is false. If the truth value of P is equal to the truth value of Q, then a formula of the form P double arrow Q is a tautology. This is the case because a biconditional is true whenever the two sides of the biconditional have the same truth value. And if P and Q have the same truth value, then a formula of the form P double arrow Q will always be true, and therefore it will be a tautology. So if a formula of the form P double arrow Q is a tautology, then according to the truth tree test for tautologies, the negation of P double arrow Q will determine a closed tree. That is, if we run a truth tree for not P double arrow Q, it should show us a closed tree, and what this will reveal is that P double arrow Q is a tautology. Alternatively, if a truth tree test for not P double arrow Q does not determine a closed tree, then what we know is that there's an interpretation such that the value of P does not equal the value of Q. And if the value of P doesn't equal the value of Q, then P and Q are not true and false under the same interpretations. That is, they're not equivalent to each other. There'll be a situation where perhaps P is true and Q is false, or P is false and Q is true. So in short, in order to test two formulas, P and Q, to see if they're equivalent, we simply write the formula not P double arrow Q in a truth tree, and if the truth tree, once it's been decomposed, yields a closed tree, then P and Q are equivalent. If it yields a completed open tree, then P and Q are not equivalent. Let's look at a short example that we won't flesh out completely. We might wonder if P right arrow Q and not P VQ are equivalent. To test this, we would first start by taking those two formulas, creating a biconditional out of them, and negating that biconditional. In other words, the truth tree setup for this formula would involve the negation of the biconditional formed from those two formulas. The next step would be to decompose the tree, and then we would check to see if the tree was open or closed. If the tree was closed, then we would know that P right arrow Q and not P VQ are equivalent. If what resulted was a completed open tree, then we would know that the two formulas are not equivalent. Hi everyone, in this video I discuss how to make use of the truth tree test to determine whether or not an argument is valid or invalid. Let's start with the definition of validity. We can define validity by saying that an argument P, Q, Y, therefore Z, where P, Q, and Y are the premises and Z is the conclusion, is valid in the language of propositional logic if and only if P, Q, and Y entail Z. If P, Q, and Y entail Z, what this expresses is that there's no interpretation such that would make P, Q, and Y true and Z false. In other words, there's no interpretation that would make P, Q, Y, and the negation of Z all true at the same time. To see how to make use of the truth tree test in order to determine whether or not an argument is valid or invalid, consider that a closed tree for a proposition or set of propositions, and let's just call it P, indicates that there is no interpretation such that P is true. In other words, if we place P in a tree, decompose P, and find that the tree is closed, then we know that there's no way of assigning truth values to the propositional letters that compose P that would make P true. If this is what a closed tree indicates, then a closed tree for P, Q, Y, not Z would indicate that there's no interpretation that would make P, Q, Y, and not Z true. And if there's no interpretation that would make P, Q, Y, and not Z true, then we would know that P, Q, Y, therefore Z is valid. So in short, we can test an argument like P, Q, Y, therefore Z using a truth tree by taking the stack of formulas P, Q, Y, not Z, and if that stack of formulas yields a closed tree, then we know the argument is valid. If it doesn't yield a closed tree, then the argument is invalid. That is, a completed open tree for P, Q, Y, not Z would indicate that the argument P, Q, Y, therefore Z is invalid. Let's take a look at an example, and we'll just sort of sketch an example to see how the truth tree method works here. So suppose we had an argument that consisted of P, Q, and Y, therefore Z, and we wanted to see if it was valid or invalid. First, we'd set up the tree by stacking the premises P, Q, and Y and negating the conclusion. Then we decompose the tree. And third, we check to see if the tree was completed open tree or closed tree. If it was a completed open tree, then we would know that the argument is invalid. If it were a closed tree, then it would be valid. So here's a kind of sketch, although here we aren't making use of any decomposition rules. What we do is take the formulas P, Q, Y, and the negation of the conclusion, not Z, and stack it on lines 1 through 4. From there, we would go and decompose the rest of the tree using the decomposition rules discussed in an earlier video. If we found that all of the branches closed, then we would have a closed tree and we could say that the argument is valid. If there were at least one completed open branch, then we know that there's an interpretation that would make it possible for the premises to be true and the conclusion false, and so the argument would be invalid. In this video, I'll talk about the nature of a proof, two notions of entailment, and what the deductive apparatus is for the language of propositional logic. So first, it's helpful to think a little bit about when we talk about good arguments and bad arguments. Sometimes we say that a good argument is one where the conclusion, some formula that we're arguing for, some proposition we're arguing for, we say that this formula or proposition is entailed by a set of premises or reasons that we have for that particular conclusion. But this notion of entailment, where when we say a conclusion is entailed by a set of premises, is a little bit ambiguous. So we want to parse this out a little bit. A set of well-formed formulas can be said to entail another well-formed formula in one of two different ways. The first is semantic entailment. We say a well-formed formula is semantically entailed. A conclusion is semantically entailed by a set of well-formed formulas, if and only if there's no way to interpret the premises in the conclusion that would make the premises true and the conclusion false. The basic idea here is that if we go about taking the smaller sentences or formulas that compose these well-formed formulas, which may be complex, if we go about assigning truth values to these smaller formulas, there's no way we can make the assignment of true and false to these smaller formulas that would make all of the premises true and the conclusion false. This notion of semantic entailment is tied up with, there's ways to kind of check this for propositional logic with truth tables and truth trees, and this is covered in an earlier video. The key thing here, though, is just to realize that there is a notion of semantic entailment, which is simply put, there's no way for the premises to be true and the conclusion false. So if the premises are true, then the conclusion is also true. A well-formed formula is syntactically entailed. Here's another different sense of entailment by a set of well-formed formulas if there's a proof or derivation of that well-formed formula. This notion of a syntactic entailment is sometimes called proof-theoretic entailment. So what we're going to explore here is this notion of syntactic entailment. So to get a clear sense of the notion, we're going to need to clarify a couple additional concepts. The first is the notion of a derivation or proof, and the second is the notion of a deductive apparatus, or the various rules that take us forward steps in a proof. Once we clarify these notions, we'll go back to this notion of syntactic entailment when we say that a formula is syntactically entailed by a set of formulas, and we'll be able to get a clear sense of what this means. So we say a derivation of a particular formula, let's call it Q. All a derivation or proof is a finite, so not an infinite, string of well-formed formulas. So it's one formula, one formula, one formula, one formula, just a kind of list or sequence of well-formed formulas from another set of formulas, which we'll call gamma, where the last formula in this sort of sequence or string of formulas is Q, and each of the formulas in this string of formulas is a premise, assumption, or is the result of preceding formulas and the deductive apparatus. So let's take a look at what this kind of means here. Let's break this definition down a little bit. So when we talk about what a derivation is or what a proof is, the first thing is we're just saying that it's a string of well-formed formulas. It's nothing more and nothing less. But this string of formulas needs to meet certain conditions. The first condition is that the last well-formed formula in the string is the formula that is being proved, or aka, in the conclusion. So if we say we have a proof of Q, then we have a string of formulas where the last formula in the string is Q. The second condition is that every well-formed formula has to be justified in a way. It has to have, if it's in that string of formulas, it needs to either be a premise, so it's something that we just take to be true, it needs to be an assumption, something that we're just going to assume to be the case, or that well-formed formula is proved, it's sort of justified or is legitimized in virtue of the deductive apparatus. Now, we haven't talked about the deductive apparatus, and we'll make that clear in a moment, but the key thing here is that the deductive apparatus, it allows for certain formulas to be in the string. So what is this deductive apparatus? The deductive apparatus for the language of propositional logic is just a set of rules of inference, rules of reasoning, or we might call derivation rules. They're just abstract, highly general rules that allow us to write down certain formulas in a proof. There are rules, you can think of them as rules of reasoning. They allow us to take certain formulas that we already have and move to new or different formulas in the proof. In order to kind of abbreviate this list of rules, we'll abbreviate it as PD. So it's helpful to get a kind of more intuitive notion of the deductive apparatus, and we can think about this in terms of everyday life. So let's take two people, Tech and Liz, and we'll just assume that Tech and Liz, they agree about a bunch of stuff. They have similar life experiences, they agree upon the results of similar scientific studies, they have similar values, so we can sort of abbreviate all the things they accept as true in terms of gamma. And all gamma is just a list of formulas, sentences, or propositions that kind of express the things that they accept as truth. Now, we can think, though, about Tech and Liz disagreeing a little bit about what follows from gamma. We can suppose that Tech says, if gamma is the case, then propositions P, Q, and R follow. They're entailed by gamma. You should accept them as well. But in contrast, Liz might say, no, I don't really see that. You say that P, Q, and R follow from gamma or are entailed by gamma, but I don't really see how that's the case. One thing to note here is that Tech and Liz, they aren't disagreeing about the facts of the world. Remember, they have the same experiences, they accept the results of scientific studies, they agree upon the facts. What they disagree about is whether or not P, Q, and R, these letters right here that are just expressing proposition or states of affair that can be true or false, what they're disagreeing is whether or not it follows from gamma. So they might say, okay, well, we just have this vague notion of what follows from what. We might try to make this a little bit more explicit. We're going to kind of fix this problem and to get to the bottom of whether or not P, Q, and R follow from gamma. So what they might do is say, okay, let's come up with a list of rules that start from gamma, start from those premises, start from these facts that we accept to be the case. And this list of rules allow us to kind of move from gamma to reason to other formulas other propositions, other things that we accept to be true. And so all the deductive apparatus is in general, the general idea is just a really highly general, abstract way of formulating the rules that allow you to move from one set of propositions, one set of formulas to another set of formulas. Okay, so we talked a little bit about what a proof is, just kind of string of formulas that meet certain conditions. We talked a little bit about the deductive apparatus. Now we're going to kind of return to this notion of syntactic entailment that we talked about at the beginning. So a syntactic consequence or a syntactic entailment is the following. To put it one way, we can say that a formula Q is a syntactic consequence or is syntactically entailed from a set of, or by a set of formulas gamma in the language of propositional logic, if and only if there's a derivation or proof using the deductive apparatus PD of Q from gamma. So the idea here, there's this sort of short and sweet of it is, we can say that Q is syntactically entailed by a set of formulas gamma, if and only if you can use this list of rules that we kind of talked about to move from gamma all the way to Q. You can kind of reason from gamma using the rules that we lay out to Q. To kind of put this, to show that the Q is a syntactic consequence of gamma, we'll write gamma, the single turnstile Q. And all that says is gamma syntactically entails Q, or there's a proof such that we can move from gamma all the way to Q. Let's look at a more concrete or a little bit slightly more fleshed out example. We might write PMR single turnstile Q. And all that's being said here is that Q is a syntactic consequence of PM and R. In short, that there's a proof that begins with P, M, and R. These are the premises that we accept to be the case, and ends with Q. Now that we have a clear sense of what a syntactic entailment is, what a proof is, and we have the general outline of the deductive apparatus, the next thing to look at is how to solve proofs. And one of the steps towards solving proofs is setting the proof up. So let's take a look at an example. Here we have a syntactic entailment, that is P and R, if Y then R, entail Z. So what this says is that Z is a syntactic consequence or is entailed by P and R if Y then R. In other words, there is a derivation or proof beginning with P wedge R, Y right arrow R that will, through a sort of sequence of steps using the deductive apparatus, we can ultimately conclude in Z. The question is, well, how do we show this derivation? How do we actually do the proof? How do we fill in the middle part, that is the formulas necessary that concludes with Z? So here we'll look at how to set the proof up, and in later videos I'll look at how to kind of fill in these middle steps. So first, a derivation or proof begins with initial setup, and we'll take a particular approach that makes use of three main columns. The first column just is listing the formulas or premises or any of the lines in the proof itself. This will be helpful just so we can refer back to them if we need to talk about them, and then also just for reference sake if we have to refer back to them because we make use of a particular rule of reasoning or rule of inference, and we want to say, oh, I used line 2 and line 4, formula 3 or formula 6. The second major column is this column that's going to consist only of formulas. This is strictly speaking the key component of a proof, because we said a proof is just a string of formulas, and this middle column is just going to kind of be this string of formula, but we're going to kind of create this vertical column of formulas. The third column is the justification of the formulas in the proof. And if we need any kind of heuristic formulas, any notes we want to write to ourselves to kind of say, okay, this is the goal at this point in the proof. This column is indicating how that particular formula at its respective line, how it got there. Is it a premise? Is it an assumption? Is it a result of prior formulas and some specific rule of reason that we made use of? So let's look at an example. So let's look at an example of how to set up a proof. We'll take the previous example where we said it's capable of being proved that from P wedge R, Y right arrow R, that Z follows. So essentially what we're saying here is we can start with the formulas P and R, Y right arrow R, and use the deductive apparatus to reason to Z, because we're saying it's entailed by those formulas, so there should be a proof of this using the deductive apparatus. So the way that we'll show this is we'll start with the formulas P and R and put it on one line, and then Y right arrow R and put it on a separate line. Now if we had more premises, we would put it on line 3 and 4 and 5. And if we had fewer, let's say we just had P and R, we would only put P and R on line 1. In addition to this, we'll want to number these formulas. In fact, we'll want to number every formula that we introduce into the proof. Here we just have two formulas that serve as our reason or premises, or the formulas that are provided, or the ones that we're starting with. So we'll label P and R 1 and Y right arrow R 2. So in addition to writing the formulas down and numbering each formula in the proof, we'll also want to indicate how that formula got to the place it did, what justifies it. And we'll do this in the third column. Since both of these formulas are provided for us, since both of them are premises, we'll simply use P to indicate that it's a premise or it's a provided formula. In addition, in the third column, we can make use of any heuristic devices, notes, or, as I'll do sometimes, indicate the goal proposition. Here I write comma Z, and I write Z to indicate the goal of the proof is Z. This is where I want to use the deductive apparatus and the formulas in the proof to reason to. And once I'm able to write Z justifiably in the middle column, then I'll know to stop and my proof will be completed. So once again, setting up the proof is relatively straightforward. You simply stack or write in a column all of the formulas that you're provided, number them, and then indicate in the third column that that formula is provided. And in addition, you want to write any notes to yourself or just the goal formula in that third column as well. So in previous video, I talked about what syntactic entailment is. I also talked about what a proof is. And in previous videos, I also talked about how to set up the proof. In addition, in previous videos, I talked a little bit about what the deductive apparatus is. In short, this is just a list or a set of rules of inference, rules of reasoning, or what we'll call derivation rules. But we don't have any kind of rules formulated yet for this deductive apparatus. The deductive apparatus is defined as a set of rules of reasoning that allow you to kind of take steps into proof, but we don't have any of these rules formulated. So this video will give the first step in talking generally about some of these rules. So remember, just to kind of refresh your mind just once again, the deductive apparatus is just a set of rules that allow us to write new well-formed formulas in a proof. If we're already given a set of premises or reasons to work with, and we know what we want to prove as the conclusion, the deductive apparatus just lets us take steps to move towards that conclusion. And to put it really shortly, deductive apparatus are just the rules of reasoning that take us from the premises to the conclusion. The particular type of deductive apparatus we'll develop here, it really kind of is closely related to how people reason in everyday life. Namely, we'll make use of rules that people employ that correspond to deductively valid forms of reasoning. And we could come up with another deductive apparatus that has a fewer rules or rules that don't really correspond to how people reason, but the one we'll make use of here is called natural deduction. It corresponds to how people naturally reason in a logically correct way. We'll abbreviate this deductive apparatus as a whole. We're using PD. And we'll call the particular rules in the deductive apparatus as PD, the derivation rules. Just to make one kind of clarification or categorization of the deductive apparatus that we'll develop as a whole, the particular type of natural deductive system that we'll articulate. This natural deductive system initially will consist of two main types of rules. The first are introduction rules. These rules introduce into the proof a certain type of proposition or a certain type of well-formed formula. So there'll be introduction rules corresponding to conjunctions. That is, these rules will allow us to derive conjunctions into the proof, as well as ones for disjunctions, biconditionals, and conditionals. There are also elimination rules. Now, elimination rules don't allow us to kind of, let's say, remove the disjunctions or conjunctions or conditionals. Instead, elimination rules reason from these kind of different well-formed formulas. So there'll be an elimination rule for conditionals, an elimination rule for conjunctions, and so this is kind of helpful to recognize, because if you get stuck at a point in the proof and you say, okay, what I really would like in the proof is a conjunction, well, then you should really look towards the conjunction introduction rules. Or if you find yourself in a proof where you are looking at a conditional, you say, hey, I'm looking at a conditional, I'm reasoning from a conditional to, let's say, some other formulas. So I'm going to look at the elimination rule, because the elimination rule reasons from a conditional to other formulas. This is conjunction introduction. And we'll abbreviate conjunction introduction simply by using wedge, the sign for wedge, and an I. So conjunction introduction is a derivation rule that says, if you have two formulas, two lines of a proof, two formulas within the proof that you're working with, let's call one P and the other Q, but P and Q can be formulas of any complexity, as long as they're well formed. Well, if we have two formulas, we can derive, we can reason to, we can infer the conjunction of these two formulas. That is, we can reason from P and Q to the complex, well-formed formula P wedge Q, or P and Q. In addition, we'll say, well, you can also reason from P and Q to Q and P. Now, a way to express this more compactly is as follows. We'll say from P and Q, these syntactically entail P and Q, and we'll justify this step in a proof using this wedge I. And from P and Q, you can reason to P wedge Q, or P and Q for short. The idea here is that we can reason from two separate well-formed formulas to the conjunction, to a single well-formed formula that is a conjunction. This corresponds to everyday reasoning. So imagine, take a proposition, John is a man. Let's say we accept this as true, and we also accept that John is a banker. Well, conjunction introduction would correspond to the reasoning that people make use of, where you combine these two into one complex sentence, one complex conjunction, which is John is a man and a banker. Now, this seems pretty trivial, but we would say, okay, this looks like John is a man, and then the separate sentence, John is a baker. This would entail John is a man and a baker as well. In the sort of setup that we make use of for solving proofs, we write down our premises. Premise 1 is just the proposition or well-formed formula P. Premise 2 is Q, and it's also justified as a premise. And then when we derive a new formula into the proof at line 3, we're deriving the conjunction of line 1, which is a well-formed formula, and line 2, which is a well-formed formula. And we're deriving P wedge Q. Now, to indicate that this is how we got here, because we want to indicate if someone looks at our proof and say, hey, how did you come up with line 3? We'll indicate 1, the justification, which is we made use of a specific rule within the deductive apparatus, which is conjunction introduction. And so we'll indicate, rather than write out conjunction introduction, we'll write wedge I, and people will say, oh, that wedge stands for conjunction, that I stands for introduction. So I know what rule you're referring to. But then we want to make clear which formulas we made use of to derive this conjunction. And the formulas that we made use of were line 1 and line 2. So we reason from P at line 1 and Q at line 2 to the complex conjunction at line 3, P wedge Q. Now let's look at a more complicated example.
So conjunction introduction simply states that from two different formulas or propositions or sentences, we can derive the conjunction of these propositions. So let's look at the really kind of ugly looking proof or entailment, P right arrow Q, R V M Z. And that entails this complex conjunction where the left conjunct is P right arrow Q and the right conjunct is RVM. So we'd start by setting up the proof. We'd say, okay, we're going to write the premises that we're reasoning from, the formulas that we're reasoning from. We're just going to plop those down and indicate where they came from. They are premises. These are formulas that are provided for us. They're given to us. We're just accepting these as true. And so we're going to indicate it as such with a P. Now, what we want to reason to is this complex conjunction to the right of the single turnstile. That is, we want to reason to if P then Q and R or M. Now, if you look at this, you look at line 1 and you look at line 2. Those are two separate formulas. Now, conjunction introduction says you can reason to a conjunction, you can introduce into the proof a conjunction, provided you have two separate formulas to combine. And so what we can do is take line 1 and line 2 and derive the conjunction of those two. We could say formula 1 is the case and formula 2 is the case. And so that's what we do here. We write if P then Q and R or M. And so we're taking line 1 and line 2 and reasoning to the conjunction. Now again, we're indicating one, where we got what rule we made use of, which is conjunction introduction, and then also what lines we made use of. We didn't make use of line 3, that is Z. Z is not a formula that we took and kind of combined it into the conjunction. Instead, we took line 1 and line 2 and combined them to derive the complex conjunction if P then Q and R or M.
In this video, I want to talk about the use of conjunction elimination. Conjunction elimination says that from a conjunction P wedge Q, where P is any formula in the language of propositional logic, and Q is also any formula in the language of propositional logic, we can derive either one of the conjuncts. So from P and Q, we can derive P, and also from P and Q, we can derive Q. To represent this a little bit more compactly, we can say P wedge Q entails P, as well as P wedge Q entails Q. Conjunction elimination essentially states that from a conjunction, we can derive either one of the conjuncts, whichever conjunct that we want, on a new line of the proof. This rule corresponds to how we reason in everyday life. So let's say we have the statement that Sally is a doctor and a woman. So here we have a sort of and statement that says Sally is a doctor, and the other part says that Sally is a woman. So we can kind of express this with a little picture here. Here is Sally. We are going to say that she is a woman. So I'm just going to kind of put a bunch of hair on her right here. And she is a doctor. So let's write that with MD. Now, conjunction elimination states that if this sentence is true, Sally is a doctor and a woman, then we can reason on a new line. That is, we can derive a different sentence which consists of one of the parts of the conjunction. So from Sally is a doctor and a woman, we can reason to that Sally is a doctor. So we could say that from this sentence right here, Sally is a doctor and a woman, we can state that it follows, so it follows that she is a doctor. In addition, we can say that from this sentence, Sally is a doctor and a woman, we can also say that it follows that. So we can say that from this complex sentence right here, not only does it follow that she's a doctor, but we can also say that it follows that she is a woman. So the idea is that from the complex sentence, we can reason to either one of the conjuncts. The point generalizes in that for any kind of sentence that we have in English, let's say I say that I am a millionaire and let's say I'm also a nice guy, and let's say that, I don't know, I love trees, so we have this kind of tree right here. From this complex sentence that is a conjunction, where it's a number of smaller sentences linked together with the use of and, we can reason to any of the conjuncts. So we'd say that from this complex sentence, it would follow from this whole thing right here. So this whole complex sentence, we can reason to a simpler sentence. So from this whole complex thing, we can say that it follows that I am a millionaire. In addition, it also follows that I could reason to that I am a nice guy. And it also would follow that from this whole complex sentence here, it would follow that I like trees or like nature. So this is a sort of simpler sentence that conjunction elimination allows us to reason to. So let's look at a particular example of conjunction elimination in a proof. So let's say we have a entailment, which is P and Z and Q entail Z. And so we want to provide the derivation or proof of this. So we start by setting up the proof. We simply write down the formula that is to the left of the turnstile. That is, we write down this P and Z and Q, and we kind of plop it down right there and indicate it that it's a premise. Now the goal of this whole proof, the goal will be to, at some point in the proof, get Z. Now, conjunction elimination says that from a conjunction, we can derive either one of the conjuncts. So you'll see that at line 1, what we have is a conjunction, P and Z and Q. So conjunction elimination says that we can reason to either Q or we can reason to P and Z. So since the goal of this proof is to derive Z, we are going to use conjunction elimination. We'll abbreviate that we're using this rule by the sign for conjunction in E, and simply write P and Z at line 2. Now remember that the goal of this proof is to derive Z. And so since we have P and Z at line 2, and conjunction elimination says that we can derive either one of the conjuncts from the conjunction, we'll simply write Z at line 3, and we're using conjunction elimination. But this time we're using this second formula right here. We're using this conjunction where there's a P on the left-hand side and Z on the right-hand side. And so we can use conjunction elimination to derive Z. In this video, I want to talk about the use of a rule known as conditional elimination. Now, conditional elimination is a rule that goes by different names depending upon the system that you're working in. Sometimes it's referred to as modus ponens, and so it's referred to, expressed as simply MP for modus ponens. In other systems, it's referred to as affirming the antecedent. But here, I'll talk about it as conditional elimination. But in all of these systems, even though it has different names, it's the same rule. The rule is that if you have a conditional if P then Q and the antecedent of that conditional P, then you can derive Q. That is, if you have a conditional that consists of, let's say, a formula P and a formula Q, where P and Q are just variables or placeholders for any formula in the language of propositional logic, and you have the formula P as sort of separate formula standing on its own, then you can derive the consequent of the conditional, which is Q. So we can express this as saying P right arrow Q, P, therefore Q. It's important to note that what conditional elimination does not say is it does not say that if we have a conditional if P then Q, we can derive Q straight away. This is not what's being asserted. It's saying that you need two expressions to derive the consequent of the conditional. It states that you have the conditional if P then Q, and you have the
antecedent of the conditional on its own line. And from this, you can derive the consequent of the conditional on a new line. So it's important to note that conditional elimination, in order to make use of this particular rule, you need two formulas. One, the conditional, and the second formula must be the formula that comes to the left of the arrow here. So you notice how these two formulas match, and if those two formulas match, then you can reason to the formula that is to the right of the arrow. Conditional elimination corresponds to how we might reason in everyday life using if-then statements. So let's take an expression like, if I smile at you, and let's say that then, so if I smile at you, then you'll smile at me. Okay. So conditional elimination states that we can reason to that you will smile at me, provided we, one, have the conditional, if I smile at you, then you'll smile at me, and we have the antecedent of that conditional on its own line or as a separate sentence. So let's say I do smile at you. I smile at you. There we go. I smile at you. Conditional elimination states that if this conditional is true, and this sentence right here is true, where you'll note that this second sentence is the antecedent of the conditional. So I will smile at you is right here. It's part of the conditional. And then here we have it as a separate line. We can affirm that this is the case. We kind of determine that I did smile at you. Then from all this, we can reason that if I smile at you, then you'll smile at me. Well, I did smile at you. So if both of these are true, then it follows by conditional elimination that you will smile at me. Now, this above reasoning here corresponds to how we would reason using the formal system. If we let if I smile at you represent that with a P, and we say, then you will smile at me. If we say we're going to represent you smiling at me with a Q, and this sort of conditional right here, this if-then statement using the arrow. So if P, then Q. And since we said that me smiling at you, we represented with a P, and we said that you smiling at me, we represented at Q, what we have here is essentially P, right arrow Q, or P, if P, then Q, P, and we are reasoning to Q using the rule conditional elimination. Let's look at a particular example. Suppose we have the entailment if Z then R, Z and P entails R. One way to look at this particular entailment is to say, look here, we have a conditional right here, and then in this conjunction, we have the antecedent of this conditional. And so if we could isolate this Z, if we could get this Z on its own separate line, then we could reason if Z then R, Z entails R using conditional elimination. And that's essentially what we would do in order to provide the derivation. That is, we would first isolate this Z on its own line using a different rule that we've introduced in an earlier video, which is conjunction elimination. We say Z and P entail Z, and now that we have a conditional Z, if Z then R, and we have the antecedent of that conditional, we have Z on its own separate line right here, we can derive R. So we have if Z then R at line 1 and Z at line 3, and so we can make use of lines 1 and 3 as well as the conditional elimination rule to derive the formula that we want to be the last line of our derivation, which is R. One final point worth mentioning is that even though conditional elimination is formulated as if you have a conditional, if P then Q, and P then you can entail Q, these P's and Q's are simply placeholders or variables for any propositional logic well-formed formula. So these P's and Q's can be any formula that we want. So to give an example of a more complex use of conditional elimination, we would be making use of conditional elimination if we had, let's say, if P then Q, or not R entails, let's say, not S. And if we had the entire antecedent of this conditional, that is, if we had this whole antecedent on its own separate line, then we could derive not S. If we had if P and Q or not R on its own line, then we would be using conditional elimination with line 1 here, 2 here, since we have the entire antecedent of the conditional, to derive not S. In this video, I want to take a look at a derivation rule known as conditional introduction. Conditional introduction says that from a subproof that begins with the assumption P and ends with Q, we can derive the conditional P right arrow Q. That is, if we assume P and under this assumption we derive Q, we can derive a conditional from that reasoning that we've done under the assumption and to the derivation of Q to the conditional P right arrow Q. So take a look here. What we have is a assumption right here. We assumed P. And then through using the deductive apparatus, that is, we just kind of used our various derivation rules, we, under this assumption, reason to Q. Now, once you've made this assumption and then derived a particular formula of your choosing or whatever you kind of want, then you can derive a conditional from this entire subproof where the antecedent of the conditional is the formula that you assumed and the consequent of the conditional is the formula that you derived in the subproof. Another way of thinking about conditional introduction is that you make an assumption. Let's say you assume S and then you reason to, let's say, L. You said under this assumption, if S is the case, then L is the case. And so conditional introduction simply summarizes the reasoning that went on in this subproof right here. That is, under this assumption S, you derived L. And so you can summarize this entire subproof right here with a single formula, which is if S, then L. Let's take a look at a particular example of conditional introduction. Here we have a proof where we want to reason from R to the conditional if Z, then R. Now, at first glance, it might be kind of curious. How are we going to derive Z, or how are we going to get Z into this proof if we don't have it in our premises, if we aren't beginning with it? Well, one of the ways to do that is to make an assumption. So you'll notice that we set up the proof here at line 1. We simply write R. And then the goal of this proof is to get the conditional if Z, then R. So we want to form this conditional. We want to introduce into the proof a conditional. And conditional introductions says that if you assume Z and derive R, then you can derive the conditional if Z, then R, which is the formula that we want. So line 2, what we do is go ahead and assume Z. And now the goal of this subproof is somehow to get R, just like we kind of indicated over here. And we can do that. We can get R into this subproof by first using an earlier rule that we talked about, conjunction introduction, with lines 1 and 2. We took line 1, line 2, and formed a conjunction from them. Then, since we have a conjunction at line 3, we can derive R from that conjunction using conjunction elimination. So now what we've done is we've assumed Z and we've derived R. That is, we assume Z and show that if under the assumption Z is the case, then R is the case. And conditional introduction says that if you assume a particular formula and then derive a formula, then you can summarize that or derive into the proof the conditional if Z, then R.
The basic idea behind conditional introduction is that if you assume a formula and show that a particular formula follows from that formula, then you can derive a conditional from that. So if you assume B, derive another formula, Q or R or whatever, then you can derive a conditional from that. So let's consider an example in plain English. Let's assume that, just assume that a nuclear bomb is dropped on my house. Let's make this assumption. We're not saying that it is the case. We're just saying, let's assume, so assume or suppose that a bomb is dropped on my house. Bomb is dropped. Okay, from this assumption, let's say from, using the derivation rules as well as some other maybe formulas that are found in the proof, that if this bomb is dropped on under the assumption that the bomb is dropped, then my house will be destroyed. So I say, okay, I assume this particular bomb is dropped right here. And now through using the various rules or in conjunction with the formulas that are in the proof, I can show from this that the house, my house, will be or is destroyed. Now, from this assumption right here, and from this kind of conclusion that we reached in this subproof, that is from the conclusion we derived under this assumption, we can use conditional introduction to derive the conditional. If the bomb is dropped on my house, bomb is dropped, then, so we're deriving this conditional from this assumption, right? From this like little subproof up here, then house destroyed. So you see how conditional introduction corresponds to, let's say, an everyday form of reasoning. People make assumptions or suppositions all the time. We say, okay, we don't know whether or not this is the case or not, but let's assume it and see what follows from that. And given that you can show a particular formula follows from that assumption, you can kind of summarize that reasoning there with a conditional. Say, well, if a bomb is dropped on the house, then it's going to follow that the house is destroyed. Let's look at two more examples of using conditional introduction. In the first example, let's consider we had the premise P and Q, and we want to derive the formula Z and X, then Q. So you'll notice that we don't have Z or X in the premises, but the claim is that from P and Q, we can show using the deductive apparatus that Z and X, then Q follows. So we set up the proof, P and Q. Then, one of the things to note is that the goal of this proof is a conditional. That is, we want to introduce into the proof a conditional. So we can start by saying, you know what? I just need to assume the antecedent of the conditional and then try to get the consequent. So I'm going to assume Z and X. And you can assume whatever formula you want. You can assume it can be a contradiction. It can be any formula of any complexity. So I'm going to assume Z and X. And the goal of this subproof is to show that Q follows. And I can get Q into the subproof. That is, I can reason to Q by saying, well, if P and Q are the case, and under the given that P and Q are the case, and under the assumption Z and X are the case, I can reason to Q using line 1, conjunction elimination. I'm reasoning from this conjunction at line 1 to Q at line 3. Now what I've shown here is that if Z and X, under this assumption Z and X, Q follows. And so I can summarize that subproof. That is, I can legitimately drive into the proof, if Z and X, then Q. I can reason to this conditional using the subproof, so lines 2 through 3, and conditional introduction. Let's look at another example. In this example, we'll look at a particular proof that doesn't involve any premises. We'll say that we can derive P and P, then P. That if P and P are the case, then P is the case. And we can do this from 0 premises. So to start, what we'll have to do is make an assumption. And the assumption is going to be based upon this conditional right here. We want to derive a conditional. And so we'll start by assuming the antecedent of this conditional and then trying to derive the consequent of this conditional. Because we're going to do this form a conditional at the end. We want to make an assumption P, derive Q, and then reason to P and Q. But here, since our formulas are a little bit different, we'll make different assumptions. But essentially what we're going to do is the same thing. We're going to assume the antecedent of the conditional and then try to derive the consequent. So we'll start by assuming the antecedent of the conditional, P and P. This is making an assumption, and the goal of this formula is to derive P. Next, we can reason to P simply by using conjunction elimination from line 1. We have a conjunction P and P, so we can reason to P. And then at line 3, we can reason to P and P, then P, using 1 through 2 conditional elimination. That is, we assumed P and P, we derived P from this formula, from the assumption, and then from this we can say, well, under the assumption P and P is the case, it follows that P is the case. So we can say, if P and P is the case, then P is the case. So this shows how we can make use of conditional introduction without any premises at all. The thing to keep in mind, though, is when we want to make use of conditional introduction, we always are looking at the type of formula that we're trying to derive. When we're trying to derive a conditional, we might want to make use of this rule.
Okay, in this video, I want to talk through two rules. One is negation introduction, and the other is negation elimination. I'll talk through the form of the rules, then I'll talk through some more intuitive explanation of the rules, and then I'll deal with some kind of frequently asked questions concerning them, and then do some examples. So negation introduction, let's just kind of read the rule here. It says that from a derivation of a proposition Q and its literal negation not Q. So what we're doing here is reasoning into Q and the literal negation of Q, which is not Q. So Q and not Q can be any formulas. They just need to be literal negations of each other. So for example, you could have, let's say you reason to P and not P instead, or Z and not Z instead. So you, from a derivation of Q and not Q within a subproof, so we're reasoning under an assumption that involves an assumption P, we can derive not P from the subproof. So let's take a look at this. So here we have our rule where we first make an assumption and we can assume whatever we want, but here P is assumed. Then we reason at some point in the subproof to Q and not Q. We reason to a formula and its literal negation. And then from this entire subproof here, we can reason to the negation of the original assumption. So we assumed P and then we're able to derive not P. You'll notice that this is an introduction rule, and the type of formula that we're introducing or bringing into the proof is a negated formula. So that's why it says negated introduction. Another thing you'll note is that when we cite the lines that we make use of to derive this formula, we want to cite the entire subproof because we're reasoning from this entire subproof that begins with P and ends with this Q and not Q. And then from the subproof, we're deriving the negation of our original assumption. Let's take a look at negation elimination, and then we'll talk through these two rules in more general terms. So here's negation elimination. Negation elimination basically says the same thing, but there's just one small difference. Again, we derive a formula Q and not Q within a subproof. And in this case, it starts with a negated formula. So since it's an elimination rule, this means that we're reasoning from a formula of a particular type. And in this case, we're reasoning from a negated formula. So it says from a derivation of Q and its literal negation, not Q, within a subproof that involves the assumption not P, a negated formula, we can derive P from this particular subproof. So let's look at the argument structure or schematic right here. So here we begin with the assumption not P, which is a negated formula. We reason to a formula and its literal negation. So in this case, we have Q and not Q. But remember, this can be any formula and its literal negation. So it could be, let's say, Z and not Z. And then from this entire subproof here, we're reasoning to P. That is, we're reasoning to a formula that involves the removal of one of the negations, that is the main negation in the assumption. So we assume not P, reason to Q and not Q, and then from the entire subproof, we can reason to P. Again, since we're relying upon this entire subproof, we'll use all of the lines of the subproof. So if this were line 1 and this were line 7, we would cite negation, elimination, lines 1 through 7. Okay, now let's talk through these two rules in more general terms. But before we do that, let's look at an example. So here's an example that will make use of negation elimination. So the proof here starts with P and not P, and then they're asked you to derive Z right arrow R. So we start the proof by assuming not Z right arrow R. And you'll notice that our assumption is the literal negation of the formula that we want to derive. And since we're planning on using negation elimination, you'll notice that the formula that we're assuming is negation. So we make this assumption here at line 2. We derive 3 from line 1 using conjunction elimination. And line 4 comes from line 1 using conjunction elimination again. So what have we done in this subproof at least? What we've done is made an assumption and then derived a formula and its literal negation. So now that we've made this assumption, derived a formula and its literal negation, we can reason to a formula which is the assumption except for it no longer has this negation. And so we can reason to Z right arrow R using negation elimination. And we'll, in terms of the lines that we made use of, it was lines 2 through 4, which is the entire subproof right here. Let's talk about these rules in more general terms. So negation, elimination, and introduction are sometimes referred to as species of reductio ad absurdum, or arguments that have this kind of reduction to absurdity. The idea here is when you make an assumption and then you show that a contradiction follows, that is P and not P follows, you've taken that assumption and sort of reduced it to absurdity. It's also sometimes referred to as a kind of proof by contradiction. That is, you prove something by showing the opposite yields a contradiction, that is a formula P and not P. Both are sometimes referred to as indirect proofs, in that they try to prove something by showing the opposite, by assuming the opposite proposition, and then showing that opposite proposition, which is the negation of the formula you want to derive, leads to a contradiction, that is Q and not Q. So one question you might have immediately before I'll deal with this question again, is how you would use these formulas in a kind of everyday life argument. So let's take a look at an example. So let's look at a concrete example involving the use of negation, elimination, and introduction. So let's say we start with some premises. These are propositions that we'll accept to be the case. Maybe we do believe in these propositions. Maybe we're just kind of committed to them in an argumentative context, but nevertheless, we're going to accept them as true. So the first premise, premise 1 here, is that if God exists, we're not saying God does exist, but if God exists, then God is all-loving, all-knowing, and all-powerful. The second premise is that if God is all-loving, all-knowing, and all-powerful, then there should be no evil in the world. So no evil in the world. And our third premise here is that there is evil in the world. So these are propositions we're going to accept, and then we're going to reason from them. Now, let's suppose you don't believe that God exists. You're committed to this view that there is no God, and you want to prove this. So God does not exist. That's what you want to establish. And you want to show that this formula follows from these premises. You want to show that you can reason using these premises up here to the proposition that God does not exist. Here is a case where we might use the negation, elimination, and introduction rules. In particular, we'll use negation, elimination. So let's see how this works. We'll start by assuming the opposite of what we want to prove. So since we want to prove that God does not exist, we are going to assume its negation. So we want to assume that since we want to prove that God does not exist, which we can, let's just call not G, we're going to assume the opposite. That is, we're going to assume that God does exist, which we could call G. So it's important to note that we are making an assumption that is based upon a conclusion that we want to establish, but rather than assuming the conclusion to be the case, we're assuming the opposite, that is the negation of the conclusion. This is the formula that we are assuming. We are assuming that God does in fact exist. The next step is to show that if we make this assumption, a contradiction will follow. That is, under the assumption that God exists, this leads us to some type of inconsistency, some commitment to a formula and its literal negation, or a sentence and its literal negation. And the idea here is, yes, if we assume God exists, then using these premises, we can reason to the sentence, there should be no evil in the world, or there is no evil in the world, and there is evil in the world, which looks like we're reasoning to not E and E. So the idea is, if you make this assumption that God does exist, it entails both a formula and that formula's literal negation. Given that we can reason to not E and E, that is, under the assumption God does exist, it means that there is no evil in the world and there is evil in the world. We can make use of the negation, elimination, and introduction rules. Under the assumption that God exists, if it entails this contradiction here, not E and E, we can reason to the conclusion that God does not exist, which is the negation of our assumption. So you'll see what happened here. We wanted to prove that God does not exist. And so we started by assuming the opposite of what we wanted, showing it to be contradictory. And given this contradiction, the opposite of G has to be the case. That is, not G, or God does not exist, have to be the case. Now, I want to kind of point out here, I'm not committed to this particular argument. I'm not trying to make a kind of atheistic point or a theological point. I'm just using it as a kind of way of illustrating this type of reasoning in everyday life. So now it's time for some frequently asked questions. People ask me a lot of questions about this particular pair of rules, and so I want to go through some of them here. So the first question is, what should I assume when I'm making use, if I want to make use of negation, elimination, and introduction? And my answer to this is, you're always going to assume the opposite, that is the negation of the formula you want to derive in the proof. So if you want to derive P, this is like, let's say, the conclusion of your argument, then you'll assume the opposite, which is the negation, which is not P. If you want to derive P and Q, then you'll assume not P and Q. And if you wanted to derive not Z, then you'll assume either Z, which is not Z and Z are literal negations of each other, or not Z, which is just another negation tacked onto not Z. Another question I get is, once people have a pretty good grasp of, okay, I understand I always want to assume the opposite or the negation of what I want, they'll say, well, when is it a good time to use these two rules in a proof? Let me give kind of two answers to this. The first is when you can identify that the premises in the argument are inconsistent. That is, you can use the elimination rules to derive a formula like P and not P. So the tactic here in a proof would be to, if you have a set of formulas that you're reasoning from, you simply use the other rules that you have to derive phi and not phi, or a formula and its literal negation. Then you'll go ahead and assume the opposite of the conclusion, and you can reiterate phi and not phi into the subproof, and then you use either negation elimination or negation introduction, whichever one is pertinent here. Another general answer is, well, if you're not really sure what to do,
That is, you've used all your elimination rules, you've tried different ways of proving it, but you haven't quite yet used this negation elimination introduction strategy, and you've simplified the proof as much as you can. Maybe it's time to look at the goal of your proof and say, well, what is my proof trying to establish? Let's assume the opposite and then work with what I have to see if assuming the negation of the conclusion gets me what I want. So the idea here, or the strategy here, would be to assume the opposite of the conclusion, then see if this assumption will allow you to derive a contradiction, that is phi and not phi. If it does, then you can use either a negation elimination or negation introduction to solve, or whichever one applies in this scenario. Another question I get sometimes is that sometimes people will always try to use these two rules. And so they'll say, well, when should I not use it? One would be when you don't really have a clear reason to do it, or you can make use of elimination rules to simplify your proof further. So just using it to use it obviously doesn't make a whole lot of sense. If there are other rules that you say, hey, this would allow using conjunction elimination or conditional elimination will get me my conclusion, then obviously maybe using negation, elimination, or introduction isn't the most efficient proof solving strategy. With that said, I do see some people who make use of this particular rule quite a bit. And so if you are comfortable using it and you take it as general strategy, then it's a powerful rule to use. Another case when you maybe should not use these particular rules is when your conclusion is a conditional. In these cases, it makes more sense to use maybe conditional introduction rather than negation, elimination, or introduction. You'll notice that conditional introduction will introduce into the proof a conditional, and so it seems like the more straightforward rule to use when you're trying to derive a conditional. Another question I commonly get is, when can I use these rules in daily life? Now, this type of question I think is outside the scope of my expertise, but I want to kind of give a general answer to it anyway, just because it comes up so often. So my first response to this is practically, that is when you should use it. It's really hard for me to say when you should or shouldn't use it, whether it makes sense to use it in the workplace or a social situation or in your personal life. Because what you're doing is showing a particular viewpoint or position or proposition to be absurd. You're showing that it entails a formula that is a sentence or a proposition and the opposite. And so I think one kind of reaction that I've seen when making use of this particular style of reasoning is people will, if you show someone else's position to yield a contradiction, they will take it as a personal assault. Because you're saying, okay, let's accept what you're saying is true, but look, it leads to a contradiction that is utterly irrational. So either you accept this irrationality or your view is wrong. And I think sometimes people will respond to this by saying that, or treating you as though you are attacking them as individuals rather than their position. So I think it's hard to say practically when you should use this. So I just wanted to kind of preface my answer to this with that. In terms of the argumentative situation, you're trying to figure out a position, or you're working in an argumentative context where people aren't going to take your arguments or objections as personal attacks. You might use this when you think an individual's position yields a contradiction or reduces to absurdity or yields a practical consequence that the proponent of the position would never accept. So the way you would do this is say, okay, person I'm arguing with, let's say I'm just going to grant your position is right. Then you draw out the contradiction in their view, and then you reason that their position has to be false. You see this a lot of times too in practical proposals, let's say about politics or what we should do in terms of public policy. There's a kind of assumption that if anyone puts forward a practical proposal or a political view, that it has to be palatable for people. People have to practically accept it. And you would use negation, elimination, and introduction by saying, okay, let's accept what you're saying is true, but look, it yields this horrible scenario that no one would accept. It's not practical. And
given that all reasonable positions have to be practical and this is not a practical proposal, then their position has to be wrong. So you can do this in the argumentative situation, and the style you would do it in is accepting what they say is true and then trying to show that it yields to some impractical consequence or some kind of contradiction. Another way you might use it is as a style of self-critique. Let me give you an example. Suppose I think that my character or anyone's character is determined by what you do on a regular basis, your sort of habits. And also, let's say I don't give to charity or I don't give to anyone, but I might say, well, you know, I think I'm charitable. So let's just for a moment assume that I have this property of being charitable. I'm not saying I am just going to assume it. Now, if I think that all character is determined by what I do on a regular basis and I don't give to charity at all or on a regular basis, then we might reason to that I am not a charitable person or charity is not a part of my character. And so I might use this particular method as ways of figuring out something about myself. I could kind of write down all of my beliefs and try to sort of suss out any inconsistencies that are found in them or sort of diagnose myself in terms of, the different properties that I have. All right, last question. The last question, and I would say this is the most common question that I get, is can I see some more examples? Can you use this negation, elimination, and introduction rule in an example, in a proof? I want to see it one more time. So yeah, I can provide another example, and here it is. So let me just come up with one on the spot. I'm just going to make one up right now. And so this is going to be, let's say P and Q and R, and let's say not P or not R, and then let's say it entails Z. So I want to prove that Z follows from these particular formulas. So I'll start the proof by simply writing out the formulas, setting up the proof. Here, I'm just taking the formulas here and writing at line 1. And then at line 2, I'm going to write not P or not Q. And so this is line 2. I'm going to indicate that both of these are premises or propositions. And then I'm going to write the conclusion over here. I'm doing this just so I can remember it, so I don't have to look back up at this line at line 1. So my first step here is I'm just going to simplify this proof a little bit. I'm going to write P at line 3 and then Q and R at line 4. And both of these rules, or both of these formulas, are derived using the negation elimination rule at from line 1. So now I'm looking at the two formulas I derived, and I'm also looking at these negation Q and negation P. And I'm saying, well, I think I could maybe derive a contradiction using line 2 and then maybe Q from line 4. So I'm going to reason to Q all by itself at line 5. And this is from 4 conjunction elimination. So at this point, again, I'm looking we have not P here and not Q here. And so maybe I can derive a contradiction. A rule you might not be familiar with is this disjunctive syllogism rule. I'm going to use it right here, which essentially says that one way of putting it is if you have a disjunction and the literal negation of one of the disjuncts, then you can reason to the other disjunct. So let me just write that rule over here. So the general form is you have phi or psi, and then you have the negation of one of these. So let's say negation of phi, then you can reason to psi. So there's different ways of formulating this rule, and one way is simply to say, provide these two formulas are negations of each other, you can reason to the other one. And so that's what I have here. You'll notice that at line 2 and 3, I have not P or not Q. So I have this not P or not Q. And then I also have P at line 3. And so now I can reason to the right side, which is not Q. So I'm reasoning to not Q at line 6 using lines 2 and 3 and this disjunctive syllogism rule. So at this point, you'll see that I have a formula Q and not Q, and I have this conclusion Z, which it doesn't matter how many elimination rules I'm going to use in lines 1 and 2, I still can't get this Z. So what I want to do is make an assumption. So I am going to assume the opposite of what I want, which is I'm not going to assume Z. This is a common mistake. You'll want to assume not Z. So I'm going to assume not Z right here. I'm going to make this assumption, and my goal of this assumption is to get a formula like P and not P, any formula in its literal negation. You'll notice that 5 and 6 are literal negations of each other. So at lines 8 and 9, I am going to simply reiterate those formulas into the proof. So I'm going to reiterate Q from line 5 using the reiteration rule, and not Q from line 6 using the reiteration rule. Now, what have I done? I've made an assumption, not Z, and then I showed that from this assumption, Q and not Q follows. So now I want to reason to, again, I don't want to reason to not Z or Z, but in this case, I'm going to reason to Z. So at line 10 here, I'm going to reason from this assumption and the subproof here. So lines 7 through 9 using negation elimination. Now, this was a roundabout way of solving this proof. You might have actually started this proof by simply assuming line 7, that is, assuming not Z, and then deriving the contradiction Q and not Q in the subproof, that is, reasoning from lines 1 and 2, using these rules in the subproof. That would be another way of going about it. I sort of did it like this just to illustrate that one particular tactic you might use, which is to try to simplify the proof, identify a contradiction in the premises, and then assume the opposite of what you want, which is not Z. So I hope this video was helpful. I hope it provided some context as to how you might use negation elimination in introduction, and I hope it also answered some questions that you may have had about the elimination and introduction rule.
In this video, we'll look at 2 rules from propositional logic proofs. We'll look at the disjunction introduction rule, and we'll also look at the disjunction elimination rule. For both of these rules, I'll state the general idea behind the rule. We'll go through some real-life examples. We'll talk through the form or structure of the rule, and then we'll talk about how to use this rule to solve propositional logic proofs. So the basic idea behind disjunction introduction is the following. It's a rule in propositional logic that allows you to introduce or create or write into a proof a disjunction or an or statement. And so what you usually have is you have a formula and that or a proposition. And let's say we have that formula phi, like as you see in premise 1 there, and then it allows you to reason to an or statement like which would be something like phi or psi. So you have these like variables here, phi or psi, and these variables here are standing for any formula that you want. So it could just be a simple proposition P, and then you reason to P or Q, or it could be something more complicated like P and Q, and then you reason to P and Q or something else. People tend actually not to use this kind of reasoning in daily life. The reasoning itself is perfectly fine, but it's sort of strange to hear people reason from a proposition to directly to an or statement. It does happen in some cases, but it's not like the most standard or frequent way people reason. But you might say, okay, well, let's look at some concrete examples. You might say, I'm going to take a philosophy class next semester. And then you could say, well, assuming this is the case, assuming you are going to take a philosophy course next semester, you could reason to, well, I don't know. I'll either take a philosophy course or maybe I'll take a biology course. This would be disjunction introduction. You're reasoning from a sentence or a proposition, a sentence that can be true or false, to a or statement. Same thing with this one. You say, well, I'm really this kind of romantic type. And so John's going to look up at the stars tonight. And then you could reason to an or statement from this. You'd say, well, John's either going to look up at the stars tonight or he's going to binge watch Netflix all night, one or the other. And so this is, again, disjunction introduction. You could think about this if you're like more visually inclined. Let's say here's me. You might say, I'm going to listen to music all night. Therefore, I'm going to either listen to music all night or, I don't know, stare at the sun. That would be an example. Here we're reasoning from a proposition to, again, to an or statement. And this other thing that we're adding, this other sentence that's being added as the or which is the disjunct, it can be anything you want. The thought is that if this proposition is true, that is, I'm going to listen to music all night, then it would follow that I'm either going to listen to music all night or stare up at the sun. But again, the important thing to emphasize is this or that gets added can be anything. So again, we could reason from the fact that I'm going to listen to music all night to I'm going to listen to music all night or eat this huge king size world's largest Hershey bar or knit myself a hat and scarf. Or it could be a complex sentence that I'm adding. I'm going to both eat this Hershey bar and knit this hat and scarf combo. So to kind of go back to it, the disjunction introduction rule is going to introduce into the proof a disjunction, this or statement. And so now we want to kind of phrase this a little bit more abstractly. So here's the statement of the disjunction introduction rule. Again, you have a formula, and then you're going to reason to a formula of a particular type where the V is the main operator. So if you look at the structure of the rule here, we have a formula phi, and then we can reason to either phi or psi, or, it's just flipped around here, psi or phi. So when you use disjunction introduction, you're going to start from a formula phi, and then you're going to reason to a formula of a particular type, which is this disjunction here. And this formula psi that you add on, it can be any formula that you want. It doesn't, there's just no limit as to what you could add there. Some people find it kind of strange that this is a rule, that this is even acceptable. But if you take a look at the truth table here for reasoning from P to P or Q, you could see that in no cases do we reason from a true premise to a false conclusion. So if you look at the first two rows here, where P is true, it's impossible to go from a true proposition P to a false proposition P or Q. When we look at P, we see, okay, in rows 1 and 2, it's true. And in rows 1 and 2, P or Q is also going to be true as well. So you could see from the truth table that this is a valid argument structure. I think one thing, again, that people find strange is that you can reason from a formula like phi to a formula phi or psi, and that psi can be any formula. And so this seems a little bit strange at times. So here's an example. Let's say you had a proposition P at premise 1, you could reason to something weird like P or not Q or S. Why you would ever do this in actual practice is kind of a good question, but the logical rule as well as the form permits it. Provided we have that premise is true, that P is the case, we won't be able to go from truth to falsity. So let's look at some examples, like, because you're probably going to be asked in an exam or some sort, like you'll be asked to just prove a rule, do a proof that makes use of disjunction introduction. And so we want to make sure we can use it correctly, even if, because it's one thing to know, like, okay, this is an acceptable way to reason. I know that this rule exists, and it's another to be able to like actually do a proof that involves it. So we'll look at a proof that involves reasoning from R to R or Q. So it's really simple to use this rule. Here we have R at line 1 which is a premise, and then we reason to R or Q. And what you want to do when you use this rule is to make sure you do two things. First is you want to cite the rule, obviously. You want to say, hey, I use this disjunction introduction rule right there. And then you also want to make sure you cite the line when you use, or the formula that you reason from. So when you use disjunction introduction, you're just reasoning from a single formula. And that's why this one only refers to just one. So you don't have, let's say, 1 and 2. You're not citing 2 lines. You wouldn't be citing 3. You're just going to cite the formula that you reason from. So you have this formula R, and then you can reason to R or Q. And if you did this, then the proof would be solved. You would have completed it successfully.
Okay, let's take a look at a slightly more complicated one, because it's not likely that you'll the proof that you have to solve for, let's say, an exam or a quiz or something like that is going to be this simple. So here's a slightly more complicated one. So we have P, and then we're supposed to reason to P or Q or not R. Now, some people will just try to reason directly from the premise straight away to the conclusion, but that would not be correct, because when you reason using disjunction introduction, you are going to reason from, let's say, P, and then you're going to reason to P or something, and that or can be whatever you want. But in this case, one thing to notice is that we have P or Q or R. So we won't be able to reason directly in one step to the conclusion using disjunction introduction there. So what we have to do instead is just do the proof in a more step-by-step fashion. In this case, what we did was we reasoned from premise 1 right here to P or Q, and notice that we're adding on this one disjunction. And then once we have this formula at line 2, this is just another formula. It's just like a phi. We're going to reason to phi or psi, where psi can be whatever we want. So we have P or Q. It's a formula, and then we're going to put P or Q or, and then this formula could be whatever we want, but in this case, we're going to make it not R, because obviously we want the conclusion. And then the other thing to kind of pay attention to is, like, sometimes people will do the proof correctly, they'll write down the formulas correctly, but they won't put the justification right. So we want to make sure we do that right. So in both cases, we use the disjunction introduction rule. So we use this VI to indicate that. And then we cite the line that we used. So on line 2, we reason from line 1. So we want to write line 1. And then line 3, we reason from line 2. So we'll cite line 2. Sometimes, like when I teach this, what I'll sometimes see is that, like, at line 3 here, someone will write something like 2 and 1. They'll write both of the lines, which is a little bit, it kind of makes sense, but it's just not right. You're like, hey, this disjunction at line 3, this formula that I derived depends upon all those prior lines. But in this case, you would only write line 2 there because you're reasoning directly from line 2 to this conclusion. Okay. So one question you might have is like, well, when should I use this rule? And that's really, I think, one of the hardest parts about solving proofs, because you get all these rules and then you can understand each one in isolation. But once you have all of them, you start to look at them and you say, well, which one do I use? There's so many. The answer to that is pretty straightforward. You would use disjunction introduction when you actually want a disjunction. The rule is called disjunction introduction. And the reason it's called an introduction rule is because it allows you to, like, write or create or put into the proof or introduce a disjunction. And so you would only use this rule if you actually had a reason for making a disjunction in the first place. So let's take a look at this particular proof. Here we have P or Q, then R, and we have P, then the conclusion here is R. First step is to set up the proof. And so we're going to write each one of those premises down. We'll write that first premise, P or Q, then R, and then we'll write P. And now we're going to try to get the conclusion, obviously. So, when you look at these two formulas, you might say, well, what do I do here? I'm not really quite sure how to solve this particular proof. And one thing you might say to yourself is, well, look at this formula. It is a conditional. So it's a formula that has this structure: if phi, then psi. And there is the rule, which is the conditional elimination, which says that if you have the left-hand side of that conditional, you can reason to the right-hand side. And that would be great here, because the right-hand side of this conditional, R, is the conclusion, and that's the formula that we want to derive. So when we look at this conditional elimination rule, we really want this left-hand side of the conditional. But let's take a look. the left-hand side of this conditional is what? P or Q. And we don't have P or Q. We only have P at line 2. So even though we want to use conditional elimination because that would give us the conclusion, it would give us this R that we really want to derive, we can't do that. And what we would need to do is have this disjunction here. And so you might say, well, now I know something. Now I actually want a disjunction. And so I have a reason to use this condition or disjunction introduction rule. So this would be a kind of indication like, when should I use disjunction introduction? I should use it when I want a disjunction. And here's a proof where I want a disjunction. So let's take a look at what we would do next. So what we do next is to reason from line 2 to line 3. And at line 3, we have this P, and then we use disjunction introduction on it to get P or Q. And now that we have P or Q, we have the left-hand side of this conditional, which allows us to reason to the right-hand side. So again, we have this conditional. There's two sides, left-hand side, right-hand side. Sometimes called the antecedent and then the conditional or the consequent. We want this left-hand side, but we don't have it. So we use disjunction introduction on line 2 to get it. And then once we have this left-hand side, see how they match. Here's the left side. Here's the left side all by itself. That allows us to reason to this right side there. So this would be a proof that involves another use of a rule. And we actually have a motivation to actually use the disjunction introduction rule. Oh, let me get rid of that. So here's a couple tips. This is the tip that I just kind of walked through. You use the disjunction introduction rule when you actually want a disjunction. That would be the primary reason. Another tip would be to remember that you can add as the other disjunct any formula of any complexity. So you can reason from not P here to not P, and then this formula right here can be anything, anything at all, as long as it is a well-formed formula. It doesn't matter what it is. So that's another thing to really keep in mind when thinking about this rule. Okay, so one thing to do is it's one thing to have someone explain to you how to do a skateboard trick or how to ice skate or how to paint something. And it's another thing to be able to do it yourself, because you might say oh, look at this tutorial for this magic trick I see. It looks so easy, but then when you try to do it yourself, you're like, this is so hard. I'm just totally clueless as to how to do it. So for that reason, it's important to practice the use of some of these rules. So why don't we take 2 or 3 minutes? And what I'd like you to do is try to solve both of these proofs. As a hint, you'll have to use disjunction introduction, and then we'll walk through them and just so you can check your answers and we can talk about them as well. So take 2 or 3 minutes to try to solve either or both of these proofs. Okay, so let's take a look. So the first one here should be the simpler of the two. We have a formula P, and we're trying to reason to P or Q. And once we set up the proof, we say, okay, here's our premise P, let's write it down. And now our goal is to derive P or not Q. The way you would do this is just in one step, you would write P or not Q. You can just add on that not Q there, and you would cite it by saying line 1. I use line 1, and then I use disjunction introduction. So this is, I think, the most straightforward because it's just one step and you're reasoning from a formula directly to this disjunction. And so we're trying to get into this proof, this disjunction here, and we can do it in one step. Notice that the disjunction that we reason to, it has the formula that we reason from right there. Okay, so let's look at one more and then I'll see if you have any questions about either one. So this next one here, we have 2 premises. We have Q, and then we have this big long conditional there. So let's set up our proof. We'll write Q, and then we'll also write S or Q, then M. And so both of these are premises. So we'll say, okay, these are premises. Let's write P there. And then our conclusion is M or R here. So there's our
setup, which is important. If you don't set up the proof correctly, then you might spend a bunch of time trying to solve something that can't be solved. And so here it's not as obvious as to what to do. But one thing to notice is that we have this conditional here. And like we mentioned in a previous exercise, that if you have the left-hand side of this conditional, the antecedent, you can reason to the right-hand side. So we have a motivation here for using disjunction introduction. So a reason from Q to S or Q there. And so this is from line 1, disjunction introduction. And so now we reason from Q to S or Q. We have the left-hand side of this conditional. And so we can reason to the right-hand side of this conditional, M. So we're reasoning to this right-hand side of this conditional, this M over there. And in this case, it's lines 2 and 3 conditional elimination, sometimes called modus ponens. And so now we have M. And when we look at M, we see that it's not quite the conclusion. Our conclusion is actually M or R there. And so we want this M or R. But we see that it's a disjunction. So again, we have this like indication, like I want to reason to a disjunction. What's a rule that allows me to introduce into the proof disjunctions? Well, this would be the disjunction introduction rule. And we would reason from line 4, M to M or R. So we'd write 4, M or R. So these are, two example proofs that involve disjunction introduction. One is just a straightforward like application of it. And then the other is like its application in context where we're trying to use it purposefully in a proof. So let's take a look at the next rule, which is disjunction elimination. So disjunction elimination, unlike disjunction introduction, is kind of a headache. It's a rule that I always try to avoid using at all costs, just because it's so complicated. It does have a lot of application and especially like some real world context, and it's helpful to know how to use it, but its use in proofs is kind of annoying. I'm going to state the basic idea behind it, then I'll go through some examples, and then we'll look at like the formal structure of it. So the basic feature of disjunction elimination is you're going to start by reasoning from a disjunction. So let's say our disjunction is P or Q. We're going to assume one of the disjuncts. So we're going to assume P. So you notice that P, we have this disjunction P or Q. We'll assume P. And then we need to show a formula follows from P. And let's call this formula R. So we make an assumption and we show that R follows from P. Then what we'll do is assume the other disjunct. So we have this either or statement, P or Q. We assume P, show R follows. Now we're going to assume Q and also show that the same formula follows, which is R. And so since the idea is that you know P or Q is the case, and you know that R follows from both P and Q separately, this allows you to reason to the fact that R follows from the disjunction itself. So let's look at an example. So let's say I have two options for my, what's tonight? Thursday night. I can either stay home and watch Netflix, or I can go out and just like party all night long. So I have this option, one or the other. Either I'm going to do the Netflix or I'm going to party all night long. Now, you don't really know what the consequence is of either one of these two scenarios. And so let's say on the assumption I do go out and party all night long, I have a great time. So here's this thumbs up here. So if I did party all night long, then I would have this great time. Now you can't actually conclude that I'm going to have a great time because you don't know really which one of these two options I'm going to pick. I said I'm either going to watch Netflix or I'm going to party. So it would be wrong to say, well, it's going to follow that I'm going to have a great time, because we don't actually know if I'm going to stay home and watch Netflix, because I might have a terrible time. But let's say we also knew if I went out or if I stayed home and watched Netflix, I would have a great time. Now, if we just knew from the fact that if I stayed home and watched Netflix, I would have a great time. We don't actually know if I'm going to have a great time, because if we didn't know I would also have a great time if I went out and partied, you wouldn't know which one of these two I'm going to pick, because it could be the case that if I go out and party, I have a terrible time.
But the point would be here is if you could show or you could reason to the fact that it doesn't matter which one of these two options I choose, no matter what I choose, I'm going to have a great time. Then you could reason to the conclusion that I'm going to have a great time. So the thought is if you have this or situation, this A or B scenario, and you can show the same conclusion follows or the same result follows in both cases, then you could say confidently that like that result is going to follow. So if you knew that no matter which option I picked, I'm going to have a great time, then you could conclude that I'm going to have this great time. Okay, so now let's go like take it back a step and go to like an abstract version of this rule. The disjunction elimination rule says you have a disjunction, phi or psi, and then you have two derivations of a formula. We'll just call it X here. So we have two derivations of X. In the first derivation, we assume phi, and then we show that X follows. And in the second derivation, we assume psi, which is the second option, and we show X follows. And now if you can show the same thing follows from both of those disjuncts, both of those options, then you can conclude that X has to follow because it follows from both. So this statement right here is just this right here. This statement of the rule is just saying that if you have a disjunction and you show that a conclusion follows from the assumption that you did one or the other, then you could reason to the conclusion that consequence follows from both. But I think like a lot of times people, when they see the abstract articulation of this rule, it's kind of puzzling. So let's kind of walk through what the rule looks like. So in this case, here's like the kind of structure of the rule. And notice that you have a disjunction. There's this P or Q. And then what we're going to do is assume P. So here's the assumption. When you assume, you're going to indent and you're going to start drawing a line. So you say, okay, I'm going to make this assumption P. Then you reason to a conclusion. And this reasoning can be in like 20 steps, or it could be in just a single step. So that's what those three little dots there. It's like a placeholder for formulas that you could write in. But what's important for this rule is that you see this assumption, which is this left formula right there, and then reason to a conclusion R. Then you make another assumption Q, and notice that Q is this right disjunct up there. So we have this option P or Q. We showed that R follows from P. Now we're going to show that R follows from Q. And if we're able to do this, then notice that R follows in both of these cases. It follows if P is true, it follows if Q is true. And then so we can say that R follows from both the disjunction and then these two subproofs. So we'd write the abbreviation for the rule, we would cite the disjunction, and then we would cite the two subproofs that we used. Again, this structure right here is no different from what's going on right here. We have a disjunction. We showed that if I go out and party all the time, I'm going to have a great time. And then we showed if I stay home and watch Netflix, I'm going to have a great time. And since we showed that the same conclusion follows from both, even though we don't know which one of these two I'm going to do, we can conclude that I'm going to have this great time this evening. Okay, so let's look at a concrete example that involves this particular use of the rule. Here is what you might be asked to prove. It has a disjunction, and then there's two conditionals. If it helps, we can like translate this. Like if you found that the party Netflix great time example, you could basically map that onto that example as well. So here we have the setup for our proof. We have three premises. We have the disjunction and then those two conditionals. And then our goal is to simply derive G there. We would start to do this proof by making an assumption. Now, one question people always have is like, well, what do I assume? And one nice thing about disjunction elimination is you don't really have to think about what to assume. You just say, well, okay, I'm going to use disjunction elimination. So I need to assume this first letter, this first disjunct right here. So if P or N stands for I'm either going to party or watch Netflix, Now let's sort of go ahead and assume and try to derive what is going to happen if I party. So let's assume that I party. Now, what can we reason to? Well, line 5 here is a use of conditional elimination. We have this conditional if P then G. We've assumed P is the case, and so we're able to reason to G is the case. So what we've shown here is that on the assumption that I party, then I'm going to have a great time. Okay, so what would happen next? Well, now what we would do is assume the right disjunct N. So we would assume N, which is I'm going to stay home and watch Netflix. So notice that this assumption at line 6 is the other disjunct. So we're not making up any assumptions. Our assumptions are completely guided by this formula right here. And then what we'll do is show that the same conclusion, I don't know why this says R, this should say G. The same conclusion follows in both cases. So in the first subproof here, we reason from if P to G. And now in the second subproof, we're going to reason from N to G. So we show that, if P is the case, then it's going to be G. And if N is the case, then it's going to be G as well. And so we showed that no matter which option I choose, if it's partying or watching Netflix, the same result is going to follow, that I'm going to have this great time there. And then so what we can do is finish off the proof there. We can go ahead and say that since I've shown from this disjunction and these two subproofs, 4 through 5 and 6 through 7, the same conclusion follows, which is G. We can write G in the main line of the proof. When we go to cite all this, we need to cite a bunch of stuff. We need to cite our disjunction, and then we need to cite the two subproofs. So you'd say, well, I use disjunction elimination. I'm going to cite my disjunction, which is line 1 here. And then I'm going to cite these two subproofs that I used. I showed that on the assumption that I party, I'm going to have a great time. On the assumption that I watch Netflix, I'm also going to have a great time. So you'd cite all of this right there. Okay, so a couple tips with respect to using disjunction elimination. One is try not to use it. You'd only use it if you're like, well, my back is up against the wall and now I have to use disjunction elimination. One of the reasons you would only use it as a last resort is because if you take a look at the rule, there's lots of places to go wrong. It's complicated. And so if you could solve a proof without using it, you're probably going to solve it in fewer lines and it's probably going to be more straightforward. So I would say use it only as a last resort. Another is that sometimes people try to use disjunction elimination without there being a disjunction in the proof. The only time you would ever think about using disjunction elimination is if you actually already have a disjunction in the proof. If you don't have a disjunction, you would not use it. All the elimination rules, they all have a similar feature to them where if you have, let's say, a conjunction, you can only use conjunction elimination to reason to, let's say, phi, if there's already a conjunction in the proof. And the same thing is true with disjunction elimination here. You actually need this disjunction in the proof in order to even think about using it. So the second tip would be just don't even think about using it unless you already see a disjunction. And then two more tips. One is don't do this, which if you take a look at this is a really common mistake that I see on exams. People try to do it all the time where you have a disjunction and then you reason directly to one of the disjuncts. I'm not really sure why this is the case. Maybe people are confusing this rule, which says that if you have a conjunction, like, I don't know, David is tall and David is happy, you could reason to David is tall with the disjunction. This would be saying something like David is tall or David is happy. You wouldn't know which one of those two makes the disjunction true, so you couldn't actually reason to one of them. So people do this a lot, and I would avoid using it or doing that, committing that same mistake that people make. And then the last pro tip is sometimes when people will say, I'm going to use the disjunction elimination rule, and then they ask themselves, well, what should I assume? Probably the only nice thing about disjunction elimination is that you don't have to think about what to assume. The assumption is guided by the disjunction. So you have P or N here. You're going to, don't even need to think about it. You're just going to assume P, and then you're going to assume N. You won't have to make up like the disjunction yourself. So those are, I guess, 4 tips about using disjunction elimination. But like I mentioned before, you only really learn something by doing it. So let's try to do it ourselves. Let's try to solve this particular proof. Take, I don't know, 3 minutes and try to see, can I use disjunction elimination correctly on this proof here? Okay, so let's take a look at this one. So in this case, you have 3 premises, and then our conclusion is S. One thing that stands out for this proof is that you have a disjunction here. And so you might say to yourself, well, there's nothing really I can do with these premises here. So let me, as a last resort, use disjunction elimination. You would start by assuming the left disjunct. You could start with the right, but let's just do with the left. And so we'll assume P here. And then our goal will be to try to derive a conclusion. So one thing to note is that line 2 is a conditional. You have if P then S. And so you could reason to S at line 2. Or line 5, excuse me. You'd be using lines 2 and 4 there to get S. So you have if P then S, well, P is the case, therefore S is the case. Now what we would do is to assume the other disjunct, which is not Q. You're going to assume the whole disjunct. And so we're going to assume not Q, the whole right-hand side here. And now we actually have a clear goal in mind. Our goal is to try to get the same formula that we derived in the first subproof. So we're trying to get this S here. Since we have not Q, and at line 3, it's not Q, then S. So we have if not Q, then S. And we also have not Q. We can reason to S at line 7. So this is 3, 6 conditional elimination. And so one thing to note is that, look, S here and S there. We reason we have a disjunction, and we show that the same conclusion follows, which is S in both cases. So if that's the case, then at line 8, we can now write outside of the subproof, we can simply write S. And so what we have here is line 1, which is the disjunction that we used. And then we have these 2 subproofs, which is 4 through 5, and then 6 through 7. And then the rule that we used was this disjunction elimination rule. So this is an example proof that involves disjunction elimination. Notice that it involves a lot of lines just to use this one kind of rule, but the process is straightforward. You assume each one of the disjuncts, and then you derive the same conclusion, and then you can write that conclusion outside of those subproofs.
In this video, we'll look at 2 rules for propositional logic proofs. We'll look at the biconditional elimination rule, and we'll also look at the biconditional introduction rule. For both of these rules, I'll state the general idea behind the rule. We'll go through some real-life examples. We'll talk through the form or structure of the rule, and then we'll talk about how to use this rule to solve propositional logic proofs. For them, we'll look at biconditional elimination. So just to recall, a biconditional is a formula that has this double arrow where it's like P double arrow Q. So this formula, P double arrow Q, is a biconditional. What the biconditional says is something like P if and only if Q. And so this is the same thing as saying, this is like an abbreviated way of saying if P then Q and if Q then P. So it's like saying both of those conditionals, but just in a shorter way. So P if and only if Q is the same as saying if P then Q and if Q then P. So as an example, let's say I say it will rain if and only if I take my umbrella. Well, if I'm saying this, what I'm really saying is if it rains, then I'm going to take my umbrella. And if I take my umbrella, then it will rain. The basic idea behind biconditional elimination is like the use of it as a rule is that provided you have
one side of the biconditional. So if you think about it, the biconditional has two sides. There's a left side here and a right side here. If you have a biconditional and then you have one of the sides, it can either be the P or it could be the Q, then you can reason to the other side of the biconditional. So let's look at some concrete examples. Let's say if I say it will rain if and only if I take my umbrella, and I know it's going to rain or it's raining, then it would follow using biconditional elimination that I took my umbrella. So we have the biconditional, we have one side of the biconditional, and we can reason to the other side of the biconditional. It's important to note that you only need one of the sides of the biconditional to reason to the other. So it could either be the left side or the right side. So in this first example, we have it will rain if and only if I take my umbrella. And then on a separate line, I have the left side, which is it will rain, and I can reason to the right side. In this second example, I have the right side of the biconditional. It will rain if and only if I take my umbrella, and I do take my umbrella. Now I can reason to the left side of the biconditional that it will rain. So a couple more examples. Let's say we have a premise that says John is a bachelor if and only if he is not married. Well, if you had either one of those sides of that biconditional, you could reason to the other. So in this proof, we have the right-hand side, he's not married. And so what we can conclude from this is that he is a bachelor. I will go to heaven if and only if I am forgiven. Well, I guess I'm going to heaven. So what does that mean? That means I must be forgiven for all my evil sins. Here's another example. If you're more visually inclined, I am teaching right now if and only if I am on Zoom. Well, I'm teaching right now, therefore it follows that I'm on Zoom. But we could also reason from that same biconditional, I'm teaching right now if and only if I'm on Zoom, and I actually am on Zoom right now, it would follow that I'm teaching right now. So here's this biconditional. You have one of the sides, either the left side or the right side, and you'll reason to the other side that you don't have. Let's express this more abstractly because examples we've been looking at are either visual examples or English. We, again, have a biconditional. There's a left-hand side. So we have P if and only if Q. P, well, we can reason to the right-hand side. Same thing with the reverse. P if and only if Q. Q, this is the second example here. And so we can reason to P. Even more abstractly, we can express this as saying, well, if you have a biconditional, this formula with a double arrow right there, and then you have one of the sides, notice here we have the left-hand side, then we can reason to the right-hand side. Same thing, we have the biconditional. Here we have the right-hand side of that biconditional. Well, this allows us to reason to the left-hand side of the biconditional. And even more abstractly still, you can express this whole idea right there. You have a biconditional, the left-hand side, you can reason to the right-hand side. You have a biconditional, you have the right-hand side, you can reason to the left-hand side. Let's look at it as in an example here. So here we have a proof that uses biconditional elimination. We have a biconditional at line 1. We have the left-hand side of the biconditional at line 2. And then at line 3, you see that we used biconditional elimination. We used it correctly. We have this left-hand side there, and we reason to the right-hand side. We would cite the rule that we used, which is the biconditional elimination, this double arrow E. And then we would cite the two lines that we used. We'd cite line 1, and we'd cite line 2 there. You need both of them. Sometimes people will try to reason from a biconditional directly to one of the sides of the biconditional. That would not be right. Nope, nope, nope. You need two lines, two formulas. You need the biconditional itself, and then one of the sides. Okay, let's look at another example. Here we have the proof all set up. Notice that there are 3 premises. There's a biconditional at line 1. There's the formula P at line 2, and then there is the formula Q at line 3. Now, some people will just skip right ahead and try to use biconditional, but nope, nope, nope. That would not be correct because you don't have one of the sides of the biconditional. You need to get that whole side there in order to use it. So you either need S to reason to P and Q, or you need P and Q to reason to S. So what you could do is take lines 2 and 3 and smoosh them together using conjunction elimination. And then after that, you could use the biconditional elimination rule, because notice now P and Q at line 4, we have the left-hand side of the biconditional. And so we can reason to the right-hand side. So a couple tips. The first tip is that the biconditional elimination rule is more permissive. That means it lets you do more than the conditional elimination. In the case of biconditional elimination, you just need one of the sides. In the case of conditional elimination, you actually have to have the left side, not the right side. So that's kind of nice thing about biconditional elimination. It's a little bit more flexible. Another tip is not to confuse the two, because people often do. This actually happens in regular everyday reasoning. Notice here how someone might reason is you have a conditional, not a biconditional, and they're reasoning from the right-hand side of this conditional to the left-hand side. That would be dead wrong. You can do this with biconditional elimination, but you cannot do that with conditional elimination. So the pro tip is try not to confuse the two rules. Okay, so let's practice, and let's just do one of these. Let's try to do number 2. And so in doing number 2, what I would also give you a hint about is that you are going to have to use disjunction introduction. So that's a tip for doing number 2 there. All right, let's take a look at this one. So if I were to look at this particular one, I'd say, like, right off the bat standing out, I'd say, look at that. Look at this formula right here. It's a biconditional. And so if I were going to look through all the rules, I would immediately look at the rules that have to do with biconditionals. And for that, we would see that there's this biconditional elimination rule that we just talked about. And that rule says that if you have a biconditional, and then you have one of the sides of the biconditional, then you can reason to the other. So when we look at this formula, we don't have either one of the sides, right? We don't have A or B, and then we don't have Q. So we can't really use it right away. But we could get these, at least one of the sides. And the way we could do that is by reasoning from line 2, which is just A, to A or B. And we would get this by using our disjunction introduction rule. And so we reason from A to A or B. Now that we've done this, though, we do have one of the sides of the biconditional. We have the left-hand side. We have A or B. So since we have the left-hand side, we can reason to the right-hand side. So we can reason to Q. We want to make sure we cite this accordingly. So we use line 1 and we use line 3. Now, it's important, of course, to cite the line accordingly, because if you just write the formula and someone doesn't really understand what your justification is, they're just going to assume you made it up. So you want to say, no, this is how I got it. This is my proof right here that I got it correctly. Now that we have Q, we look at our conclusion and say, well, what is our conclusion here? It's a Q or M. Well, if you gotten this far, then it shouldn't be too much more difficult to get to the conclusion, because we have Q, we want this disjunction here, and so we could reason to Q or M using, again, disjunction introduction here. So this is an applied use of the biconditional rule. We just needed to get the left-hand side here, and then we could derive the right-hand side. Okay, so let's take a look at the last rule for today, and that is biconditional introduction. So biconditional introduction, it's an introduction rule. And so what that means is it's going to allow you to write into the proof, that is, introduce a biconditional. All right. So again, a biconditional is an if and only if statement, and a biconditional if and only if Q says P only if Q, and if Q then P, which again is the same thing as saying if P then Q and if Q then P. So this P if and only if Q is just two conditionals conjoined together as if P then Q and if Q then P. So the way you would prove a biconditional is the case is by proving both of the conditionals. So if you had a statement like P if and only if Q, and that means the same thing as if P then Q and if Q then P. Well, if you could prove both of those, you could prove if P then Q, and you could prove if Q then P. Then, since that's the same thing as saying P if and only if Q, you would have a proof for that biconditional. So let's look at a concrete example of that. Let's say John is at the party if and only if Liz is at the party. Someone says that and you want them to prove it. What they would need to show is two things. They would need to show, one, if John is at the party, then Liz is at the party. And if Liz is at the party, then John's at the party. Okay, so how do you do this? Like formally, what you would do is if you wanted to prove the biconditional phi if and only if psi, this formula right there, you would start by assuming the left-hand side of the biconditional and then deriving the right-hand side of the conditional. So what you'd be doing here is proving this formula. And then you would need to do it the other way around. You would assume the right-hand side of the conditional, and then you would show that the left-hand side of the biconditional follows. So what you do is prove this formula. And if you could do both of those things, if you could prove both of those conditionals, then you could be justified in deriving that biconditional there. Okay, so here's another way of thinking about it that I think is helpful for remembering it. When we are going to prove a biconditional, what you are going to do is assume this left-hand side, and then you are going to derive the right-hand side. So this would be like step one. And then what you'll do is also the reverse. You will assume the right-hand side, and then you will derive the left-hand side. So this would be, I don't know, proof two. So this is the way I kind of think about if I had to use the biconditional introduction rule, I would need basically two subproofs where I would first assume the left-hand side, then derive the right-hand side. And then I would do it the reverse direction. I would assume the right-hand side and then derive the left-hand side. Okay, let's now take a look at like maybe a more visual example, because sometimes that's helpful for some people. Now I'm going to prove to you in a sort of abbreviated way that I am a loving father if and only if I am inseparable from my child. I have a child, I have a daughter, and so I'm going to show you that like this particular proposition is the case. The way I'm going to do this is by, again, proving two conditionals. First, I'll assume that I'm a loving father and show that I'm inseparable from my child. Then I'll show you that assume that I'm inseparable from my child. And from that, I'll prove that I'm a loving father. And if I could do both of those things, then I've proven to you that I'm a loving father if and only if I'm inseparable from my child. Okay, so what I would do is start by assuming I'm a loving father. And then I'm going to try to show to you that I'm inseparable from my child. So, I would try to give you some reasons that say, on this assumption that it's the case, it would follow that me and my child are inseparable. Okay, so once I've done that, then I would do things the other way around. I would start by assuming I'm inseparable from my child, and then arguing that from this assumption, it follows that I'm a loving father. And so I would assume I'm inseparable and then show, okay, from it follows I'm a loving father. And if I could do both of those things, like if I could fill in the gaps between those two, fill in the gaps between those like dotted lines there, then it would follow that this biconditional is the case, because I would be able to show you that both of those conditionals are true. Okay, so let's look at this in like the formal structure of the whole thing. If you're going to use this in an actual proof, what you would do here is you would assume, and you want to show that this biconditional is the case. We're going to first start by assuming P and then showing Q is true. So you would indent into your proof and you would say, I'm going to assume P. Then you would try to reason to Q. And then once you've gotten to Q, you would say, now I'm going to do it the other way around. Now I'm going to show if I assume Q, it follows that P is the case. So you would assume Q, and then you would show that P is the case. And then you could reason from those two assumptions that you have this biconditional P if and only if Q. So notice here that this P, this assumption right there, is the formula that you derived here. And the formula that you derived in the first assumption is the formula that you assume in the second subproof. Okay, so that's the structure of the rule. Let's look at a concrete example of this, and let's look at a really simple example just so you can see how the rule works. Here we have a proof where we begin with P, and then we have Q, and then we're going to derive the biconditional P if and only if Q. We start by setting up the proof. So line 1 would be P, line 2 would be Q, both of them would be premises, and then our goal is to get this biconditional. We would start by saying, well, I want this biconditional, and so what I need to do is start by assuming P, and then my goal is to derive Q there. So line 3, we indent from the proof, we assume P, and then we derive Q. I don't know if you have the reiteration rule, but if you couldn't do this, you would say like P and Q, and then you would just derive Q. Now that we have this, we're going to do it the other way around. We're going to assume Q and then derive P. And now we've shown that if P is the case, then Q is the case. And if Q is the case, then P is the case. And so we could write our biconditional P if and only if Q. In terms of like citing the lines correctly, all you would need to cite are your two subproofs right there. So you'd cite lines 3 through 4 and 5 through 6. So you'd write either like 3 through 6, or you'd write both of those subproofs. And of course, you would write the rule that you use, which is the biconditional introduction rule. Okay. A couple pro tips. Obviously, you'd only use this rule when you want a biconditional. There'd be no other really reason to use it. If you use the rule and you don't actually need a biconditional, great, but you just like derived a formula that you don't really need. So you'd only look at this if you say to yourself, oh, my conclusion is a biconditional, or I want a biconditional. And then the other thing to remember is it involves two subproofs. And so, because sometimes people will try to use this rule with only using one subproof.
So one of the most common questions students have when solving proofs is which rule, which deductive rule, Intelim rule do I use to move forward in the proof? This is sometimes expressed as a worry. Students will say, or people will say, there's just so many rules, I just am overwhelmed. Now, this is a natural concern, and this video is designed to sort of fix that worry by giving you one rule or one tip for solving proofs or for selecting which rule to use when your proof has premises in it. So this rule will only really work. It's only something to think about when you already have some premises in your proof. Now, the rule or tip is this. Look at the formulas that you have as your premises. So just focus on the premises. Do not look at the conclusion. Next, look at the main operator of those premises. So for example, let's say you had a proof and it had these formulas in it. What you would do is you would look at the main operator of these formulas. Here we have the conditional, here we have the disjunction. Then when you're looking at rules to use, you should focus your attention on elimination rules. So elimination rules are rules that have a sort of E after them that involve those operators. So in the case of line 1, you would focus your attention on conditional elimination rule. It's an elimination rule that uses the right arrow, which is the main operator of this formula. You would not focus your attention on conjunction introduction or conjunction elimination rule. These would not be, you could just ignore those as a kind of tip. In line 2 here, we have a disjunction. And so we would focus our attention on an elimination rule or some equivalent form of elimination rule that makes use of disjunction. So we would focus on disjunction elimination. We would not look at rules that involve, let's say, biconditionals or, I don't know, conditional introduction. Again, we're focusing on elimination rules that involve operators that are in our premises. So this is the tip to when you're trying to figure out which rule to use, look at your premises, identify the main operator, and then focus your attention on elimination rules that involve that operator. Let's look at a couple of examples. So let's start with a really simple example. Let's say you had P and Q, and then you had, let's say, R, and you need to solve Q. Now, a lot of people can solve this particular proof, but I'm using it just as an illustration. You might say, well, I see all these derivation rules. I don't know which one to use. The tip is this. Look at your premises, which are at line 1 and line 2. You have P and Q and R. Identify the main operator in those formulas. Line 2 doesn't have any operators. Line 1 does. It's the sign for conjunction. So now that we know this is a conjunction, you should look at the corresponding elimination rules for conjunctions. You should not look at, let's say, conditional elimination or disjunction elimination, or maybe disjunction or conditional introduction. You should look at the derivation rules that correspond to conjunctions. And in particular, you should look at the elimination rules that correspond to conjunctions. Now, there's only one, and that rule is conjunction elimination. So you should look at that rule and try to apply it here. Now, if you did, you would get something like this. Let's say you applied it kind of blindly. You might say, well, the rule says that if I have a conjunction, I can reason to either one of the sides. And let's say you reason to the left side, you use conjunction elimination on line 1. And then you said, well, it also allows me to reason to the right side. So I can reason to Q. And so this is one conjunction elimination. And look at that. You have solved the proof because the goal of your proof was to get Q. And you weren't thinking about the conclusion in the process. You were simply looking at the formula and saying, what kind of formula is it? What is the main operator? Now let me direct my attention to rules that apply to those types of formulas. Let's look at another example. In this case, we have a little bit more complicated proof. We have a proof with 3 premises. 2 of them are complex well-formed formulas, and our conclusion is Q. Again, there's many derivation, many deduction rules. Which ones do you use? I don't know how to pick. Common question, common worry. But again, our tip is if you have a proof with premises, look at elimination rules that correspond to those formulas. In other words, identify the main operator of each premise and then look at the derivation rules that correspond to that operator. So let's do that. In this formula, our main operator is this sign for conditionality. And in our second premise, the main operator is the sign for disjunction. We have the right arrow and the V. So what we should do is we should not be looking at, let's say, conjunction introduction or conjunction elimination or biconditional elimination. These we can ignore. Instead, at least as our first step, is to look at the elimination rules that involve the right arrow. And at least at some stage in your learning, the first one you're going to learn is the right arrow elimination. So you should look at this rule. You should ignore the rest and focus on this one and ask yourself, can I use this particular rule? In addition, the other rule is, or the other formula we have has the V or the sign for disjunction as its main operator. So depending on where you are, the rule that you might have is disjunction elimination. So you should ignore all the other rules and focus on these 2, at least to start your proof. Now, in our case, when we look at conditional elimination, that rule looks something like this. It says if you have a formula and the first one's a conditional and you have the left-hand side of the conditional, then you can use conditional elimination. So this is the rule here. And so you want to say, can I use this particular rule? So the first thing you're going to need is, do I have a conditional? And we do at line 1. Do I have a formula that is the left-hand side of that conditional? And we do. We have a conditional, P right arrow Q. The left-hand side is P. We have P on its own line. And so this rule says we can reason to the right-hand side of that conditional. So we can reason to whatever psi is. And in this case, it is Q. So we can reason to Q at line 4. So this is 1, 3, conditional elimination. Now notice, we weren't really thinking about trying to solve the conclusion. We weren't saying, oh, how do I get the conclusion? Instead, our approach was, let's look at our premises, let's identify the main operator, and then let's apply the derivation rule that corresponds to that operator. In our case, we had a conditional and a disjunction. We focused our attention on the conditional, and then we applied the conditional elimination to get our conclusion. Let's look at one more example. In this case, it's a good idea to pause the video and try to solve it yourself. And in trying to solve it, I think it's a good idea to say, again, use our tip. Look at the formulas, identify the main operator, and then try to focus your attention on rules, derivation rules that correspond to those operators. Okay, hopefully you have paused the video. Let's work through it. In our case, we have a conjunction at line 1. So the main operator here is this and at line 2, the main operator is the right arrow. So we should look at elimination rules that have either the and or the right arrow. So again, we should focus our attention on 2 rules, the and elimination rule and the right arrow elimination rule, or conditional elimination. We should ignore, at least for now, all kinds of other rules, conjunction introduction, disjunction introduction, right arrow introduction. These are all rules, but they should not be our first focus. Okay, so we're going to say, let's start with line 1. We have a conjunction. That rule says that if you have a conjunction, you can reason to either one of the sides. So rather than thinking too far ahead in our proof, let's just go ahead and reason to both of the sides. So at line 3 here, we'll reason to P, and at line 4 here, we'll reason to Q and R. So P is the left-hand side of this conjunction, and then Q and R is the right-hand side. So both of these are from line 1 using conjunction elimination. So we've used conjunction elimination on line 1. Now let's look at the formulas in our proof. We have a conditional at line 2, and then we have a conjunction at line 4. When we look at conditional elimination, which is the elimination rule that corresponds to this operator, we can say to ourselves, well, I cannot actually use this rule, at least at this point. The reason I can't use this rule is because the rule has this form. And so in our case, we would need R all by itself in order to reason to the right-hand side. But we also have another formula in the proof that is a conjunction. If we look at it, the main operator is that and so we can use the corresponding elimination rule. So again, we're not going to think too far ahead. We're just going to identify the formula type, the main operator in the formula, and apply the corresponding elimination rule. So we could reason to Q and we can reason to R. And so this is from 4. We're using this conjunction elimination on line 4. All right, so let's look through our proof again. We've already used conjunction elimination on line 1, and we used it on 4, and we've essentially broken this formula apart. But let's go back to line 2. It's a conditional, and so we want to use conditional elimination. Conditional elimination is only possible provided we have a conditional, and then we have the left-hand side of that conditional. So we have a conditional, which is R, right arrow T, And so we would need the left-hand side of that conditional to reason to the right-hand side. So the question is, do we have R somewhere in this proof? And we do at line 6. So since we have the conditional R right arrow T, and we have R at line 6, we can reason at line 7, to T. So this would be line 2, which was our conditional, and then 6, which was the left-hand side of that conditional. And so 2 and 6. And then the rule we used was conditional elimination, which was right here. It's illustrated right here. It's illustrated right here. All right, so what we've done here is looked at some premises and simply identified their main operator and then focused on the corresponding elimination rule that is tied to that operator. And if you see, we have our conclusion. We solved the proof without really thinking about trying to get that conclusion. We simply took these formulas and just kept breaking them apart using these elimination rules. So this is one tip for solving proofs that involve premises. Identify the main operator of the formulas in the premises, and then look or focus your attention on the elimination rules that are connected to that operator. One issue that students sometimes have when solving proofs is they get stuck. Now, I want to give you one tip to follow whenever you get stuck in solving a propositional logic proof. So here is the basic idea. Let's say you have a proof and you're working through it, you're moving along, and you get stuck. You're not sure what to do. Well, assuming you have looked at your premises and tried to use elimination rules to break those formulas down, chances are the next thing that you're going to need to do is try to make use of some introduction rule. So this is just a tip. It's not going to work every time. But the thought process here is to not look at the premises of your proof, but instead to look at whatever your conclusion is. You should look at the main operator of your conclusion and then try to focus your attention on an introduction rule. So a rule that usually has an I to the right of it as its abbreviation that corresponds to the main operator in this conclusion. So if you had, let's say, a conditional as your conclusion, you shouldn't look at conjunction elimination or biconditional elimination. You should focus your attention on, can I use a rule that introduces the type of formula I want into a proof? So you should look at rules, which in this case is conditional introduction, that corresponds to the main operator in the formula you want to derive. Let me give you one more example. Let's say your particular conclusion is a disjunction. So you want to solve for a formula of this form, phi or psi. You should not look at, let's say, conditional elimination or biconditional elimination. Instead, you should look at the disjunction rules. And in particular, you should look at rules that introduce this type of formula. So you should look at disjunction introduction. Okay, let's say we have this proof here, which is we have two premises, S and T, as well as P, and our conclusion is P or Q. Now, we started off this proof by saying, line 1 is a conjunction. Let me use conjunction elimination. I know if S and T is true, then S is true and T is true. And I did this by using conjunction elimination on line 1. And then we get to line 4 and say, oh no, what do I do next? I'm not sure how to solve this. I actually need Q in the proof, but I don't know how to get it. I couldn't get it from line 1. So what do I do? Well, again, let's follow our tip. Our tip is look at the conclusion. So our conclusion here is P or Q. That's our conclusion. What type of formula is it? This formula is a disjunction. Main operator is the V. So our tip says to look at the introduction rule that corresponds to this operator. And that rule would be disjunction introduction. So focus your attention on this rule. That rule says that if you have a formula, you can reason to a disjunction, and that disjunction has as one of its disjuncts the formula that you reason from. So if you had, let's say, A, you could reason to A or B. If you had A, you could reason to A or not B. You can reason, this can be whatever you want it to be, as long as it has the formula that you reason from as one of the disjuncts. Okay, so we looked at this rule, we thought about it a little bit. Let's come back over here. So we want P or Q. Well, we could say to ourselves, I have P, and so I can use this disjunction introduction rule to reason to P or Q. So let me do that. Let me say I have P, and then I can use disjunction introduction to introduce into the proof of disjunction. And so I got this by using line 2, disjunction introduction. So the tip here again is if you get stuck, you should direct your attention at the conclusion of the argument, identify its main operator, and then look at the introduction rule that corresponds to that operator. That will give you a hint or a suggestion as to what rule you might think about in solving a proof. Let's take a look at another proof. In this case, I think it's worthwhile to pause the video, try to solve it yourself, and if you get stuck, remember what our tip is for solving proofs. Okay, hopefully you paused the video and did your best effort to try to solve this. Let's kind of check our work. So we have a proof which has one premise, Q and S, and then the conclusion is P right arrow Q. All right, so we might start this proof by just looking at the premise and saying, you know what, I can break this apart. I have Q and S, it's a conjunction, and I know that if a conjunction is the case, then the two conjuncts are the case. So if Q and S are true, so is Q on its own, and so is S on its own. And both of these steps in the proof are justified by using line 1 and this conjunction elimination rule. Now at this point, you might say, I'm stuck. I'm not really sure what to do. I don't know how to solve this. And you might start using rules blindly. The suggestion then is to not use rules blindly, but look at the conclusion. Our conclusion here is P right arrow Q. So what you would like to do is to introduce into the proof a conditional of the form P right arrow Q. Now, you might sort of say to yourself, well, how do I do that? Well, we know it's a conditional. We know the main operator is the right arrow. So let's look at that rule, the introduction rules that correspond to the right arrow. We're going to focus our attention on this rule and ignore the other rules for the time being. Now that rule looks like the following. It says that if you make an assumption of a formula and then you have reason to a formula, then you can reason from this entire subproof to a conditional. You can introduce into the proof a conditional where the antecedent or the formula to the left-hand side of the right arrow is the formula you assumed, and the formula that you reason to in the subproof is the right-hand side of that conditional. So what we want to do is we want this formula right there to be P right arrow Q, because this is our conclusion. So we want this phi here to be P, and we want this psi to be Q. So if we kind of plug that back into the structure of the rule, we want to assume P, because remember, we want this phi here to be P, and then we want to reason to Q. So we want this psi here to be Q. So let's think about that. Let's think about how we could sort of assume P, get Q, and then we can reason to P right arrow Q, which is our conclusion. Now, we're just going to make the bold move of starting by making an assumption. So we'll indent, and then we'll assume P. You can assume whatever you want, so there's no problem with this. We can make this assumption P. Now our goal is to try to get Q in this subproof, to try to put it in there. Now depending on where you are, how many rules you have, there's a couple ways of doing this. I'm going to do it the sort of most laborious way, which is to say, well, my goal is to get Q into the proof. So I can take line 4, which is P, and line 2, which is Q, and conjoin them together. Because if P is true and Q is true, then P and Q is true. So this would be 2 and 4 conjunction introduction. And now, since I have this conjunction P and Q, if the conjunction is true, then both of the sides are true. So I could reason to Q. So this would be 5 conjunction elimination. All right. Remember, if I make an assumption P and reason to Q, I can reason to the conditional P right arrow Q. So let's do that. Let's just reason from our subproof 4 through 6 and say, I'm going to write this conditional P right arrow Q. It essentially is just summarizing what is found at lines 4 through 6. Lines 4 through 6 says I can assume P. If we assume P, then Q follows. And line 7 is saying if P is the case, then Q is the case. So our justification will be 4 through 6, conditional introduction, which is this entire subproof. Now we have our conclusion. And we got our conclusion even when we got stuck at line 3. And what pushed us home, what was the important insight that we had, was to look at our conclusion, identify the main operator of that conclusion, and then focus our attention on an introduction rule that corresponds to that operator. Our conclusion was a conditional, and so we looked at conditional introduction. So this is a tip to keep in mind when, after you've broken down, let's say, the premises of a proof and you get stuck. This is one way that one thing to think about that might help you move forward in a proof.
Mister, put down that gun. Shut up. Now come on, your money or your life.
In this video, I will explain disjunctive syllogism. I'll talk about what the rule is from a formal perspective. I'll talk about how it can be used in English, and I'll work through a couple examples. Let's look at the form of disjunctive syllogism. Disjunctive syllogism states that if you have a disjunction, in this case phi or psi, where phi and psi are both variables for any well-formed formula, and you have the negation of psi, that is the negation of one of the disjuncts, then you can reason to phi, which would be the other disjunct here. Alternatively, we could say that if you had phi or psi, and then the negation phi, then you could reason to the other disjunct, in which case it's psi. Let's look at an example in a natural deduction proof. Here we have a disjunction at line 1, the negation of one of the disjuncts at line 2. Notice that at line 1 we have R as one of the disjuncts, and at line 2 we have the literal negation, not R. And disjunctive syllogism allows us to reason to P right here, which is the left disjunct. So we're reasoning from P or R, not R, to P. If we're asked to justify this, we simply state the lines of the formulas we used, in which case this was 1 and 2, as well as the rule, which is disjunctive syllogism. Let's look at an English example of disjunctive syllogism being used. So suppose we had the proposition, there is cake at the party, or there is ice cream at the party. We'll abbreviate this as simply saying there is cake or ice cream. If we were to represent this in propositional logic, we'd write C or I. Premise 2 says it is not the case that there is ice cream at the party. So we have not I here. And so notice that we have a disjunction at line 1, and at line 2, we have the negation of the right disjunct. This allows us to reason to there is cake at the party, which is the left disjunct, C. Let's look at this last example in a little bit more detail. Let's start with premise 1, there is cake or ice cream. Now, if this is true, then it's true in one of 3 cases. Either there is cake, there is ice cream,
or there is both cake and ice cream. So premise 1 is true provided one of these three cases is the case. But now let's look at premise 2 here. It says that it is not the case that there is ice cream. So what does this do to our three cases up here? Well, it removes the second case because it's saying that there's no ice cream. And it also removes this third case right here. This first premise is true provided there's cake, there's ice cream, or there's both cake and ice cream. Now this third case cannot be true because it's not the case that there is both cake and ice cream because there is not ice cream. And so this leaves us with only one option, and that option is that there is cake. Let's look at another formal example. In this example, we have a disjunction again. We have P or not M then T. And at line 2, we have the negation of this right disjunct. We have the negation of not M right arrow T. We have it in the form of not M right arrow T. And since disjunctive syllogism states that if you have a disjunction, the negation of one of the disjuncts, then you can reason to the other disjunct, we can derive P at line 3 using disjunctive syllogism in lines 1 and 2. A final example involves robbery. I might come up to you and say the following.
Now come on, your money or your life.
Intuitively, you would reason, well, I don't want to give you my life, so here's my wallet, here's my money. This type of reasoning has the structure of disjunctive syllogism. So hopefully this video was helpful. I'll put links in the description below that refer to other videos that deal with derivation rules in propositional logic. In this video, I want to take a look at the rule for modus tollens. So this is the modus tollens rule, sometimes abbreviated as MT. So the general statement of this particular rule is as follows. What we have is a conditional. So if phi, then psi. We have the negation of the consequent of the conditional. Then we can reason to the negation of the antecedent of the conditional. So really quickly, if you take a look, we have two formulas, the conditional. We have the negation of the consequent of the conditional. So you just notice that this right-hand side of this conditional, we have on a separate line, but the negated version. So we have psi here on a separate line, which is the negation of it. So we have psi and then not psi. And then this allows us to reason to the negation of the antecedent of the conditional. You'll notice that in our conditional here, if phi, then psi, our conclusion is going to be not phi, which is the negation of the antecedent of this conditional. So if you take a look at this example here, we have a conditional, if it rains, then I get wet. We could translate that as if R, then W. Let's say I'm not wet. I didn't get wet. We can translate this as not W. And then we reason to, using modus tollens here, the conclusion that it didn't rain, so not R. Notice that we used two formulas to get to this third formula, which is the conclusion. We used these two propositions on lines 1 and 2. And then the rule that we used was this MT rule or modus tollens rule. Let's look at two examples involving modus tollens. At line 1 here, we have a conditional. We see there's if P and Q, then S. We also have the negation of the consequent here. So if we're remembering our modus tollens rule, it's a conditional. The negation of the consequent of the conditional allows us to reason to the negation of the antecedent or left-hand side of the conditional. So here we have our conditional. We have the right-hand side of the conditional. So this allows us to reason to not P and Q. What we're doing is reasoning from the Let's look at an example involving the use of modus tollens. So in this particular example, notice that at line 1 here, we have a conditional. So that conditional is nothing more than if phi, then psi. It's represented more complex. Let's take a look at an example involving conditional. Let's take a look at an example involving modus tollens. So line 1, you see we have this conditional. We have if phi, then psi. Line 2, what we have is the negation of this right-hand side of the conditional, the consequent of the conditional. So essentially we have not psi there. Now, if you remember, modus tollens says that we can reason to the negation of the antecedent of the conditional. We can reason to the negation of the Now, if you remember, modus tollens says we can reason to the negation of the antecedent of this conditional. So this conclusion that we draw here is the negation of this formula, this subformula that's part of this conditional. So what we can do with respect to this particular proof is we can reason to the negation of this antecedent at line 1. We have P and Q at line 1, and so we can reason to not P and Q at line 3. We got this by using this modus tollens rule, and the formulas we used were lines 1 and line 2. We used the conditional from line 1, and we used the negation of the consequent of that conditional at line 2. Both of those rules together allowed us to reason to line 3, which is the negation again of the Let's look at one final example of the use of modus tollens. So here again, we have a conditional at line 1, and we have the negation of the consequent of the conditional at line 2. So if you look at our consequent of the conditional line from line 1, it's not t, but at line 2 we have not t. There's one extra negation at line 2, which is saying that this not t is not the case. Remember that our rule for condition. So the modus tollens rule will allow us to reason to the negation of the antecedent of. Let's look one more time at our modus tollens rule. It says that if you have a conditional and you have the negation of the consequent of the conditional, then you can reason to the negation of the antecedent of the conditional. We're taking not phi there and reasoning. We're taking phi here and reasoning to not phi. Now let's apply this again, this idea to our proof here. We have not S, then not T. We showed that we have the negation of the consequent of the conditional. So what would we write at line 3? Well, in our example, not S is our antecedent. So the rule tells us to negate that formula. It says to take not S and then say that it's not the case. So we'll write another negation in front of it. We'll write not S. Again, we used our modus tollens rule, and then we use lines 1 and 2 to reason to that formula.
So the first rule I want to look at is hypothetical syllogism. So we'll state the rule. And I think whenever you state a rule, sometimes the rule isn't very clear until you do some examples. So here's hypothetical syllogism. It says that if you have two conditionals, so if P then Q, and then Q then R, then you can reason to a third conditional, P then R. Now, these conditionals can't be any conditionals. They have to be a conditional where the antecedent of one conditional is the consequent of another conditional. So if we take a look at the statement of hypothetical syllogism, we see this if-then statement, and you'll notice that the consequent of this conditional is the antecedent of this other conditional. So you have these parts of the conditionals that match. And so given that you have this match, or you have the same
formula, you can reason to another conditional, which is if this part, then this part. So you'll see that you reason from this phi to this chi right here. Okay, so let's look at this a little bit more in detail. Oh, I can't clear all the drawings. All right, so this is just a kind of restatement again, so you can see it differently, but just there's colors this time. Again, we have these conditionals, if phi, then psi. And so you have a conditional. Then you have this match here where the consequence of the conditional at line 1 is the antecedent. The antecedent is just the part to the left of the right arrow at line 2. And so given you have this match, you can reason from the antecedent in the conditional in line 1 to the consequence of the conditional in line 2. Okay, so this is not uncommon type of reasoning. People reason with hypothetical syllogism all the time. And you see this a lot when people reason with these chains of if-then statements. So I might say, well, if I go to the store, I don't actually smoke, but this is just an example. If I go to the store, I'll buy some cigarettes. And if I buy some cigarettes, I'm going to end up smoking. And so the conclusion then of taking premise 1 and premise 2 together would be what? Well, if I go to the store, I'll end up smoking. And so you see again that there is this, I'll buy some cigarettes, which is the consequent of the first conditional and the antecedent of the other conditional. And so we can link these two parts of the conditional together. We can reason from, if I go to the store, I'm going to end up smoking. And you see this also when people have longer chains of reasoning. So there's a famous fallacy called the slippery slope fallacy, where you say, well, if I do this small, innocuous, unimportant, seemingly trivial action, then a certain result will happen. And if that result happens, then another result will happen. And if that result happens, then disaster will strike. And then you'll reason backwards and say, well, I don't want disaster to strike, so I shouldn't do this very small action that sets off this chain of reasoning. Okay. Again, it's also helpful. You can look at things in terms of the formulas. You can look at things in terms of English, but some people appreciate more, visual examples. And this isn't part of the logic itself, but it's just a useful way of remembering the rule. Here we aren't even using sentences, and we aren't using symbols in the language of propositional logic. We're using pictures, and you could, put your own pictures in there if you want, but these were the easiest for me to draw in Photoshop. So here we have if smiley face, then person, if person, then frowny face. And if you're going to use hypothetical syllogism here, you could probably guess what the conclusion will be. Well, if smiley face leads to person and person leads to frowny face, then smiley face is going to lead to frowny face. One thing to note about hypothetical syllogism is it requires two conditionals, and the conditionals have to be of a certain sort. So when you go to cite hypothetical syllogism, you say, all right, I'm going to write a new line in the proof. I'm going to state how I got this new smiley face, therefore, or then frowny face. You want to cite both of the lines that you used. So you'd cite line 1, line 2, and then you'd write hypothetical syllogism. But since that's a lot to write, you can simply write HS to abbreviate it. Okay. The next thing to think about is when should you use hypothetical syllogism? Well, the point, because I think this is one of the harder parts about propositional logic proofs. You're asked to do a proof, and then you look at it and you say, oh my goodness, look at all of these rules. Which one do I use? There's so many. And so you might start using random rules and say, I'm completely lost. I don't know what to do. So for any rule that you develop, you not only want to know when or how to use the rule, but you also want to know when to use the rule. This one is pretty easy as to when you would use the rule. You would only ever use it or only ever think about using it if you had what? 2 conditionals. So if you only had one conditional in your proof, you wouldn't say, oh, maybe I should use hypothetical syllogism. Here is, you just look to see, do I have two conditionals? And if I do have two conditionals, then I'll think about using hypothetical syllogism. I'll see if I have the requisite conditions to use it. So let's look at some examples that would be found in a proof itself. Would be the more concrete example that you might find in an exam. Someone asks you to do a proof on an exam, and so you want to know, like, okay, how would I use it in an actual natural deduction proof? Okay, so we have if P then Q, Q then Z, and then P then Z. So this isn't the most difficult proof, but when we look at this, we'd say, well, what would I write for line 3? What would be the step that I use? What would be the move in the proof that I would use? But I'll give you 10 seconds to think about what you would write for line 3. Okay, so you would write if P then Z, and you'd write that, you justify it by hypothetical syllogism, and then you use line 1 and 2. The reason you would do this is because you see you have the two conditionals needed to use hypothetical syllogism. And then you also have that nice little match that you want. You have this Q right here, and then you have this Q at line 2. And so you can link those two formulas together to reason to if P then Z. Okay. Here is a more complicated one. This one is not the easiest one to look at. You might say to yourself, well, I'm going to use hypothetical syllogism, but like, what exactly would I write at line 3? So take 10 or 15 seconds to think about what you would write at line 3. Okay, so what you would write at line 3 is if P and S, then not Z. So why would you write that? Well, one is if you see that line 1, it's not Q. And then at line 2, you also have the exact same formula as the antecedent of that conditional. You have not Q. So you have this formula that you could think about as linking those two conditionals together. And so you're going to link this first, the antecedent of line 1 with the consequent of line 2. And that would give you P and S, then not Z. So you're creating a new conditional. And then when you go to cite the whole thing, you'd say the rule that you use, hypothetical syllogism, and then you would cite the lines that you use, which would be lines 1 and line 2. Yeah, so let's say you assumed not Q, then not Z. Oops, it's not Q, excuse me. You could use a hypothetical syllogism in this subproof if you wanted. You would just take this line 3 right here, and it would be found in your subproof, which would now be like your new line 3. So you can definitely use it in the subproof. The issue with, let's say, doing that there's nothing wrong with using that rule. But the issue is that you would have this conditional now in a subproof. And so you'd have to have like a reason for wanting that subproof to begin with. Let's take a look at one more example of this. So I just want to kind of get a sense of whether or not you understand the use of hypothetical syllogism. So I'm going to send out a poll. If you just simply answer yes or no, the question is this a correct use of hypothetical syllogism? So here are the results of the poll. So it's kind of split. Half of the class thinks, yes, this is a legitimate use of hypothetical syllogism, and then a little smaller than less than half of the course thinks that it is not. So is it or isn't it? Well, I would say that it is. So why is it a acceptable use of hypothetical syllogism? Well, notice that we have not M at line 1, which is the antecedent of a conditional, and then not M at line 2, which is the consequent of a conditional. So we have this formula that kind of links these two conditionals or chains those conditionals together. And then when we look at our conclusion here, we have if P then Z. So we're reasoning from if P then Z by way of, or this like chained formula that links those two conditionals together. So this would be an acceptable use of hypothetical syllogism. what might have thrown you off is the fact that I just kind of moved the typical order in which they were presented around. So I usually had this if P, then not M, then not M, then Z. But here I just changed lines 1 and 2. And the order really doesn't matter as long as you have this formula that is the antecedent, which is the formula to the left of the right arrow in one conditional, and the consequent in another. Oh, yes. All right, so let's take a look at this one. I'm asking you whether or not you think this is an acceptable use of hypothetical syllogism. Okay, geniuses, look at that, 100%. Everybody's like, no, this is completely wrong. What bozo is reasoning like this? Congratulations, yes, this is definitely not an acceptable use of hypothetical syllogism. There's not that formula that links those two conditionals together, so this is not appropriate. Good work. Yeah, it's not an acceptable use of hypothetical syllogism, and for probably the reasons that you recognized. All right, so it's one thing to be able to look at a proof and say, I can tell whether or not it's appropriate or not. That's like looking at, let's say, an ice skater and saying, oh, I can tell if that's a triple axle. I know the difference between a triple axle and something else. But it's another thing to be able to do it yourself, which is a different task or capacity altogether. So what I'd like you to do is to try to solve the following proof right here, and then we'll walk through it together. So take 2 or 3 minutes and try to solve this proof yourself. Okay, let's take a look at this one. So the first thing for every proof is you want to make sure you set it up correctly. If you don't do this, well, then you're doomed. And also another reason why you would want to do this, even if you can't solve the proof, is because maybe your instructor gives you partial credit, and sometimes they'll give you partial credit for setting up the proof. So even if you don't solve it, you definitely want to set it up correctly. So we do this by simply taking all of the formulas from the left of this single turnstile with a symbol for syntactic entailment and list them off one by one. And they're all separated by commas. And then we want a third column for justification. And since they're all premises, we'll write P for each one. Okay. Now the next step is, well, what do we do? And you have a couple options here. And so I'm going to give you one way of solving it. But if you have questions about, like, maybe you solved it in a different way, we can talk about that. And I can tell you, yeah, that's on the right track. It's just a different way of solving it, which is perfectly fine. So one of the things that I looked at was, if I look at lines 1 and 2, I see if P then M, and then I see M then Z. And so I see that M that's in both of those conditionals. And so I say, well, if P then M and M then Z, then it's going to follow that P then Z. And so at line 4, I wrote if P then Z, and I got this by hypothetical syllogism, and then I cited both of the lines that I used. Okay, well, this is not the conclusion, so we need to do something else. And so the next step would be to try to reason to the conclusion, which is if P then W. And so if we look at line 3, we see we have if Z then W. And if we look at line 4, we have if P then Z. So what we have is this Z right here, which is the antecedent of line 3, and Z right here at line 4, which is the consequent of line 4. So when we reason to the conclusion, we can reason to if P then W, and we use lines 3 and 4 to reason to if P then W. So in this proof, we use hypothetical syllogism 2 times, once to get P then Z, and the other time to get P then W. Let's take a look at this next proof right here, where it's a lot longer. And what I'd like you to do is just to take a moment and see if you can solve it. Absolutely. You weren't thrown off by my what are the many steps that you use? Look at all these other formulas at line 2 that need to be used. No, you can just reason directly to A and B then Z, just like you said, using lines 1 and line 3. What you recognized was that there was this M at line 3, and then M at line 1. And so you could link A and B to Z, getting you the conclusion straight away. Another thing to note about hypothetical syllogism is you kind of never really need this rule. It's kind of a junk rule. More exact, it's called a derived rule. A derived rule means that you can use a more basic set of rules to do all of the proofs that hypothetical syllogism does. That is, you can actually prove hypothetical syllogism itself with a smaller subset of rules. So the question would be like, why do I want hypothetical syllogism? What's the point? The whole point of having it in your rule system is just because it simplifies proofs. It makes some types of reasoning, some types of proofs a lot shorter. And the cost is you have another rule to remember, but the benefit is that you can shorten some of the proofs. So it's worthwhile to try. This isn't the most difficult of proofs to solve, but it's worthwhile to actually try to solve hypothetical syllogism itself without using hypothetical syllogism. So what I would like you to do here, or at least try to attempt, and it's perfectly fine if you don't get it, is to try to prove hypothetical syllogism without using hypothetical syllogism. So take, 3 minutes to try to prove this particular proof. Okay, let's take a look at this one. So to solve or prove hypothetical syllogism, what we would want to look at is the conclusion that we're trying to derive. And if you look at the conclusion, it is a conditional. And so you might say to yourself, oh, what I want to do is introduce into the proof a conditional. And so if that is your thought process, you might say, I'm going to use the rule that introduces into proofs conditionals, which is conditional introduction. That rule involves assuming the antecedent of the conditional you want to derive. So you're going to create a subproof that starts with the antecedent of the conditional you want to derive, and then trying to derive in the subproof the consequent of the conditional. So this is what you would do. You would assume P because that's the antecedent of the conditional we want to derive. And then we say to ourselves, okay, now I want to derive R. It's the formula I want to get. So how do I do this? Well, if I look at lines 1 and line 2, since I have P at line 3, I can use this conditional elimination to derive Q. So I assume P is the case, and I see line 1 says, if P then Q, I have P, therefore Q is the case. So I can write Q at line 4 using conditional elimination. Now that I have Q at line 4, I look at line 2 and say, oh, line 2 says, if Q is the case, then R is the case. And so since Q is the case as it's established at line 4, then R is the case. So at line 5 now we have R. Okay, so what was the point of making this assumption? Well, we assumed P, and then our goal was to drive R, which we have done. And now we can use this conditional introduction rule. And conditional introduction says that you create or derive a conditional based upon this subproof where the antecedent of the conditional is the formula that you assumed, which was P. And the consequent of the conditional is the formula that you derived in the subproof, which was R. And so we can use conditional introduction at line 6. Okay, so what does this show? One thing it shows is you don't need to use hypothetical syllogism. You can just do this every single time you are planning on trying to, instead of using hypothetical syllogism. But it also shows that if we ever wanted to use hypothetical syllogism, it would save us 1, 2, 3 steps. And these are 3 steps that we might not want to go through. So we get a benefit of hypothetical syllogism in that we don't have to do this type of proof every single time we want to reason in a way that's really natural for people. People reason all the time. If P, then Q, Q, then R. So if P, then R. And so again, you don't ever have to really use hypothetical syllogism, but having it in your arsenal will allow you to save steps because you won't have to do all of these steps here.
So in this video, I want to take a look at the rule for implication. Now, implication in a lot of systems, especially a Intelim system, is a derived rule. What that means is you don't really need this particular rule. You can prove everything implication does using other rules that you might have in a system. But implication is a nice rule to have because in a lot of cases, it simplifies certain proofs. So let's start by stating the form or structure of implication. What this rule states is if you have a conditional, let's say phi then psi, then you can reason to a disjunction. So it would be not phi or psi. So if you have this conditional here, you could transform it into a disjunction. Similarly, it says that if you had a disjunction where one of the disjuncts is negated, you could reason to a conditional. So if phi, then psi. Because of this, we can say that, we have one way here where we reason to this disjunction, and then you could see we're reasoning to the other direction. We could simplify our presentation of the use of implication by writing if we had a conditional, if phi then psi, then we can reason to this disjunction, not phi or psi. And we want to represent the fact that we can reason the other direction from this disjunction to the conditional by using this single turnstile, but in the other direction. So what this is saying that you can reason either way. You can take this formula, if phi then psi, and reason to this disjunction, or you could go the other way. So these two formulas, or this particular presentation of the rule, is what's sometimes called a rule of replacement or equivalence rule. Another way of putting this is that these two formulas are interderivable. So what does implication really say? So we have a conditional, and then we're translating it into a So what's going on when we use implication? What we have is So what's going on when we use implication? What's going on when we reason from, let's say, R then W to not R or W, or the other direction? But essentially what's happening is we're reasoning from a conditional, like if it rains, then I get wet, to a disjunction, if it doesn't rain, then or I'm wet. So what's going on when we use implication? Essentially what's happening is we have a conditional like if R then W, or if R then W here, or if it rains, then I get wet. And we're reasoning to a disjunction as a formula that says something like not R or W, or the other direction. Something along those lines of if it doesn't rain, So what's going on when we use implication? Well, if we let our conditional, something like if R then W, stand for if it rains, then I get wet, and we let our disjunction that we're reasoning to, something like not R or W, then what we're doing is reasoning from a sentence like if it rains, then I get wet, to a sentence like either it does not rain or I get wet. And what's happening here is we're saying that this conditional says the same thing as this disjunction right here. That these two formulas are just two different ways of saying the same thing. They're true and false under the same circumstances. They're equivalent to each other. And so it's perfectly legitimate to replace the conditional here, if it rains, then I get wet, with this disjunction here. Either it does not rain or I get wet.
Now, for some people, this is not quite obvious. So it's helpful to look at, let's say, a truth table to see that these two sentences here, at least with respect to logic, are equivalent. So let's look at one. So here's our truth table here. We have the conditional, if phi then psi, and we see that's false just in one case, in the second row here. And then we have our disjunction, not phi or psi, and we see it's also false in one case. And in all the other cases, they match up in terms of truth values. So we see that these two formulas are equivalent, and so that motivates the use of the implication rule. Since these two formulas are true and false under the same circumstances, since they're equivalent, we can replace the conditional with this particular disjunction. So let's look at an example of implication in a proof. So at line 1, we have P then Q, and you could use implication on line 1 to derive not P or Q. We would cite the line that we're using, which was line 1, and then indicate that we're using implication. And of course, since you can swap one formula out for the other, we could do the other direction. We could reason from this disjunction at line 2 back to the conditional that we started with at line 1, writing if P then Q. But at this time, we're using line 2 implication here. So you see again that all we're doing here is replacing this conditional with a formula that says the same thing, but just in a different way with this disjunction. Let's look at a more complicated example of implication. In this case, we're looking at a negated conditional. Now recall that in implication, we can take a conditional and replace it with the formula that says the exact same thing. So with respect to line 1, what we can do is take that conditional that's found in those parentheses and replace it with a disjunction that says the same thing. The key aspect here to keep in mind is that we want to make sure we negate the antecedent of the conditional right there. So in our disjunction, we have not P rather than simply P. Now I want to look at one more example of implication. Let's say we had the formula not P, right arrow S. Now let's make it not S. So here we have a formula. If we were to use implication on this, recall that the rule states that if you have a conditional, you can transform this formula into not phi or psi. And so when we apply implication to not P, then not S, the formula that we would write is not P or not S. The key thing to focus on with respect to the use of implication is we have a conditional, and this phi here can stand for any formula. In this case, phi stands for not P. And so it says to take that formula and add a negation to it. So you see we're adding this negation to phi. And so even though P is already doubly negated, we're going to add a negation. With respect to psi right here, it says don't do anything to it. Simply represent it as the right disjunct when you use implication. So even though not S is negated here, all we're going to do is take not S and write it as not S as follows. We're going to keep it, leave it alone. Whatever formula this is, we're going to just move it to. Okay, so what we're going to look at now is De Morgan's laws. So here's De Morgan's laws. It's not the prettiest thing to look at, but we'll talk through some examples of it, tie it to English, and I'll give you another visual example of it as well. So De Morgan's laws say that if you have a negated disjunction, so not, here's the negation, it is the main operator. So it's negating a disjunction right here. You can derive a conjunction where the conjuncts of the original disjunction are now negated. So you see that we have this negated disjunction, and then we reason to a conjunction but you'll note that both of the conjuncts are negated. And it allows you to reason the opposite direction. So you could reason from a conjunction, like this formula, not P and not Q, to a negated disjunction. So it's a rule that allows you to move back and forth between disjunctions and conjunctions. In addition, De Morgan's laws also states that if you had a negated conjunction, so this is where like the operator is the and, you can reason to a disjunction, but the disjuncts of the disjunction that you are reasoning to are now negated, as well as vice versa. So you can swap those two formulas back and forth. So if you look at De Morgan's laws here, we have this negated disjunction, and we can reason to a conjunction, but now the conjuncts are negated. In addition, you can reason the other direction. So you could reason from the negated disjunction to the conjunction, or from the conjunction to the negated disjunction. Same thing with the other one. You can reason from the negated conjunction to a disjunction, where the disjuncts are negated, and you could reason the other direction. Okay, so I think De Morgan's laws is important, but I really don't think people tend to learn them just by looking at the rule itself. You learn it by using it, looking at some examples, thinking about it in from different perspectives. So let's try to look at it from different perspectives and hopefully get a clearer sense. So one question that you might have is that, isn't this somewhat related to the truth tree rules that you have for propositional logic? And the answer is yes, in a way. So let's say you had a negated disjunction. So then if you had a negated disjunction and you're going to use a truth tree rule, you would use the negated disjunction decomposition rule, and that would require you to stack the formulas, and you would have this negated disjunction stacking. So that kind of tells you, hey, what's going on here? We have this negated disjunction, and we're reasoning basically to a conjunction, but we just tend to stack it right here where both the sides are negated. The kind of difference, though, is that in this case, we can reason the other direction. You can reason from this negated, this conjunction with the two negations back in the other direction. So it's a little bit different from the tree rules from propositional logic. Okay, so let's take a look at De Morgan's laws. So let's start with English. De Morgan's law says you take a formula of one type, you can swap it out with another, and vice versa. And there's something similar that goes on in English, that people can sometimes say the same thing in two different ways, and you have these equivalent expressions in English. So if someone says neither P nor Q, we say they're saying the same thing if they say not P and not Q. And so if they were to reason from neither P nor Q to a sentence, not P and not Q, we'd say, yeah, that's a perfectly fine way to reason, because they're just saying the same thing. And they could reason back the other direction. If they said not P and not Q, they could reason back to neither P nor Q. What this is involving is you're reasoning from a negated disjunction to, if you look at not P and not Q, to a conjunction where the propositions or the conjuncts are both negated. Same thing is the case with the negated conjunction. If someone says not both P and Q, so they're saying not both of these, then they're reasoning to not P or not Q. And so if you were to do a truth table for these particular formulas, you would see that they're true and false under the same scenarios. Okay, that's one way of thinking about it. Maybe you're more English inclined, and so you try to think through the rules in terms of the English language. So let me give you one more example along these lines. So let's say I said, I don't want, I want neither bread nor a cupcake. So you make this bread and I say, ugh, that bread looks gross. And then I look at your cupcake as well. And I say, ugh, that cupcake looks gross. Why did you put the frosting on it like that? And so you say, I say, I want neither your bread nor your cupcake that you've made. You're obviously a terrible baker. And so what does this entail? Well, it entails a conjunction, which is I don't want your bread and I don't want a cupcake. You would understand that. You'd understand if I said this, that either one of these sentences, that you'd be saying the same thing here. The same thing is if you use the negated conjunction. If I said, I don't want both bread and cupcake, here I'd be saying, I might be open to one or the other, or neither, but I definitely don't want both of these at the same time. The bread is a pumpkin loaf, so it's pumpkin based, and the cupcake is a pumpkin based cupcake. And so I would say to myself, if I said, I don't want both bread and cupcake, that's just too much pumpkin for me in one sitting. So I either want one or the other, but not both of them together. And so this would entail, you would understand from what I said from this is that I don't want bread or I don't want cupcake. Okay, so let's look at an example of this. So here is an example in a proof, a simple one-line example where we use De Morgan's laws. So you see at line 1, we have what? We have a negated disjunction here. And so when we apply De Morgan's laws, we take this negated disjunction from line 1 and we turn it into a conjunction. So we're changing the sign from a disjunction to a conjunction. And then we're negating each one of these internal disjuncts here. When we use De Morgan's laws, of course, we want to cite the line. We want to say, okay, I used De Morgan's laws. Here is the justification. I'm telling you I used De Morgan's laws. So you'd write De Morgan's laws or DEM to indicate that this is the rule you used. And when we use De Morgan's laws, we only use one line. We're taking a formula of one type and swapping it out with another. So it applies only to a single line. So you wouldn't cite multiple lines here. Oh, let me remove all this annotation stuff. Here is another example of De Morgan's laws. So if you take a look at line 2, what we have is this conjunction. And one thing to note about this conjunction is both of the conjuncts are negated. So you see that at line 2, we have not R, and we also have not Q. And so we can use De Morgan's laws. And when we're doing this, we're saying, I'm going to take this conjunction and I'm going to turn it into a disjunction. I see that both of those conjuncts are negated. It's not R, it's not Q. And so I can transform it with a formula that says the same thing. It's saying the exact same thing, it's just saying it in a different way. And the rule that allows you to do that again is De Morgan's laws, DEM. And we use it on line 2. So De Morgan's laws is super important. It's very helpful. And the reason it is so important and helpful is it simplifies proofs to an incredible degree. Proofs that would normally take sometimes 30 lines long now can be solved in a couple steps. And so this is one of the reasons it's such a great rule, not because it has any spiritual or mystical qualities to it. It just makes your life so much easier. And so if someone gave you something that says, oh, this makes my life so much easier, you'd say, oh, thank you very much. I'm going to use this all the time because I want my life to be as easy as possible. Because of that, it is helpful to think about ways of remembering how to use De Morgan's laws correctly, just because it is such a helpful rule. So in various cultures, people, especially children, play this game called leapfrog. Sometimes it has different names in different cultures. Sometimes it's called like goat hop. And there are different variations on it. If you've never played this game, that's fine. But the idea is that a person kind of crouches down and you leap over them. And then they try to leap over you and so on and so forth. And the more competitive version of the game, you kind of get taller and taller. So it makes it more difficult to leap over them. Okay, so thinking about that in mind, this is a really stupid heuristic, but you can think about that game when you use De Morgan's laws to ensure that you use it correctly. So let's say you had a negated conjunction. You have this negated conjunction, not P and Q. You can think about the negation hopping over the parentheses and applying to the internal parts, the internal conjuncts. So the negation is going to leap over both the left parenthesis right here and apply to the P and apply to the Q as well. In doing so, since Leapfrog is a magical game, is going to transform this conjunction into a disjunction here. So not only is it going to attach to both the P and the Q, but it's going to transform, since Leapfrog again is a magical transcultural game, the conjunction into a disjunction. Now, and the same thing is true for the disjunction, the negated disjunction. We have a negation on the outside. It needs to leap over the parenthesis and apply to both the P and the Q. And in doing so, it is going to transform this disjunction into a conjunction. This is a helpful way of thinking about or visual metaphor if you're more visually inclined and you think, okay, I'm going to use this rule. You said it's important. It's bound to come up in various proofs. You can think about the negation leaping over the parentheses and applying to each of the two parts, and then it changes the sign from either a conjunction to a disjunction or a disjunction to a conjunction. All right, so this is definitely, I think this metaphor is helpful when you have to apply it to complicated negated conjunctions or disjunctions. So I would say take a minute, just write on your piece of paper, whatever scratch you have. If you're going to use De Morgan's laws and apply it to this particular formula that you see here, this negated disjunction, what would that formula look like? So take a minute to try to apply De Morgan's laws to line 1 here. Okay, so let's take a look at what De Morgan's laws would look like. In thinking about this negation, again, it's going to leap over the parenthesis and apply to both of the propositions here, both of the disjuncts. So what it would do is add a negation to each one of those disjuncts. So it would turn it from not P to not P. So it's leaping over the parenthesis and applying to that whole formula. And then it's also leaping over the parenthesis and applying to not Q or S. So it's applying to that whole formula. Now, once you have these not P and not QS, you of course would maybe take off these negations using the double negation rule. But when you're using De Morgan's laws, that negation is leaping over and applying to each one of those subformulas. And then, of course, it's transforming it from a disjunction, this V here, to a conjunction, that caret there. So the next kind of question to think about is, when should you use De Morgan's laws? And the answer to this is pretty straightforward. You typically use De Morgan's laws in one direction. Use it in the direction of taking a negated disjunction or a negated conjunction and applying it in that direction. That is, taking this negated formula and turning it into a conjunction or a disjunction. The reason for this is because now, once you've used De Morgan's laws in that direction, it just becomes easier to use other rules. So if you use De Morgan's laws on, let's say, not P or Q, you would derive not P and not Q. And when you look at not P and not Q, this is a rule like you can do stuff with. Like you can say, oh, this is a conjunction. Let me break that conjunction down into simpler parts. Now I can use it first with some other formulas. So it turns it into a formula that is easier to use. If you were to reason in the other direction from, let's say, not P and not Q to not P or Q, the next thing you would say is, well, what rule can I use on this? Like, what can I do with this formula? And there really isn't anything. It's like nothing you can do. It's like a formula that just like no rules apply to it. The same thing with the negated conjunction. You have this negation and it negates this whole conjunction here. Use De Morgan's laws and it turns it into a disjunction. Well, now there are some rules that you could say, okay, maybe I can use these rules on this new formula that I have, this disjunction. But if you look at this negated disjunction or negated conjunction, if you think to yourself, like, what rule can I use on this? There's really nothing. There's no rules that are going to help you solve a proof. So in general, we try to use it in the direction of deriving, or whenever we see a negated disjunction in the proof or a negated conjunction in the proof, you should think about using De Morgan's laws. Okay, so here is just an illustration of an example we saw earlier. We saw not R or S. We used De Morgan's laws on it. It turns it from a negated disjunction into a conjunction. And once we do this, then we can break this conjunction down at line 2. It says line 1 conjunction elimination. It really should be line 2 conjunction elimination. That's my bad. So what we're doing here is, now that we've used De Morgan's laws in this direction, we are able to like do something with the resulting formula. Here's another example. So we have a negated conjunction at line 1. And whenever you see a negated conjunction or negated disjunction, you should say to yourself, maybe I should use De Morgan's laws. It's a rule that allows me to get at formulas that I can actually do something with. So if we use De Morgan's laws on line 1, it gives us not R or not S. And this is a formula that we can do something with. We can use disjunctive syllogism on it. And since we have not R or not S, and we have not S, we can say, well, this formula right here cancels out this one. It's not the case that not S, and so it must be R. So again, De Morgan's laws, you should think about using it whenever you have a negated conjunction or a negated disjunction, because it allows you to potentially use other rules to solve your proof. One kind of caveat, this is a sort of rare case, but it may come up, is it's helpful to think about what De Morgan's laws does. It says, I'm going to take a formula and I'm going to swap it out with one that says the same thing, but in a different way. If that's the case, then it can be applied not only to the entire formula, but to parts of formulas, that is, subformulas. So if you look at line 1 here, what we see is we have a conditional. So we don't actually have a disjunction or a negated disjunction. But as part of that conditional, what do you see? You see the consequence of this conditional. So a subformula of a larger formula is a negated disjunction. And so what you could do, if you wanted to, is you could apply De Morgan's laws to this part. You can replace it with a formula that says the exact same thing, but it just says it in a different way. So we can replace this negated disjunction with a conjunction that each of the parts are negated. So this is not like a regular occurrence, but it's similar to, let's say, if you had a conjunction and let's say one of the parts was doubly negated, you could apply double negation to this formula to remove the 2 negations. And so you're applying it not to the entire formula, but to part of the formula. Again, I want to emphasize that you should always think about using De Morgan's laws whenever you see a negated conjunction or a negated disjunction. It greatly simplifies things, and it should be, I think, your default move whenever you see one of those 2 formulas. It's helpful, I always think, to have some kind of trigger, some type of heuristic for remembering that, though, because it is so important. So even though like logic seems pretty sterile, one way you can think about it is just to think about something really, really gross, something that disgusts you, that you feel like kind of sickened by. And so now that you have that kind of sickened image in your mind, you should associate negated conjunctions and negated disjunctions as sickening. They're gross, they're repulsive. And the reason they're so gross and repulsive is because you cannot do anything with them. You can't apply conjunction elimination on this negated conjunction because it's not a conjunction, it's a negated conjunction. You also cannot apply, let's say, disjunction elimination or disjunctive syllogism on this negated disjunction because it's not a disjunction, it is a negated disjunction. So these rules, I think, are gross, or these formulas are gross because you can't actually apply any rules to them. So the thing you should think about is if you have these gross formulas, and that's kind of weird to say that there are gross formulas, but if you have those gross formulas, one thing that you can do is remove that grossness by applying De Morgan's laws to it. So as soon as you see these formulas, I think it's an effective step in a proof to apply De Morgan's laws immediately, and then you can do something with the resulting formula. Okay, so let's try a couple examples of De Morgan's laws. This one is relatively straightforward, but it's always important to start with the simple proof and then kind of work our way up. Take, I don't know, 2 minutes and try to solve this particular proof right here. Okay, so let's take a look at this one. Line 1, we have a negated disjunction. And so you should say to yourself, oh, gross, this formula is so disgusting. There's nothing I can do with it. What in the world could possibly help me here? The answer is pretty straightforward. You should use De Morgan's laws. Using De Morgan's laws, we're going to negate both the internal disjuncts, and we'll turn it into a conjunction. We are, again, going to play our leapfrog game. This negation is going to leap over the parenthesis to this P and leap over to this T. So both of those internal formulas are going to be negated. And we're going to turn this disjunction into a conjunction using De Morgan's laws. Again, we'll cite De Morgan's laws, DEM for De Morgan's laws. And then we're going to cite the line that we use, which was line 1. It's helpful to remember that even though I've just emphasized really strongly that whenever you see a negated disjunction, you can reason to a formula using De Morgan's laws, but you don't also want to forget about, you can use De Morgan's laws to reason in the other direction. So in this case, we have not P and not T. And so when we look at this, if we were to try to derive not P or T, we might not really know what to do here. One thing we could do is take those two formulas, not P and not T, put them together in a conjunction. And so now what do we have here? We have a conjunction, and both of the conjuncts are negated. And so we can use De Morgan's laws to reason in the way that is not very common, but still possible, which is to turn this conjunction, this not P and not T, into a negated disjunction. So we can use De Morgan's laws on line 3. Now, I just want to, I just throw this out here just because I want to, even though I've emphasized that there's one preferred direction, there's also the other direction that is less common you'd find in a proof, but nevertheless still possible. Okay, let's take a look at another proof. This one is not the easiest proof, but it can be solved in a couple lines. Here is a negated disjunction, and you're asked to reason to simply not S. So take a moment and take, let's say, 5 minutes to try to solve this particular proof. Okay, let's take a look at this one. So we look at this formula, we say, ugh, this formula looks gross. It's a negated disjunction. What could possibly help us? Let's use De Morgan's laws. When we're thinking about using De Morgan's laws, we can think about this leapfrog method. This negation is going to hop over the parenthesis and apply to the not R, making it not R, and to this other disjunct, which is M or S. So what does that look like? It looks like not R and not M or S. Oh, this doesn't look very good. This doesn't give us S. This is problematic. So one thing we could do is say, well, now we have a conjunction. Let's break that conjunction apart. We can reason to not R, and if you wrote that down, perfectly fine. That's a good step. But since we see S in that not M or S, let's just reason to that single conjunct using conjunction elimination. We have an and statement, so we can reason to either side. Now at line 3, what do we see? Oh, this is another negated disjunction. Ugh, it is very gross. So let's use De Morgan's laws on it so we don't feel as queasy as we did before. Now we have not M and not S using De Morgan's laws on it. And now we have a conjunction. Great, a conjunction we can do something with. We can break this apart. So you could reason to not M, or you could reason to the conclusion, which is not S. So poof, there it is. Not using conjunction elimination, we reasoned from line 4 to the conclusion, not S.
So in this video, what I'd like to do is introduce the language of predicate logic. And I want to do this by explaining why we would move from a logical language like propositional logic to another logical language at all. So it's helpful to think about what's good about the language of propositional logic. What are its strengths and what are its weaknesses? And once we identify these strengths and weaknesses, it will allow us to find a motivation for moving to a different logical language, like the language of predicate logic, which I'll talk more about in future videos. So the first strength of propositional logic is that if you have an argument that's valid in the language of propositional logic, I'm using the term valid here sort of loosely in terms of either a case of semantic entailment or a case of where you can provide a derivation or syntactic entailment. But let's say you identify an argument in the formal language of propositional logic as valid or a good argument. You can translate that argument from propositional logic into English, and the resulting translation will be a valid English argument. And so this gives us a nice way of identifying valid arguments in English, because if you can find one in the language of propositional logic, then you can find one in English. The second nice feature of propositional logic is that there are decision procedures associated with it. That is, if you're given an argument, you can use a truth table or a truth tree to kind of mechanically test to see if it's an instance of logical consequence. It's an instance of, it's a valid or invalid argument. You can do other things with tables. Of course, you can check to see if a set of formulas are consistent, or check to see if a proposition is a tautology or something like that. But the thing that's nice about it is, in contrast to English, where we might make use of a tool of imagining the premises being true and the conclusion false, in propositional logic, since it's formulated as a formal language, we also have this kind of algorithmic or mechanical or automatic way of checking to see if the argument is valid or invalid. So that's a nice perk. The third thing is that there's a proof system. We have these set of codified rules for reasoning from certain formulas to another formulas. The fact that we have this codified set of rules is a nice feature. It allows kind of consensus or uniformity about like whether or not something is a proof of a formula or not. So what's the problem with propositional logic? The main problem with propositional logic is its expressiveness. That is, it is not expressive enough. And so what does this mean? What it means is that there are some valid arguments in English, some arguments in English where we say the conclusion is a logical consequence of the premises. But when we go to translate that argument into the language of propositional logic, what we see is it doesn't come out as an instance of logical consequence. That is, we have a valid argument in English. When we look in the language of propositional logic, what do we see? Well, it doesn't come out as a valid argument in the language of propositional logic. So that seems like a kind of problem with the formal language. What we would like is that the formal language is capable of capturing every valid argument in English, if not more. So let me give you an analogical example of why this might be important. Let's take a language, and we're just going to kind of make up a language, but we'll call it language L1. Now let's say this language has, a host of different terms, but when we talk about emotions in this language, it has a term for, let's say, complete and utter happiness. And there's also a term for complete and utter sadness. Now this language, if you're feeling very happy, you're able to convey this feeling of happiness to someone else. You just use the term that corresponds to expressing a state of complete and utter happiness. And if you're just in tears, crying deeply, you're so sad, then you're capable of conveying that idea to other people. But take a scenario where, say, you can think of a number of different scenarios, but let's just use an example of, let's say you have a child and your child is going off to college or doing something like that. Your little son or daughter or whatever is going off to college, and you like your child, And so you might have a sort of mix of emotions. On the one hand, you are kind of happy. This is a good thing for your child. You think that they aren't going to be driven into severe debt. You think this is going to help develop them as a person. But on the other hand, you are also a little bit sad about it. You're going to miss your child. This is a person you raised and spent time with for many years. So you have what we might say is a kind of mix of emotions, so it's a sort of blend. Or you might say on the one hand, you feel happy about this whole thing, and on the other hand, you feel a little bit sad about it. Now, if we look at the language L1, one of the things that we see is that it looks difficult to express this. That is, we might convey to someone that we have this feeling, this mix of happiness and sadness, where we don't feel completely happy about it and we don't feel completely sad about it, but instead we feel a kind of hybrid of those emotions. Or if you don't think like that's what's an accurate characterization of the situation, you at least want some type of term to say that I have this kind of combination of these two feelings, or I feel happiness in this respect or that respect. And so we need a way of kind of linking those two. So this is an artificial example just to kind of illustrate that one of the problems that we identify with language 1 is that it doesn't seem to be expressive enough. It only allows us to express things in terms of complete happiness and sadness. But what we would like is a language with a little bit more power. We want a language that gives us the capacity, these are muscles here in case you didn't know, to indicate the expressiveness. We want a language that gives us the capacity to kind of combine different ideas together, or let's say kind of fuse them together. And so we would like a language, let's say L2, that is capable of doing this. And if we don't have such a language, we feel that this language is lacking in some respects. It doesn't fulfill the function or the kind of goals that we want it to. So how does this apply to the language of propositional logic? Let's take an argument that looks intuitively valid. That is, we want to say that this is an instance of logical consequence and show how propositional logic sort of struggles to capture this aspect of it. So here we have an argument, all men are mortal, Socrates is a man, and Socrates is mortal. And when we look at this, we might say, oh, this is a case of logical consequence. We have if we can imagine the premises being true, and if these premises are true, if all men are mortal, so we have, let's say, this kind of circle, and all the men we put in here, and it's in a sort of larger class of all the mortal things, living beings that aren't like humans or whatever. And we say that Socrates, we have this kind of Socrates person right here, he is a man. And if he's in this kind of class of individuals who are men, then he's in the larger class of individuals that are mortal. So we say that it's impossible for the premises to be true and the conclusion to be false. This scenario can't hold. And so we think this is a kind of valid argument to use a sort of loose term. And we would like a formal language to be able to capture this. But what we see when we try to translate this argument into the language of propositional logic is there isn't a clean way of doing it. If we look at sentences and whenever we identify if then, we use the conditional sign or not to use negation. What we see when we look at this particular argument is it looks like a series of simple sentences. This kind of predicate or subject and predicate. And so we might translate this using simple sentences, using propositional logic or propositional letters. So for premise 1 right here, we might translate it as M. So all men are mortal. We just let that be translated into the language of propositional logic as M. Premise 2, we can translate as S. And the conclusion, we can simply translate as R. So what this gives us is, in the language of propositional logic, is M, S, therefore R. But the issue is that there isn't a way to prove that R follows from M and S, and R is not semantically entailed by M and S. Such that if we used a truth table and truth tree, we would see that it doesn't show or doesn't determine R to be a logical consequence or as following from M and S. In other words, kind of sum this all up, it gives us the wrong result. We want this particular argument to be identified as valid in the formal language, but that doesn't occur. And so we think that there is a problem. There's a sort of problem with propositional logic. It doesn't express this particular argument as valid. So to summarize here, what we're saying is that the language of propositional logic is not expressive enough. What we want is a language that's capable of expressing all of the arguments that propositional logic identifies as valid, but also a host of others that it doesn't capture as valid when those arguments are valid. So what this does is motivate a move to a more expressive or more powerful logical language. And that's the language of predicate logic, which I will kind of talk about in future videos. This language is supposed to, or does, capture all of the arguments that are valid in propositional logic, as well as a host of other ones, including that Socrates is mortal example. It will take that argument, translate it into the formal language, and when we run a particular test on it, it'll come out as valid, which is the result that we would like. So in this video, what I want to do is talk a little bit about the language of predicate logic, as well as introduce the symbols of this particular language. So the language of predicate logic is a formal logical language. And as a formal language, it consists of two principal parts. It consists of a set of symbols and a syntax. The symbols are simply its base notation or alphabet, if you will. And the syntax, all it does is express the appropriate or grammatical way of putting those symbols together. So you have a host of symbols and specialized notation, and that's a set of symbols. And the syntax says, here's the proper way you can put those symbols together. And that's what a formal logical language is. But there's always another aspect of a logical language, and that's its semantics. Once you have this formal logical language, then you say, okay, now what does this language mean? What do these symbols mean, and how do they get their meaning in combination with each other? And that's what semantics essentially does. It takes those well-formed formulas, those, might say grammatical sentences of the language, and then it will use different functions or features to assign them a truth value, typically true or false, but there are other logical languages that have a semantics that, does different things with them. So it's helpful to see a kind of visual diagram of this. So we have the logical language here, the language of predicate logic, and it consists of symbols. These are all the different letters that make up the language. And that logical language also consists of a syntax in terms of a set of grammatical rules. And that's what the formal language is. It's just the symbols and the syntax. And once we have this formal language in place, we'll go ahead and use various functions or rules to assign the well-formed formulas, the full units of the language, a truth value in terms of true or false. So in the remainder of this video, what I'd like to do is talk about the symbols of predicate logic. Here we won't talk about what the symbols mean, nor how to put those symbols together in a grammatically correct way. Instead, we'll just introduce the basic symbols or alphabet of the language. The first set of symbols to look at are called names. And names refer to lowercase letters A through V with or without numerical subscripts. So let's take a look at some examples here. So the letter A is a name, B is a name, and C is a name. But since we don't want to be limited simply to the 23 or 24 letters right here, instead we want an infinite number, we'll allow for subscripting positive integers to these names. So A sub 1 will be a name, A sub 2 will be a name, A sub 3 will be a name, and so forth and so on. The next symbol that we'll look at are called end-place predicates. End-place predicates refer to uppercase letters A through Z with or without numerical subscripts. So to look at a couple examples, A is a end-place predicate, B is an end-place predicate, and C is an end-place predicate. And we could kind of go onward and onward all the way to Z. In addition, since we want an infinite number of end-place predicates at our disposal, we'll allow for A sub 1 to be an end-place predicate, B sub 2 to be an end-place predicate, C sub 50 to be an end-place predicate, and so forth and so on. The next symbol to look at are called variables, and variables refer to lowercase letters, W through Z, with or without numerical subscripts. So, for example, X will be a variable, Y will be a variable, Z will be a variable, as well as W. And again, since we want an infinite number, X sub 1, X sub 2, X sub 3 are all variables. In addition to variables, we'll have the truth functional operators, sometimes shortened to just be referred to as operators. So we have the sign for negation, conjunction, disjunction, implication, and the double arrow for biconditionality. We'll make use of parentheses. In addition to parentheses, we'll optionally make use of square brackets or braces, depending on how you call them, as well as curly braces or curly brackets, depending on how you talk about them. Finally, there are two quantifiers. These quantifiers are the universal quantifier and the existential quantifier. The universal quantifier refers to the upside down A, and the existential quantifier refers to the backward E. In the next couple of videos, we'll look at two different things. We'll look at one, the syntax of predicate logic, which refers to how to put those symbols together in organized or grammatical units. That is, we'll look at a set of formation rules that specify the well-formed formulas of the language of predicate logic. Once we have an understanding of the syntax of predicate logic, we'll turn to the semantics. That is, what do each of these symbols mean, and what do they mean when they're put together in grammatically correct or syntactically correct ways? In this video, I want to look at the syntax of the language of predicate logic. The syntax refers to the appropriate or grammatical ways of putting different symbols together to form well-formed formulas. So let's take a look at this. Okay, so let's take a look at the formation rules or the syntactic rules for predicate logic. There's a couple ways of specifying these formation rules, and we are going to err on the side of simplicity rather than breadth or precision. So let's take a look. So here are the 5 formation rules, or 4 plus a kind of additional clause. The first formation rule says that if you have an n-place predicate followed by n names, then the result is a well-formed formula. So let's say you have P, and P is a one-place predicate. That means there is sort of one spot after it for a name or term to kind of go in there. Then provided there's a single name after it, because or one name after it, then the result, PA, is a well-formed formula. Now let's say you had a two-place predicate, and the two-place predicate was R. And since it's a two-place predicate, there's space for 2 terms after it. And provided you had 2 names after your two-place predicate, the result would be a well-formed formula. So with this first rule, what we're looking for is, given some predicate, whether it be P or R or Q, we want to identify the number of places after it. That is, what type of predicate is. Is it a one-place predicate, two-place predicate, three-place predicate? Once we've identified that, provided it has the appropriate number of names after it, then the result will be a well-formed formula. The next 2 rules aren't terribly interesting in that they don't introduce anything new from propositional logic. What the second rule states is that if you have a well-formed formula, let's call it P, then the result of negating the entire thing is a well-formed formula. In the case of rule 3,
If we know that P and Q are well-formed formulas in the language of predicate logic, then we can put them together in a conjunction, a disjunction, a conditional, or a biconditional, and the result will be a well-formed formula. The next rule states that if you have a well-formed formula, let's say you have P, and P is a well-formed formula, and that formula contains the name A, or any name for that matter. And if Pxa is what results from substituting the variable x for every occurrence of A in P, then the formula AX PXA or EX PXA are well-formed formulas, provided that PXA is not a well-formed formula. This rule will require a little bit more specification. It might not be kind of clear what's going on here, so we'll come back to it. What we want to kind of identify now is that here is this rule for forming quantified formulas, for forming well-formed formulas with the quantifier associated with it. We'll come back to how the whole mechanics of this work in a moment. What this fifth rule states is that nothing else is a well-formed formula in the language of predicate logic, except those formulas that can be formed by repeated applications of the above rules. In other words, the only thing that are well-formed formulas in this language are formulas that can be formed using these four rules right here. So what I'd like to do here is go back to the two new formation rules. The first rule makes reference to what's known as an n-place predicate. That is, it says that if you have an n-place predicate, let's say P or Q, or let's say R or S, then provided there are n names after this predicate, then the result will be a well-formed formula. You can think of n-place predicates in terms of various predicate expressions or relational expressions in English. So for example, X is tall is a one-place predicate in English. And by this, what we mean is that if you were to put a name in the place of X, you would have a complete sentence. So if you have the one-place predicate X is tall, then if you substitute the name John for X, you'd have the sentence John is tall. And so this is a kind of complete unit here. In the case of is taller than Y, what we have here is a two-place predicate. There are two places for names to be slotted in or substituted in. So if we simply said John is taller than, and then we kind of stopped, we wouldn't have this complete unit here. So the two-place predicate is taller than has two spots or two places for subjects or names to go. And so we could say John is taller than Mary, and again, we'd have a complete unit. The same thing would be the case for is standing between X and Y. Here we have a three-place predicate. There are three spots for names or expressions that designate objects to go in. The same thing is the case for predicate logic. We have various n-place predicate terms, and there are the n slots after those n-place predicate terms. So if we have P and we know that P is a three-place predicate, then we have three spots for an n-place for names to go. If Q is a one-place predicate, then one spot. If R is a two-place predicate, then two spots. And if S is, let's say, a five-place predicate, then we have five spots. What the rule says is that we form a well-formed formula provided once we've identified what type of predicate is, if it's a two or one or three-place predicate, provided it has the n terms or n names after that predicate. So if P is a three-place predicate, provided we have three names, then we have a well-formed formula. If Q is a one-place predicate and we have one name, then QD is a well-formed formula. Now, if R is a two-place predicate and we have only one name, where we have this sort of missing spot here, then at least how the rule is formulated, this is not a well-formed formula. And if S is a five-place predicate and we only have two terms, A and let's say A again, then we don't have five names after
the S, and so it is not a well-formed formula. So now I'd like to look at the fourth formation rule because I think it's the most complicated or the one that's most difficult to understand. So I'd like to look at this rule by walking through an example. So the beginning part of the rule states that suppose that P is a well-formed formula in the language of predicate logic, and that formula contains the name A, but it can be any name. So let's take an example. Let's say we have a one-place predicate and it's P, A. Next, let's suppose that Px/A is what results from substituting the variable x for every occurrence of A in P. So what we're saying here is imagine a sort of substitution process where we go about replacing each instance of A with X. So in this particular case, what it would give us is, since we're replacing every instance of A with X, it would give us Px. And this is not a well-formed formula, at least is how we've defined it. Then the rule states that we can put a universal quantifier as well as a variable that we used in the substitution process in front of the result of this substitution, and the result will be a well-formed formula. Or we can put an existential quantifier along with the variable x, which is the one that we use to substitute for the names, and the result will be a well-formed formula in the language of predicate logic. So just to look at our particular example here, Px is what results from replacing A with X. And so we can take this particular formula and place a universal quantifier along with the variable that we used in the substitution process in front of this formula. So A upside down AX PX, and the result is a well-formed formula. Or we could put the existential quantifier in front of this formula, and the result would be a well-formed formula. So this is how you make use of the fourth formation rule to form well-formed formulas that involve the universal quantifier. Let's look at one more example. Suppose we have R, A, B, and we'll suppose that R is a two-place predicate. And since there are two names after R, we have a well-formed formula. So we meet this condition. So if P is a well-formed formula in language of predicate logic and it contains a name. And so we have this well-formed formula. Now suppose that R, Y, B is what results from replacing each instance of B with the variable Y. So this sort of substitution process would give us, what it would give us is R, A, Y. So what we're doing here is replacing each instance of B with a Y. Now, given that we have RAY here, we can place either the universal quantifier in front of it, AY, RAY, and the result will be a well-formed formula. Or we could put the existential quantifier in front of it, RAY, and the result would be a well-formed formula. This is another example how we might make use of this fourth formation rule to form well-formed formulas that involve quantifiers. So it's helpful to finish up this discussion by briefly talking about, or briefly looking at, a variety of well-formed formulas, formulas that are well-formed formulas, and formulas that are not well-formed formulas. So let's start by looking at PA. PA, assuming P is a one-place predicate, since it's followed by a single name, it's a well-formed formula. The name comes to the immediate right rather than the immediate left or above it or below it. In contrast, AP is not a well-formed formula because the name needs to come to the immediate right of the n-place predicate, not to the left or above it or below it or way out in left field. RAB, assuming R is a two-place predicate, is a well-formed formula. It's a two-place predicate followed by two names that come to the immediate right, so it's a well-formed formula. ARB is not a well-formed formula because, again, the names need to come to the immediate right. It has two names, but they're just not to the immediate right. RAA is a two-place predicate with two names to its immediate right. Even though it's the same name, that doesn't disqualify it from being a well-formed formula. It just needs two names to fill the spot. Doesn't matter what names they are. X is not a well-formed formula. One, because it doesn't have any names in it, and how we formulated the rule in this case is that there needs to be names following it rather than, let's say, variables. Not PA and RBA is a well-formed formula. Here we have two well-formed formulas and they're put together using the conjunction rule, whereas not PA, RBA, even though you have the appropriate number of names, it's not put together using the correct propositional rule. Finally, assuming P is a one-place predicate, we can make use of the formation rules to create this particular formula AXPX. We already showed an example of how we said, okay, let's say PA is a well-formed formula, and then we can have this process where we replace A with X, and then we can take what's results from that and put a universal quantifier in front of it, and it would give us AXPX. In contrast, AXPY is not a well-formed formula, because there's no way to make use of this fourth formation rule to have a universal quantifier with a X in front of it, where it's quantifying over, or the result is this PY. To see this, let's say we start with a PA again. Now we want to get this sort of PY here, but here we're at a kind of crossroads. We say, well, the way it looks like to do this is to say, well, we're going to replace every A with Y. And the rule states that if we used Y here, then when we go to place a universal quantifier in front of it, it needs to be this same variable. So it needs to be AY, PY. But that's not AXPY. This has a X variable where when we make use of the rule, it forces us to use this Y right there. So AXPY is not a well-formed formula, but in contrast, AXPX is a well-formed formula. In this video, I plan on introducing predicate logic semantics. I'll need to break up the discussion of predicate logic semantics over a course of a number of videos. So here we'll set the stage by talking about how predicate logic semantics differs from propositional logic semantics and introduce one of the core notions, which is the notion of a model. So the first thing to note is how predicate logic semantics differs from propositional logic semantics. In the case of propositional logic, well-formed formulas are assigned a truth value, T or F, in a sort of two-step process. First, there's an interpretation function. And what this interpretation function does is assign a truth value, T or F, to all of the propositional letters in the language. So if you have an uppercase P or Q or R, it will assign it either a value of true or false, not both and not neither. Next, once we have truth values for the propositional letters, well-formed formulas in the language, conjunctions, conditionals, and so on, are assigned truth values using a valuation function. Essentially, what the valuation function does is take the truth value that's assigned to the propositional letters, and given the type of formula it is, will determine whether or not the entire formula is true or false. The semantics of predicate logic is a little bit more complex in that the elementary symbols that we have don't express complete propositions. They don't express the types of things that can be true or false. Instead, one way of thinking about it is they express parts of propositions. So we need to go about assigning their meaning, the meaning of the symbols of predicate logic in a different way. So what do we need with respect to predicate logic semantics? We need essentially two notions. The first is the notion of a model. And a model is essentially a two-part structure consisting of two things. First, it consists of a domain of discourse, which we'll talk about more in a moment. And it consists of an interpretation function.
Once we have this model in place, we'll also, similar to the language of predicate logic, make use of a valuation function, which will take well-formed formulas and determine whether or not that formula is true or false with respect to that model. So let's talk about the two parts of the model. The first part is the domain of discourse. Now, a domain of discourse is simply a set of items or of things. The domain is either restricted or unrestricted. If it's unrestricted, then the domain consists of anything you want, all the things that could possibly be talked about. Most domains are not unrestricted. Rather, we talk about restricted domains. We talk about specific collections of things. In order to restrict the domain or specify the types of things that we're going to talk about, we can do this in two different ways. First, we can list or name each of the individual items in the domain. So if we want to talk about our favorite movies, we simply just name each of our favorite movies. Another way of talking about or restricting or specifying the domain is to just indicate the property that all of the items in the domain have. So rather than going through each individual item in the domain and naming it or pointing it out or picking it or indexing it, we say all the things that we're talking about have this particular property. So let's look at two examples or a couple examples of the ways we might specify a domain. So if we wanted to talk about 4 people, let's say we wanted to talk about David, Liz, Tech, and Ryan, we could specify the domain that these are the things that we're talking about. This is a collection or set of things by simply naming them all off. We say David, Liz, Tech, and Ryan. So we have the symbol for domain, this D right here, and we simply rattle each of their names off. Another way of kind of putting this is if we wanted to talk about letters A, B, and C, or we wanted to say that we just want to talk about these like dummy objects, they don't really stand for anything, we could simply list them A, B, C, and D. The other way of listing or specifying a domain is, rather than individually naming them, to specify the property that they all the things have. So if we wanted to talk about human beings, we don't want to talk about movies or numbers or shapes or buildings, we only want to talk about, let's say, human beings. Then we simply say that the domain consists of the set of things that have the property of being a human being. Let's talk about the first function of the interpretation function. So the idea here is that the interpretation function, which we designate as I, it looks at each name in the language of predicate logic and then assigns it an object in the domain. So let's say our domain consists of a set of integers, 1, 2, 3, so forth and so on. Now, what the interpretation function does is looks at all of the names in the language. So, you kind of go through all the different ones. And what it will do is pick out one and only one object from the domain that it refers to. So when we say we are going to interpret the name A, we interpret it in terms of some single object in this domain. So we might say the interpretation of A is 1, and the interpretation of B is 2, and the interpretation of C is 3. One thing worth pointing out here is that while every name is interpreted, it's not necessary that a name, it designates or denotes a specific object, that object in the domain cannot be designated or denoted by another name. So it's helpful to think of intuitively, we might say that, an individual, let's say David, an individual name David refers to, let's say, me. My name is David Agler, and so it kind of picks me out. But I also have other names, nicknames. And so if here's my nickname, it refers to, again, the same individual, David. So here we have two different names, but they refer to the same object, which is me. The same thing is the case with respect to predicate logic. We can say that, let's say, the interpretation of A refers to the number 1. It also might be the case that the interpretation of, let's say, E also refers to number 1. So once a name has been interpreted in terms of an object in the domain, it's open, or it's at least possible, that the interpretation function will also assign other names that same object. Let's look at the second function of an interpretation. The second function of an interpretation is to assign or give the meaning of n-place predicates. And the definition of it simply says that we take that n-place predicate and it's interpreted in terms of a set of n tuples. Now there's quite a bit of jargon there, so I'm going to try to break this idea down into a couple parts. So let's look first at the scenario where R is a one-place predicate. What an interpretation function would do here is assign it a set of objects from the domain. So let's let the domain consist of this set of numbers 1, 2, 3, 4, 5, and 6. So what an interpretation function would do here, the interpretation of R, would just pick out a collection or group or set of objects that are drawn from the domain. So we might say the interpretation of R is simply the numbers 2, 4, and 6. Or we can think of it as saying R picks out the even numbers from this collection of numbers 1 through 6. And you can think about this in other examples. If we have, let's say, the domain of people, living human people. And we might have a one-place predicate that stands for something like is tall. And so what the interpretation of is tall would be is simply the collection of people from the domain that have the property of being tall. So it would pick out all of the people who are tall people. It would just kind of go through all of the items in this domain here and select the tall ones. If R is a two-place predicate, what type of thing does it pick out? What type of set? So if R is a two-place predicate, what the interpretation function does is assign it a set of ordered pairs from the domain or over the domain. A set of ordered pairs, or rather an ordered pair, is a sequence of two objects. And we can symbolize an ordered pair using angled brackets. So if we had a ordered pair, or kind of two objects that are put into an arrangement or sequence where the order is important, and A is the first object and B is the second object, we could express this, that A and B are an ordered pair, by writing this left angled bracket A and B, and then a right angled bracket. So this expresses that A and B are an ordered pair. Let's look at this in a little bit more detail. So let's talk a little bit about what an ordered pair is in some slightly more detail. So we can think about an ordered pair as a special kind of set where the order of the items is important or significant or means something. So one way of thinking about an ordered pair is in contrast just to a regular set or collection. So let's say we're talking about two people, John and Tech. And we'll represent that as lowercase j and Tech as j. And so let's kind of draw John and Tech here. Here is John, and here is Tech right here. So here's John with the J, and here's Tech with the T. Now, if we're just talking about these individuals as being part of a collection, and we don't really care about their arrangement. We just want to talk that they're a member of the group of the things that we're talking about. Then we can express this set or this collection simply as J or T, or we can express it as T or J. So here we're expressing this collection, but both of these collections are saying the same thing. We're just talking about all of the items that are found in this set, and the order in which they occur or the number of times in which they occur also doesn't really matter. And so they're equal to each other. But let's say we wanted to talk about a set of individuals where their placement or their arrangement or their is important. We want to talk about the collection of individuals, or where the first individual has a particular type of relationship to the second individual. And so one example is we can think of the taller than relationship. We can think of a set where there are two individuals and the first individual in the set is taller than the second individual. So in this case, when we look at John and Tech, we see that John here, he's taller than Tech. And we want to be able to express this. And so we write J, the first individual, is taller than the second individual. So we express this relationship that John and Tech have in terms of each other as an ordered pair. The first individual is taller than the second individual. And this is not identical to the order, in contrast to the sets that we looked at up here. This is not identical to the ordered pair where the first individual is Tech and the second individual is John. So all this ordered pair is a special kind of set where the order or placement of the objects in the set or sequence is significant or plays an important or informative role. Going back to our discussion or the statement of what an interpretation function does, we see that the interpretation function, as it's stated, assigns a set of n tuples from or over the domain to n-place predicate terms. And we haven't really explained what an n tuple is quite yet. So it's helpful to use what we talked about before to kind of trigger an understanding of what an n tuple is. So we can talk about single objects in a set. So A, B, C, D. These single objects are known as one tuples. We can talk about ordered pairs, a kind of set where the sequence or order matters. So A, B, as well as, let's say, C, D, this ordered pair. These ordered pairs here are also referred to as two tuples. They have two items. They're an ordered arrangement or ordered set where there are two elements in this ordering. And you can think of, kind of go on and on with respect to this. You could say, well, we can imagine a set that is ordered, and that set has three elements. So A, B, and C. And this three element ordered sequence is a three tuple. And you can go on and on and on concerning this. And so you can say that an ordered sequence of n elements, where you just have some number of ordered elements, this is an n tuple. So however many it has, that will kind of characterize the n in n tuple. So what the interpretation function does is it assigns a set of n tuples from items in the domain to n-place predicate terms. And so if we interpret something like R, and R is a two-place predicate, what we'll expect to see is a set of things where each of the items in this set, given that R is a two-place predicate, is a two-tuple. And so we might see A, B, as well as, let's say, B, the ordered pair B, A, and onward and onward. But each of the items in the set, given that R is a two-place predicate, will be a two-tuple. So let's look at an example of this. Let's suppose that G is a two-place predicate. And it might be helpful in understanding this, the kind of first go around, is to understand it in terms of an English two-place predicate. Let's say it stands for greater than. So what the interpretation function will do is assign it a set of two tuples over D. So the elements in these two tuples will be found in the domain. Now let's specify a domain. To keep things simple, let's say we have a domain and it consists of the numbers 1, 2, and 3. So the interpretation function will kind of assign names to items in the domain, but what we're interested in unpacking here is how the interpretation function behaves with respect to this two-place predicate G. So what the interpretation function will do here is pick out a set that has elements that are two tuples where the first number is greater than the second number. And so if we look through this 1, 2, 3, we're going to say that the interpretation of G is going to pick out ordered pairs or two tuples where the first item is greater than the second item. And so we see that 3 is greater than 2, 3 is greater than 1, and 2 is greater than 1. So it's going through this domain, going through each one of the objects in the domain, and it selects a pair of things where the first item is greater than the second one. So let's put all of the things that we've talked about together and apply it to a particular example. So we're going to take the whole notion of a model with respect to the domain of discourse and the two roles of the interpretation function and look at a specific example. So let's take the example of 3 circles. And just to make things easier, to kind of refer to them in an easier way, we're going to label these 3 circles 1, 2, and 3. So our domain consists of these 3 circles and nothing else. The next thing is the interpretation function's role in going through the names of the language of predicate logic and assigning them an object in the domain. And so let's take the name A and say it refers to the blue circle, or what we've designated as the number 1 here. So we say the interpretation of A here, it refers to the blue circle. Next, we need to interpret B. And we say that the interpretation of B here, what does it refer to? Well, it refers to, from the domain, the red circle. Finally, the interpretation of C, well, what does it refer to? Well, it refers to this green circle. Now, one of the things is that the interpretation function goes through all of the names of the language of predicate logic and assigns it an object in the domain. And since our language has not just the names A, B, and C, what is often done when required is to add some kind of part where it says, and something like, and all other names, and you just kind of designate some object in the domain. So you say the interpretation of, let's say, D onward, all those refer to, let's say, the green circle. A lot of times this is left out because it won't play a role in evaluating different formulas, but this is part of the definition of the interpretation function. Now that we have an interpretation of all the names, the next thing the interpretation function does is assign sets of n tuples to the n-place predicate terms. So it's going to interpret the meaning of those n-place predicate terms in terms of a set of n tuples drawn from or over the domain. So let's look at this particular example that we have here. So let's take 4 one-place predicate terms and then 1 two-place predicate term. So what the interpretation function is going to do is assign these terms some meaning. So let's say this one-place predicate term C, it stands for is a circle. We designate that each one of the items from our domain is in the interpretation of C. When we go to interpret B, let's say B stands for something like is blue, then it's going to pick out the items from the domain that are, let's say, blue. And so since circle 1 is blue, it selects in its interpretation just this first circle right here. If R stands for is red, then it'll pick out the red circle. If G stands for is green, then it'll pick out the green circle. Now, the last interpretation is the interpretation of the two-place predicate term. And just for heuristic purposes, let's say L stands for is larger than. And so what this interpretation function will do is it'll pick out ordered pairs or a set of two tuples where the first object from the domain is larger than the second object. What this interpretation is larger than does is it selects objects where the first circle is larger than the second circle. So since 3 is larger than 2, then it selects this ordered pair where the first object is larger than the second one. We also note that 3 is larger than 1. This third circle right here is larger than the first one. So it's going to pick out this ordered pair where the first circle is larger than the second circle. And since this second circle right here, this red circle right here is larger than the first circle, it's going to pick out this ordered pair where circle 2 is larger than circle 1. So this is a complete example of a model. We have 1, the domain of discourse, the items of which we're going to talk about, and then we have our interpretation function, the other main part of a model. With respect to the interpretation function, we have the interpretation of names, which simply selects objects, single objects from the domain. And then we have our interpretation of all the predicate terms, which selects sets of n tuples over the domain. So it's only going to pick objects that are found in the domain. It won't pick anything else. So just to conclude, the semantics of the language of predicate logic consists of two parts. The first part is what has been covered in this video. This is the notion of a model. And the model consists of two parts, which is this domain of discourse and the interpretation function. In the next video, what we'll look at is the other part of the semantics of predicate logic, and this is the valuation function. What the valuation function will essentially do is take formulas from the language of predicate logic and using the model, so with respect to this model, it will assign these formulas truth values, true or false. And it's going to do that by using or utilizing this model. So this notion of a model is important because if you don't have a clear grasp of what a model is or how to construct one, this valuation function won't mean anything to you because the valuation function only works relative to this model. So in this video, I'll continue the discussion of predicate logic semantics by talking about the valuation function for predicate logic semantics. In particular, we'll look at the valuation function for non-quantified formulas. And in another video, I'll take a look at the valuation function for quantified formulas. So just a quick review, the semantics of predicate logic are characterized in terms of two parts. The first part is known as a model, which consists of a domain of discourse and an interpretation function. This video will focus on the valuation function. So let's look at the definition of a valuation function in the language of predicate logic. Here we won't present the full definition, and so we'll present part of it. And in this video, we'll only focus on a certain aspect of this definition. So the definition of a valuation function is that relative to a model, so a domain of discourse, as well as an interpretation function, what a valuation is a type of function that assigns a truth value, T or F, one and only one, to each predicate logic well-formed formula. And it does this in a way specified in these kind of three rules down here that we'll kind of go through. Here we'll only focus on the first two, but the valuation function is a way of assigning truth values, T or F, to formulas given the way that's going to be specified by these three rules. So the first case is a predicate logic formula where the predicate logic formula consists of an n-place predicate term followed by n names. And it says that this type of formula, a predicate, an n-place predicate followed by n terms, is true if and only if our interpretation of A is in the interpretation of R. That is, the interpretation of A is in the interpretation of R. Now, if this doesn't quite make sense right now, that's okay, because I'll kind of go through it in a little bit more detail, and we'll go through a number of examples to help illustrate it. The other thing to take a look at are when it's a predicate logic well-formed formula, but the main operator is a truth functional operator. So negation or the conjunctions or disjunctions, conditionals and biconditionals. Here, there's nothing new to really learn. I'll put a link in the description below if you're unfamiliar with this, but how these formulas are determined in the same way that a propositional logic valuation function is determined. So for example, in the case of conjunctions here, the conjunction P and Q is going to be true if and only if P is true, so the valuation of P is true, and valuation of Q is also true. So it's determined in the standard way that propositional logic formulas are determined. So I mentioned our definition here was going to be partial. This is because I won't specify quite yet how the truth values of quantified formulas are determined. I'll leave this for a later video. So I'm going to take a look at the first valuation function once again. That is how we go about determining the truth value of n-place predicates followed by n names. Now I want to just sort of state this rule again, and then we'll look at some examples that will help illustrate this. So what this rule states is that the truth values T or F are assigned to non-quantified formula. And by this, I just mean the n-place predicates followed by n names. And it's determined in the following way. So we have a closed, well-formed formula consisting of a predicate R followed by the appropriate numbers of A, appropriate number of names A. And this type of formula is true if and only if, as we stated, the interpretation of A is in the interpretation of R. So the interpretation of A is in the interpretation of R. Now let's state this with a couple examples, and then we'll look through some more detailed examples. So what we're saying here is that a formula like HA, where H is a one-place predicate followed by one name, this particular formula is true if and only if the interpretation of A, that is the interpretation of A, is in the interpretation of H. So you can write the interpretation of A is a member of this set picked out by the interpretation of H. Similarly, LAB is true if L is a two-place predicate, it's followed by two names here, if and only if the interpretation of A and B is in the interpretation of L. That is, only if the ordered pair is found in the interpretation of L. So now let's look at some more detailed examples now that we've kind of fleshed out this definition just slightly. Okay, what we have here is a model, and what I'd like to do is go through a number of formulas and talk through how the truth value of these formulas are determined. So let's take a model where the domain consists of 3 circles, and for ease of convenience, let's refer to these circles as 1, 2, and 3, where 1 is the blue circle, 2 is the red circle, and 3 is the green circle. The model not only consists of this domain of discourse, but it also consists of an interpretation of the names as well as the predicates found in the language. So let's let A refer to the blue circle or circle 1, B refer to the red circle or circle 2, and C refer to the green circle or circle 3. In addition, let's talk about 2 predicate terms. First, we'll look at a one-place predicate, let's say G. Let's say, intuitively, we can think of this as the G picks out is green, or anything that's green, and L, which will be a 2-place predicate, and it'll pick out a ordered pair or things in a certain type of relationship where the first object is larger than the second object. So we see that this
interpretation of L picks out first this sort of ordered pair where circle 3 is larger than circle 2. It also picks out a ordered pair where circle 3 is larger than circle 1. And finally, it picks out an ordered pair where 2 is larger than circle 1. Okay, now that we have that in place, let's go through and look at different non-quantified formulas and talk about how we can determine the truth value given this model. So let's start with GA. Here's this predicate logic formula. It's a one-place predicate followed by one name. Now let's talk about how we go about determining this. So we have GA, and what we have to ask ourselves is the interpretation of A in the interpretation of G? And so is the object picked out by the interpretation of A in the interpretation of G, in the set picked out by the interpretation of G? So let's see, A refers to the number 1 here, or the blue circle, and G refers to all the green things in the domain. So it only has the green circle, or circle 3. So what we see is that the object picked out by the interpretation of A is not found in the interpretation of G. That is, if A just refers to the blue circle and G picks out the green things, we see that the blue circle is not in the collection picked out by the green things. And so what we see is that no. And given that the interpretation of A, that is the blue circle, is not found in the interpretation of G, which is the green things, we have to say that the valuation of GA is false. Let's look at another example. How about GC? To answer this, we say, is the interpretation of C in a member of the collection picked out by the interpretation of G? So what does the interpretation of C refer to? Well, what it refers to is the green circle, or circle 3. And is this in the collection? Is 3, or the green circle, found in the collection picked out by the interpretation of G? And yes, the green circle is in this collection of green things. And so we would say, yes, GC is true. How about the LAB? Here we have L, which is a two-place predicate followed by two names. And let's go about trying to determine whether or not this particular formula is true or false. So what we are doing here is seeing that is the ordered pair where the first item is picked out by the interpretation of A and the second object is picked out by the interpretation of B. Is this ordered pair found within the interpretation of L? So if we look, we see that A, the interpretation of A, picks out number 1, or the green circle, and B picks out the red circle. So we have first the green circle, then the red circle in this ordered pair, or first 1 and then 2. So is this ordered pair found in the interpretation of L? So we look through the interpretation of L and we see 3, 2, 3, 1, 2, 1. We don't see 1, 2. So no, since the interpretation of A and B is this ordered pair of the blue circle and red circle, or 1 and 2, and 1 and 2, this ordered pair is not found in the interpretation of L, the truth value of LAB is false, because it is only true if and only if 1 and 2 are found in the interpretation of L. How about LCB? Again, this is a two-place predicate term, L followed by two names. So it's a well-formed formula. And let's go about trying to determine if it's true or false. So what we're going to do is look to see if the ordered pair, where the first item is picked out by the interpretation of C and the second object is the interpretation of B, is this found in the interpretation of L? So is the ordered pair consisting of 3 as well as 2, that is where the first item is 3 and the second item is 2, is this found in the set of ordered pairs picked out by the interpretation of L? And what we see is, yes, since the interpretation of C and interpretation of B is this 3, 2, this ordered pair 3, 2, and since this is in the set that's picked out by the interpretation of L, the truth value of LCB is true. So this video should have given you at least an introduction to determining the truth value of non-quantified formulas in the language of predicate logic. And in the next video, what we'll do is look at quantified formulas. These are formulas where the main operator is the universal quantifier or the existential quantifier. And we'll talk through how to determine the truth value of those quantified formulas. In this video, I want to look at how the valuation function plays a role for assigning truth values to quantified formulas. There's some complexity associated with this issue, but I'm going to put that to the side and instead focus on how to simply look at these quantified formulas and with reference to a model, determine whether or not that formula is true or false. Perhaps in a later video, I'll talk about some of the problems with this approach and how to overcome those problems. But here I just want to lay down the basics as simply as possible. The first thing to note is what the valuation function does with respect to quantified well-formed formulas. What it does is take formulas as input, formulas like AX, PX, that is the universally quantified X, PX, or existential X, RXA as input, and then what it will do is determine whether or not that formula is true or false. So it takes a formula like this, the valuation function does its work, and it will deliver a truth value, T or F, not both, but not neither. Another thing to note with respect to the valuation function is it always determines the truth value of these formulas relative to a model. It's important to take note of this because some well-formed formulas might be true in one model or some models, and they might be false in others. So the simple way of thinking about how the valuation function operates on these quantified formulas is to think that universally quantified XPX, a formula like this, says that everything is P in the model. That is, it will look through, the valuation function will look through the model and try to determine whether or not every item in the domain is in the interpretation of P. So we can think about this upside down AX as saying all, for every single one. The existential quantifier, the EXPX right here, in contrast says at least one thing in the model is in the interpretation of P. So we can understand the existential quantifier as saying at least one. And we can use this information to determine the truth value of these formulas. We'll look at the formula here, check to see if everything in the model is in the interpretation of P, and if it is, then this particular formula is true. If it isn't, then the universally quantified XPX is false. Similarly, what we'll do is if we have an existentially quantified expression right here, we'll look at the model, again, we'll look at the domain of discourse and the interpretation, and then we'll look to see if any items from the model are in the interpretation of P. And if they are, then the formula is true. If there isn't, then the formula is false. So let's take a look at some simple examples. First, we start with our domain of discourse. We start with our model right here, which consists of a domain of discourse and a interpretation of the names A, B, and C, as well as the predicates in the language. Our domain consists of three numbers, 1, 2, and 3. Each of those numbers are named in terms of A, B, and C. We have an interpretation of a one-place predicate E, which we can think of as sort of expressing evens. We have an interpretation of O, which picks out 1 and 3. We can think of this as expressing odds. We have an interpretation of N, which picks out all of the items in the domain. We can think of this as saying, okay, all the numbers in the domain. And we have an interpretation of S. S can refer to anything that doesn't pick out any of the items in the domain. So let's just say it's the unicorns, just if you need. With this information, we can go about determining the truth value of various quantified formulas. So let's take AXEX, that is the universally quantified XEX. What this says is that every item in the model is in the interpretation of E. And so to see if this is true, we look to see if every item in the model is in the interpretation of E. And what we find is that this is not the case. When we look at the domain of discourse, we see that it consists of numbers 1, 2, and 3. But when we look in the interpretation of E, we see it only picks out the evens, that is number 2. So there is at least one item that is not in the evens, which is either 1 or 3, and so AX, EX is false. Next, let's look at AX, NX, that is the valuation function, how it operates on a universally quantified X, NX. This says that every item in the model is in the interpretation of X. For all X, X is N. When we look at the domain, we see it consists of numbers 1, 2, and 3. And when we look in the interpretation of N, we see it consists of numbers 1, 2, and 3. And so every item in the domain is N, that is in the interpretation of N. So the valuation for all X and X is true. Next, let's look at the expression EX, OX, that is the existentially quantified X, OX. What this says is at least one item in the domain is in the interpretation of O. We see that in the domain, there's 1, 2, and 3. In the interpretation of O, there's 1 and 3. And so there's at least one item in the model or in the domain that is in the interpretation of O. You only need one for this to be true, and it comes out as true. But we have 2 items right here, which is sufficient for making this expression true. Next, let's look at EXSX. That is, there is at least one item X that is in the interpretation of S. So in order to check to see if this is true or false, we simply look to see if there is at least one item in the domain that is in the interpretation of S, and we see that there is not. In the domain of numbers here, 1, 2, and 3, we see that there isn't any items in this interpretation of S or unicorns. So the truth value of EXSX is false. Here we've taken the original model that we've looked at and simplified it slightly and added a 2-place predicate G, where G we can understand as the greater than relationship. And our interpretation of G picks out a set of ordered pairs where the first item in the pair is greater than the second item in the pair. We want to evaluate the expression AX-GXA. That is the universally quantified X, GXA. We can think about AX-GXA as expressing kind of 2 different statements. One of the statements it might express is that for every item in the domain, which consists of numbers 1, 2, and 3, that item is in the greater than relationship with the item picked out by A. In other words, where we let X stand for any item in the domain, 1, 2, and 3, this universally quantified X, GXA says that all of these statements are true. That is, 1 is greater than 1, 2 is greater than 1, and 3 is greater than 1. So it's expressing this complicated statement of 1 is greater than 1, and 2 is greater than 1, and 3 is greater than 1. And so in order for the universally quantified expression to be true, all 3 of these statements right here need to be true. Another way of thinking about the universally quantified X, GXA is as it saying that a certain set of ordered pairs or a certain group of ordered pairs are in the interpretation of G. What AX-GXA states is that the ordered pair of X1, where X is a variable for any item in the domain, is found or is a member of the interpretation of G. Since X is a variable for any item in the domain, we say that 1 and 1 is in the interpretation of G, that 2 and 1 is in the interpretation of G,
and 3 and 1 is in the interpretation of G. So what it's asserting is that all of these statements right here are true. Now what we see is that for at least one of these statements, it is false. That is, 1 and 1, the ordered pair 1 and 1 is not in the interpretation of G. We see that it's not found here. And if we understand it in terms of these component statements, we see that 1 is greater than 1 is not true. And in order for this, for all x, gxa to be true, it needs to be true of each one of these statements. And since it's false for 1, this is false for 1, the expression ax, gxa is false. The next formula that we'll take a look at is the universally quantified x, gxx. Here, what we're saying is that for any item in the domain, there is an ordered pair xx, where x is any item in the domain. This will be found in the interpretation of G. And so we go through the domain and substitute items from the domain and check to see if it is in the interpretation of G. And we can quickly see that when we substitute 1 for the variable x, we see that this is not found in the interpretation of G. And since it's not found in the interpretation of G, for all x, gxx is false. More intuitively, if for all x, gxx simply says every number is greater than itself, we can quickly look at the interpretation of G and say, in this particular model, there are a bunch of numbers where those numbers aren't greater than themselves. And in fact, no number is greater than itself. Next, let's look at the expression, there exists an x or existential x, gxb. Now this particular expression will be true provided there is a ordered pair x2 in the interpretation of G. That is, there's a number that is greater than the number picked out by B, or there's a number greater than 2. And what we can find is that for at least one number, at least one item in the domain, that number is greater than 2, and it is found in the interpretation of G. And so this expression, there exists an x or at least one x, gxb, is true. Lastly, let's look at the expression, there exists an x or for at least one x, gbx. So this is different than the prior formula that we looked at. The previous formula that we looked at was there exists an x and gxb. So this one is saying that there's at least one item in the domain, and that item is greater than the number picked out by B. Here we have there is at least one item x, and B is greater than that item. So what we're looking for here is an ordered pair, since B picks out 2, that is greater than some item in the domain, and that ordered pair is found in the interpretation of G. It is found in this interpretation. And there is at least one item in the domain that 2 is greater than, and that is 1. So if we let x stand for 1, then what we have here is that this ordered pair is found in the interpretation of G. And so this expression for there exists an x, gbx is true. In other words, if you understand ex, gbx is saying 2 is greater than some number or at least one number, we can look at the domain and look at the interpretation of G and see that there is at least one number that 2 is greater than, and that number is 1. And so we can use that information to say that this expression that we're looking at is true. In this video, what I want to look at is how to translate formulas in the language of predicate logic into English.
And you can use this kind of information to translate the other way, from English into the language of formal logic. So the first thing that we need with respect to any translation is a translation key. And this translation key has three components. The first thing that it has is a domain of discourse. So we just need to make sure we have a model in place, the formal model, and we need to tie this into the sort of set of things that we're talking about. The next thing that we need is an interpretation of all predicate logic names into English names. That is, we need a way of translating, let's say, lowercase a, b, c, d into proper names or terms that pick out single objects in the English language. And then the final thing we need is an interpretation or a sort of translation method for translating n-place predicates into English predicates. So in predicate logic, what we have are these uppercase letters R, P, Q, and we need a way to translate those R, P, and Q into English predicates like is happy, is tall, is greater than. So let's look at an example of a translation key. So we have the domain of discourse, the living human beings or the things that we're talking about. And then we have a way of translating individual names from predicate logic into English. So we'll let A stand for the English name Annie or proper name Annie. It doesn't have to be English. The lowercase j from predicate logic to John and F to Frank. And then we have a way of translating n-place predicate expressions into the desired language that we want to talk about, whether it's English or some other language. So TXY, where this two-place predicate right here, we'll say that it stands for the expression is taller than, and HX, this uppercase H followed by X, is the English predicate is happy. So what we can do with the translation key is translate various English sentences into this language of predicate logic. So if we have a bunch of English sentences, we can take this translation key and turn English sentences into formal expressions in predicate logic. We can also do the reverse. We can take formulas in predicate logic and translate them into English sentences. If we let phi and psi stand for any predicate logic well-formed formulas, not phi or phi and psi, we can just translate these like we would for propositional logic. And I'll put a link in the video below as to how to do this in case you forget how to translate something like phi, right arrow, psi. So I won't elaborate here. Instead, what I want to focus on for this video is how we translate formulas that are unique to predicate logic. That is, n-place predicate terms followed by n names or quantified expressions right here. Let's look at an example involving n-place predicate well-formed formulas. So we won't look at quantified expressions quite yet. Here we have our translation key over here, which specifies the domain and translates names from predicate logic into English names or just proper names in general. We have the n-place predicates in the language of predicate logic and its translation into natural language predicates. Translating n-place predicate well-formed formulas is a pretty straightforward process. The only thing that really needs to occur is a sort of reversal of the order. So if we have HA right here, we know that A stands for Annie and H stands for is happy. So if we were to translate the expression right here in just a straightforward manner, we'd have something like is happy Annie. But this is not how people talk. This is not a kind of grammatical construction right here. Instead, what we'll need to do is flip the name and the predicate, sort of swap their roles right here. This is because in the language of predicate logic, the predicate comes first and it's followed by any names or terms. Whereas, at least in English, it's a little bit more natural to start with the name and then ascribe various properties or predicate certain things about it. So HA gets translated as Annie is happy. Next, let's look at HJ.
we know that J stands for John, and H again stands for is happy. And so we can translate HJ as John is happy. How about TAJ? This is a little bit more complicated, but it isn't too terrible to deal with. Since we have this two-place predicate term T, and T stands for is taller than, we have two blanks to sort of fill in subjects. We have blank is taller than blank. And so what we'll do is take A and say A is taller than B. So this first, A is taller than J, excuse me. So this first item here is taller than the second item. And since we have our translation key, we can swap out or translate A for Annie and J for, what do we have here? We have John. And so what this gives us is the sort of natural expression, Annie is taller than John. So we translate TAJ as Annie is taller than John. In the case of TJF, we can use a similar process. Here we have John is taller than F, and F stands for Frank. So John is taller than Frank. In this next example, instead of TJF, we have TFJ. And so the order of the names are simply reversed. Here we have Frank is taller than John. So this TFJ stands for Frank is taller than John. In this last expression, we have this not and this not and has TJF and TFJ. So we already know that TJF stands for John is taller than Frank, and TFJ stands for Frank is taller than John. So all we need to do is take these two expressions from 4 and 5, which is John is taller than Frank and Frank is taller than John, and put it in this propositional logic construction or translation. So this not and gets translated as, well, at least one way. It is not both the case that, and then we kind of plug in our two expressions here. It's not both the case that John is taller than Frank and Frank is taller than John. So we would put this into English. Let's look at some quantified translation. We can understand the universal quantifier as standing for expressions in English like for every x or all x or each and every x or for each x, and the existential quantifier as for some x, there exists an x or at least one. So in other words, universal quantifier all and existential quantifier some. That is, whenever we see universal quantifier, we can kind of swap out this quantifier for all. And whenever we see the existential quantifier, we can swap that expression out and let it stand for some. Let's look at some examples. So the first one, we have EX or existential quantifier X, HX. We know that H stands for the property is happy. And we said that we're going to let the EX stand for some. But one way we might do this is to translate this particular expression into something sort of pseudo-English. So what this existential X, HX says is there's at least one item in the domain of discourse or in the model that is in the interpretation of H. But since no one talks like this, we can sort of translate this into something a little bit more natural by saying at least one living human being, so items relative to this domain right here, is happy. That is, we're translating this H as is happy, and we're saying at least one item in the domain, which is living human beings, is happy.
But still, no one really kind of talks like this either. So the natural way to translate EXHX is someone is happy. Well, what about AXHX? That is the universally quantified XHX. Letting AX stands for every or all, we can translate this as every X or all X's or any item in the domain is H. No one really talks like this again. So what is it essentially saying is that everyone, since we're talking about human beings or people, all of those things have the property of being happy. So we can translate AXHX, this universally quantified AXHX, as everyone or everything in the domain has the property of being happy. This last expression I'll cover in some more detail in a later video, but I just want to kind of give you a heads up about it. What we have here is a formula where the quantifiers are overlapping. That is, the universal quantifier has the existentially quantified expression within its scope. We can understand this expression AXEYTXY as stating for every X, so for any item in the domain of discourse, there is some Y, there is some item in the domain of discourse such that the X, that every X, is taller than that some Y. In other words, what this AXEYTXY is saying is that everyone is taller than someone. In other words, what it's saying is that every item in this collection of human beings, living human beings, if we go through the domain and we pick out any item that we want, we can always find some item, which is again in the domain, which is another living human being, where the first item is taller than the second item. That is, where the first person is taller than the second one. In other words, what it's saying is everyone is taller than someone. Now, this might sound strange because it's a weird thing to say, because we would say, well, what about the shortest person? This sentence right here has to be false because the shortest person isn't taller than anyone. But the point here is not to translate only true expressions. Our goal is just to look at various predicate logic formulas and figure out the best way to translate them into English. And once we've done this, we have the tools required to do the other way around. That is, if given an expression, everyone is taller than someone, we could see how we might translate this back into the language of predicate logic. Now, again, if this last translation wasn't immediately clear, I plan on looking at just how to translate formulas that have overlapping quantifiers in a later video. In this short video, I want to introduce predicate logic truth trees. So the way of introducing predicate logic truth trees is to go back and talk a little bit about propositional logic truth trees and sort of compare and contrast a little bit. So propositional logic truth trees, what we can do is for any propositional logic argument, we can apply the truth tree method and determine if the argument is deductively valid or invalid. More exactly, a truth tree method for propositional logic allows us to mechanically determine if a formula is semantically entailed by another set of formulas. So what it allows us to do is determine whether or not Z is entailed by P, Q, and R, just to use an example, or if Z is not entailed by these formulas. Now, all this is well and good, but one of the problems with propositional logic truth trees is rooted in the language of propositional logic itself. That is, we can't take all the arguments that we intuitively think are valid and translate them into propositional logic. And if we can't do this, then we can't make use of the propositional logic truth tree method. That is, we can only use the method if we can get the argument into the language of propositional logic. But what we saw is there's a whole host of arguments, either in English or other formal languages, that we can't kind of reduce down to propositional logic. What we need is a more expressive language to capture all of these different arguments. So one example of a more expressive language is the language of predicate logic. And fortunately for us, we can adapt parts of the truth tree method to this language of propositional logic. Now, the good of this is that the truth tree method will work for predicate logic. That is, we can apply some of the techniques, and for certain arguments in predicate logic, the truth tree will work perfectly fine. To simplify things quite a bit, the bad of this is that it won't work for the entirety of the language. That is, there's some arguments in expressing the language of predicate logic where our truth tree method will just kind of repeat endlessly, and it won't give us a algorithmic way of determining whether or not the argument is an entailment or non-entailment. So in order to make use of the truth tree method for predicate logic, one thing that you'll need to know how to do is make use of the decomposition rules from propositional logic. In other words, in order to make use of the truth tree method for predicate logic, which we'll abbreviate as RL, you'll already need to know how to make use of the truth tree method for propositional logic. I'll put a couple links in the description below in case you want to refresh yourself on how to use the truth tree method for propositional logic. One of the things that you'll need to know how to do from propositional logic is that make use of the various truth tree decomposition rules. And what we'll do for predicate logic is we'll import all of the truth tree decomposition rules from propositional logic. So we'll make use of all of these decomposition rules. In addition, we'll make use of 4 new additional decomposition rules. These will apply specifically to formulas of predicate logic. So what I'd like to do in the remainder of this video is to talk about the notation of these decomposition rules and talk about the type of formula that each decomposition rule applies to. In this video, I won't go through how to make use of these decomposition rules. I just want you to be comfortable with identifying a formula and knowing which decomposition rule you should apply. So the first decomposition rule worth looking at is negated existential decomposition. And this is a rule that we'll abbreviate with not existential D. And negated existential decomposition applies to negated existentially quantified well-formed formulas. That is, formulas where the main operator is the negation and the operator with the next most amount of scope is the existential quantifier. So the idea here is if you saw a formula that is a negated existentially quantified formula, then you would apply the corresponding decomposition rule, which is negated existential decomposition. The next rule to take a look at is negated universal decomposition, which we abbreviate with not upside down AD, that is not universal D. And this decomposition rule applies to negated universally quantified well-formed formulas. That is, formulas where the main operator is the negation and the operator with the next most amount of scope is the universal quantifier. So again, if you saw a formula of this form, you would apply the negated universal decomposition rule. Next, we have the existential decomposition, abbreviated as backwards ED, and this applies to existentially quantified well-formed formulas. That is, formulas where the main operator is the existential quantifier. And so again, if you saw a formula where the main operator is the existential quantifier, the corresponding truth tree rule you would apply is existential decomposition. The final predicate logic decomposition rule is universal decomposition. And by now you might be seeing a pattern. This universal decomposition, abbreviated as upside down A for the universal quantifier, applies to universally quantified well-formed formulas. That is, formulas where the main operator is the upside down A. So again, if you saw a formula where the main operator is the universal quantifier, you would apply the corresponding decomposition rule, which is the universal decomposition rule. In this video, I want to discuss the first 2 predicate logic decomposition rules. And these are negated existential decomposition and negated universal decomposition. So as a kind of preliminary, let's let this symbol for phi right here stand for any predicate logic well-formed formula, including n place predicates followed by n terms.
So this would include statements like, PX if P was a one-place predicate, or RXY if R was a two-place predicate. So the rule for negated existential decomposition, which is the decomposition rule that applies to formulas where the main operator is the negation and the operator with the next most amount of scope is the existential quantifier, is as follows. If we have a negated existentially quantified formula, we can decompose it in terms of a universally quantified formula that ranges over phi. So this formula right here, phi, is down here, except for now, and the negation that was originally on the outside right here is now on the inside of the universal quantifier. The idea here is we're replacing or decomposing this negated existentially quantified expression with a universally quantified expression that ranges over the negated phi. So we're replacing this formula right here with one that's equivalent to it. When I say equivalent to it, I mean these two formulas are true and false under the same conditions. That is, for example, then, a sort of application of this rule is if we had not EX, PX, we could decompose this formula right here, that is, represent the conditions under which it's true in terms of an equivalent formula, which is AX not PX. And we would indicate that we applied negated existential decomposition to, let's say, line 1 here, using the negated existential decomposition rule. One more example. Let's say we had not EX RX X. So we have a two-place predicate R. Applying negated existential decomposition would give us a X not R XX. So essentially all we're doing with negated existential decomposition is replacing one formula with one that's equivalent to it. But we're just simply swapping out this not EX with this AX negation. So we're leaving this RXX alone, but we're just replacing this not EX with AX negation. The second predicate logic decomposition rule is negated universal decomposition. Again, we'll let phi, this little symbol phi right here, stand for any predicate logic well-formed formula, including n-place predicates followed by n terms. So again, this is a slight simplification, but it'll work for explaining the rule. So negated universal decomposition applies to formulas where the main operator is the negation and the operator with the next most amount of scope is the universal quantifier. So in the case of negated universal decomposition, we represent the condition under which this particular formula is true in terms of an existentially quantified formula that ranges over the negation of phi. So again, we're replacing the negated universally quantified formula here with one that is its equivalent to. These two things say the same thing in a sense, but they say it in a different way. So to give you one example, let's say we had not AX, not PX. Applying negated universal decomposition to this formula, so not AD, would give us EX not PX. So all we're doing right here is replacing this negated universal quantifier with a existential quantifier. We're leaving this not PX alone, and we're replacing the negated universal quantifier with the existential quantifier that now ranges over the negation of not PX. So let's look at an example where both negated universal decomposition and negated existential decomposition are applied. So suppose we start with two formulas in our tree. That is, we have not AXPX and not EYRYY. So these are the propositions we are going to evaluate the truth conditions of using our tree method. Since we see that line 1 is a negated universally quantified formula, we can apply negated universal decomposition to that line 1. And so we decompose line 1 using the negated universal decomposition rule. And this gives us EX not PX. Again, we're simply replacing this not AX with EX negation right here. And we can check this formula off to indicate that we have fully decomposed this formula. That is, we've fully represented the conditions under which this particular formula, line 1, is true, in terms of line 3. Now, at line 2, we have a negated existentially quantified formula. And so we can apply the negated existential decomposition rule to line 2. Applying the negated existential decomposition rule to line 2 gives us AY not RYY. That is the universally quantified not RYY. So again, what we're doing is replacing this negation and the existential quantifier with the universal quantifier that now ranges over not RYY.
So the next rule that we'll take a look at is existential decomposition. Existential decomposition is pretty straightforward. What you have is in a tree an existentially quantified formula. Let's say it's something like EX MX. And you want to represent the conditions under which this formula is true in terms of another formula that is quote unquote simpler than it. And so what this says is that we can represent the conditions under which it is true by removing the existential quantifier and replacing all of the variables it binds with a name, but that name has to be foreign or new to the branch. So in this case, we don't have any names, let's say in our tree, so we could replace X with whatever name we want. So it could be A here. Now the key thought here is the reason we're replacing this X with a name A that is not found in the branch is because this A here is referring to some item in the domain, something that has the property of being M. And we don't know anything else about this particular thing. So the idea would be is if you had EX MX and it said something like someone was murdered. When you say someone is murdered, you're not saying exactly who, you're just saying that there's at least one individual that is murdered. And so when we use a name to refer to that individual who was murdered, what we're doing is saying, you know, this individual, which will give a name, has this particular property of having been murdered. So it's important that this name A doesn't already refer to someone that we know some information about. So if I say, you know, oh, my neighbor is named John, I can't say, well, I also have this proposition that someone was murdered, therefore John was murdered. So let's formalize all this a little bit more. So we have this particular formula EX and phi, where phi is some formula. And what existential decomposition allows you to do is take this existentially quantified formula and replace all of the variables it binds. In this case, it's binding just X, and replace it with a name. But there's conditions placed upon the names that we use to replace those bound variables. A is going to be what's called an individual constant or name, as we've been referring to it, that does not occur previously in the branch. So what we would do is if we had a branch that had PA, QA, and then let's say EX, PX, when we use existential decomposition here, we would want to make sure we do not pick any of the names that are found in the branch that contains this existential quantifier. So we would say PB, we'd pick a new name. So let's look at one quick example of the use of existential decomposition. So at line 1 here, we have our beginning of our tree, which is EXPX, someone is a person. And at line 2, we use existential decomposition on line 1, and we replace all of the variables that are bound by this existential quantifier with a name, and that name cannot be found in the branch containing that existentially quantified formula. In this case, since there are no names, we could pick whatever name we want. And so in this case, we pick A. So let's look at another example. Here we have EXPX and EXQX. And similar to before, at line 3, we make use of existential decomposition on line 1. What we're doing is taking this EXPX, we're taking that existential quantifier and sort of removing it and replacing all of the variables that it binds with a name. So we're taking all these X's with a name that is not found in the branch. And so since we have PA here, we replace that X with A, and this is perfectly fine. But now take a look at line 4 here. If you take a look at line 4, what we're doing is trying to use existential decomposition on line 2. Line 2 is this EXQX, and so we're replacing that X with an A. But this is not correct. The reason it's not correct is because this A is already found in the branch containing this existentially quantified formula at line 2. We've already picked A, and so we cannot replace this X with A. So this would be, let's say, the correct way to do things. At line 2, rather than replacing this X with A, we replace it with B. And in this case, we're replacing that existentially quantified variable at line 2, this X here, with a name, which is B, that is not found in the branch. If we look upward through this branch here containing this EXQX, or we look through this branch, the letter B is not found, and so this is perfectly acceptable to use. Similar to before, we cite the line of the formula that we're decomposing, and then use the abbreviation for the rule that we're using. So the next rule I want to take a look at is universal decomposition, and this one gets abbreviated as upside down AD. So the idea behind this rule is that if you have a universally quantified well-formed formula, that is a formula where the main operator is the universal quantifier, then you'll make use of this universal decomposition rule, this upside down AD rule. And as it mentioned, this is how we'll abbreviate it. The basic idea behind this particular rule is that if you had a universally quantified formula AXPX, what we want to do is represent the conditions under which this is true in terms of simpler formulas, or in terms of a set of formulas. Now, what does AXPX say? It says something like everybody is a person. So if we were to try to decompose this, and let's say we had 3 individuals, we'd say, well, Al is a person, Bob is a person, and let's say Chris is a person. So provided our domain, or the number of individuals, or everyone that we're talking about is finite, we can go ahead and list off A, B, C, and use universal decomposition to decompose this universally quantified formula from line 1. So in short, what we can do is represent the conditions under which a everything or all statement or a universally quantified formula is true by simply listing off all the individuals. Another way of thinking about this is what we're doing is taking this universal quantifier and removing it and replacing all of those X's with any name that we want. And if we wanted to fully decompose this formula, we would list all of the individuals that have this particular property P. So every individual from the domain that has that property. So again, if we have a domain and there's 3 people, John, Sally, and Frank, and all of these individuals are named, let's say A refers to John, B refers to Sally, and C refers to Frank, we can represent the fact that what would be the truth conditions of everybody as a person simply in terms of these 3 simpler sentences: that John is a person, that Sally is a person, and that Frank is a person. Now I want to point out 2 problems with the use of universal decomposition as I mentioned it. The first is that this process of listing off all of the formulas won't really work if the domain is infinite. The thought process is let's say you had AXPX and you said, okay, and everything in the domain has this property of being P. Well, if you want to list off the conditions under which this formula is true in terms of simpler formulas, well, it seems like you would be going on forever listing all of them by writing them all out because there's an infinite number. So that's one problem. The second problem is that this procedure won't really work if there are some items in the domain that are unnamed. So the thought process here is, let's say we had an interpretation of a property and it had, let's say, 3 items, 1, 2, and 3. And our domain, let's say, also consists of 3 items, 1, 2, and 3. But we only have an interpretation that names 2 of those items. Let's say A refers to 1 and B refers to 2. And we want to say something that is true, which is that everything in this domain is this property E, or is in this interpretation. But now when we go to decompose this line 1 here, this universally quantified formula, what we'll have is EA and EB. But we don't have a way of referring to 3 right here. We don't have, let's say, a name that picks this thing out. So that's somewhat of an issue. If we want to decompose this universally quantified formula for every item that is E, then we need to make sure that each one of those items that is in this interpretation, there's some name that picks it out. So with that in mind, it's not going to be the case that we can fully decompose a universally quantified formula every time. And so that's why you won't see, let's say, a check mark by it, these universally quantified formulas, because if you're dealing with infinite domains, then it won't be fully decomposed. Nevertheless, you can provide, let's say, a partial decomposition for it, or a full decomposition if you're working with a finite or limited number domain. But in general, the way this rule works, universal decomposition, is again, you have a universally quantified formula that ranges over a formula. And you use it by removing the universal quantifier and replacing the bound variables, in this case it's x, with any name that of our choosing. Another thing is that the replacement of the name needs to be consistent or uniform. Let's say you had the formula, everyone loves themselves. Well, here, when you go to use universal decomposition, the replacement of these bound variables, which are x here, needs to be consistent. So it'd have to be LAA, or it could be, let's say, LBB. What would not be correct would be LAB, where we replace one x with A and another x with B. This is not a consistent or uniform replacement. So let's look at a couple quick examples. If you take a look at line 1 here, we have this universally quantified formula. And then at line 2, we use universal decomposition, citing the line number and the rule. And notice what happens. We have AX, not PX. What we're doing here is removing this universal quantifier. So we're taking it off. And then we're going to replace all of the variables it binds, in this case x, with any name of our choosing, provided we do it uniformly. So at line 2, we take that AX and replace it with A. And the same thing happens at line 3, and we could keep on doing this. Since it says AX, not PX, so everything doesn't have this property P, we could go on, not PC, not PD, as many times as we want, or as many times as necessary. And in each case, we're doing the same thing. We're removing the universal quantifier and replacing all of the variables it binds. So let's look at one example that incorporates a number of the decomposition rules in it. So if we take a look at this tree here, we have lines 1 and 2, and this is the initial setup. 2 formulas are written down. We have a negated universally quantified formula and a negated existentially quantified formula. Now at line 3 here, what we've done is to use the negated universal decomposition rule. The reason we did this is because, look, line 1 here is a negated universal decomposition, universally quantified formula. And so what we do is just kind of flip this negation inward and replace that AX with EX. Now at line 4, what we're doing is using negated existential decomposition on line 2. Line 2, it says not, that's the main operator, this negation, and it's ranging over this existentially quantified formula. So it's a negated existential, and so we use the corresponding rule. Turns this negated existential into a universally quantified formula that ranges over a negated formula. So that leaves us with lines 3 and 4 here. With respect to line 3, what we did was use, since we see it as an existentially quantified formula, the main operator is that EX there, we saw that if you have an existentially quantified formula, you can remove this existentially quantified formula and replace this X with a name that is not found in the branch containing that formula. And since we don't have any names, we could pick any name we want. So in this case, we picked PA. Now for line 4, we have AY not RYY. It's a universally quantified formula. Notice that the main operator is that upside down A. And in this case, what we did was just decomposed it 2 times. We have this AY not RYY. And so what we did was take that AY not RYY and we replaced each one of these Ys with any name that we want. And we can pick names that are already found in the tree. So we can pick A, which we did at line 6, and then we can also pick B, which we did at line 7. So this would be an example that involves 4 different decomposition rules.
In this video, I'm going to talk about the revision to the notion of a completed open branch in the language of predicate logic. So what is that revision? Well, a branch is considered a completed open branch in predicate logic if and only if it meets 3 conditions. The first condition is similar to propositional logic. It basically states that a branch is a completed open branch if and only if all of the complex, well-formed formulas that can be fully decomposed are decomposed. The second and third conditions are for all universally quantified formulas, a formula where the main operator is the universal quantifier that occurs in the branch, there is a decomposition for that universally quantified formula for each name that occurs in the branch. Now, this particular clause is, I think, more difficult to understand than the other 2, so we'll kind of come back to this in just 1 second. But let's just state this third condition. The third condition is that the branch does not contain a formula and its literal negation. So you don't have something like P and not P, or not PB and PB in the branch. Okay, so let's go back to this second conditions because it's the most important one and we need some illustrations to get a clear sense of this. So what this condition states is that for every universally quantified formula in the branch, we decompose that universally quantified formula for every name that's in the branch. So what this is saying, just let's give an example here. Let's say you had PA and you also had AX PX. When we go to decompose this universally quantified formula using universal decomposition, we can replace the universally quantified variables with any name that we want. So we could pick B or C or D. But this restriction states that we can only call the branch open if for every name that occurs in the branch, we've decomposed the universally quantified formula for that name. So in order to have a branch that just contains these 2 formulas to be open, we need to decompose this second formula, that universally quantified formula, using A. So the idea here is that A is a name found in the branch. There's a universally quantified formula here. So we need to make sure we decompose that universally quantified formula using A, where we substitute the A for the quantified variable. The reason we want to decompose the universally quantified formulas for every name is just to ensure that there is not a latent contradiction found in the branch. Let me give you an example. Suppose we had not PB, and again we had AX PX. Now suppose we looked at the second formula into universally quantified formula, and we're going to replace the X with A. Now at this point we might say, well, I've decomposed the universally quantified formula once. I could go onward and onward. I could pick C and D and E and F and so forth and so on. I can pick any name, but I need to find some sort of stopping place. You'll notice though that B is found in this branch. And were we to decompose the universally quantified formula for B, what we would get is not an open branch, but we would get a closed branch. We would get a formula PB and its literal negation, not PB, in the branch. And this would lead to the branch closing. So the idea behind this second condition is that we decompose all the universally quantified formulas for every name that's found in the branch just to ensure that there is no formula in its literal negation found in the branch. Let's look at 2 more examples to help illustrate these 3 conditions. Now imagine you have a truth tree that consists of these 4 propositions, and you'll notice the only proposition that can be decomposed is this 4th proposition, this universally quantified AXPX. When we go to decompose it, we need to make sure we decompose line 4, the universally quantified formula, for every name that's found in this branch that contains the universal quantifier.
So we see that A is at line 1, B is line 2, and C is found at line 3. So we need to decompose the universal quantifier 3 times. Once for A, once for B, and once for C. So once for each name that's found in the branch. Now I want to look at a second example, but this second example will not only illustrate the 3 conditions associated with a completed open branch, but it also suggests a strategy, an efficient way of decomposing truth trees. And that strategy is that we should always try to decompose universally quantified well-formed formulas last. We leave those formulas to decompose them last and try to decompose all the other formulas first. Now in this example, we've decomposed a tree that consists of 2 formulas, this existentially quantified x px and the universally quantified x not px. In this particular example, there's nothing wrong with the use of the decomposition rules. There's just something wrong with thinking that this represents a completed open branch. So at line 3, what we have is a decomposition of line 2 using universal decomposition. And this is fine. We can replace the universally quantified variable x with any name that we want. In line 4, this is also an acceptable use of existential decomposition. We look through the branch and see, hey, A is already found, and there's a restriction on the use of existential decomposition such that you cannot pick a name that's already found in the branch. And since A is found in the branch, then we need to pick a different name. And so B is a perfectly acceptable name to use. The problem with calling this branch, though, a completed open branch is that you'll notice that there is a name, B, found in the branch and a universal quantifier found in the branch. And this universal quantifier has not been decomposed using B. That is, we haven't replaced the universally quantified variables x with B. And so we'll need to go ahead and decompose this line 2, universally quantified x not px, using B in order to make sure that we decompose the universal quantifier for every name that's found in the branch. And when we do this, instead of finding an open branch, we would get not PB. We would see that the branch is actually a closed branch. Now, a further thing about this particular example that is suggestive is it points to a particular strategy for decomposing truth trees, and that is to decompose universally quantified well-formed formulas last. One of the things to note is that this tree took 5 lines. We decomposed the universal quantifier at line 3, then we did existential, and then we saw, oh, we have this B right here, and there's a universally quantified formula here, so we need to decompose line 2 using B. So it caused this 5th line. But were we to decompose the existentially quantified formula first and leave the universally quantified formula for last, we would see that it would save us a line here. So at line 3, we decomposed the existential quantifier at line 1, and we picked A because A is a name that's not previously found in the branch. At line 4 here, we decomposed the universal quantifier. And remember, when we decompose the universal quantifier, we decompose it for every name that's already found in the branch or that's found in the branch. And since A is found in the branch, we picked A. And it gives us the same result. The tree is closed, but you'll notice this only took us 4 steps rather than 5 steps. So the goal of this video was to explain what a completed open predicate logic branch was. And that is a branch that has the following 3 conditions. 1, all the complex well-formed formulas that can be decomposed have been decomposed. 3, there's not a formula and its literal negation. And the most important or most difficult to understand one is that when we have a universally quantified well-formed formula in the branch, and there are names, there's formulas with names found in that branch, we need to make sure we decompose the universally quantified formula for every name that we see in the branch. In this video, I want to explain how you can recover or construct a model from a completed open branch. Now, this particular video might presuppose a little bit of knowledge that might have been covered already in some of the videos that I've done thus far, but you can maybe kind of read around, or you can ask questions in the comment section below if you don't quite understand something. Let me give you a little bit of context. Let's say you have an English argument you want to test to see if it's valid or invalid. So what you do is you'd start by translating it into predicate logic. So phi, psi, and chi right here. Let's just say that these are
predicate logic well-formed formulas. Then you would set up the truth tree by taking the premises and the negation of the conclusion. You'd stack these particular formulas. Then you would decompose the tree using the decomposition rules. And then you would look to see if there's a completed open branch or if the tree is closed. If there is a completed open tree, that is, there's a tree with at least one completed open branch, then we know that there's at least one model where all of the well-formed formulas in the stack are true. That is, we would know that this formula, there's a completed open branch, this formula, and this formula, are all true. And if that's the case, then it's possible for the premises to be true and the negation of the conclusion to be true, which is just another way of saying it's possible for the premises to be true and the conclusion to be false. And if that's the case, then the argument would be invalid. So a completed open tree of these particular formulas would show us that, or indicates to us, is that there's at least one model, one configuration of the world that makes all of the premises of the argument true and the conclusion false. So what this video is going to aim at doing is explain to you how you can construct or recover a kind of toy model from that completed open branch. So let's look into this. Before I explain how we can construct a model from a completed open branch, it's helpful just to remind ourselves of one particular definition. This is the notion of a literal well-formed formula. All a literal well-formed formula is an n-place predicate followed by n names, or a negated n-place predicate followed by n names. So here are some examples of some literal well-formed formulas. PA, it's an n-place predicate followed by n names, not PA, RAB, RAA, not RAA. Another way of thinking about what a literal well-formed formula is, it's a simple formula that we cannot decompose further using our decomposition rules. So now I can talk about the step-by-step process by which you would recover a model from a completed open branch. After I kind of walk through this step-by-step process, then I'll look through an example. It might be helpful once I've gone through the example to come back to this portion of the video and look through the steps once again. The first step is to identify a completed open branch. This is what we'll use to recover the model. I covered what a completed open branch is in an earlier video, and so if you're not sure what a completed open branch is, I'll put a link in the description below and you can check out that video before coming back here. The next is to start from the base of the completed open branch and work your way up through the branch, writing down all of the literal well-formed formulas in a branch. So let's just imagine we had a branch that contained the literal well-formed formulas PA, PB, and not QB. The next part of constructing a model from this completed open branch is to give an interpretation for each of the names in that branch. We have two names in our branch. We have A and B. And so we'll want to have these names designate some item in the domain. The reference of our objects is kind of up to you. It could be numbers, it could be colors, it could be movies. It's whatever you want to talk about. For simplicity's sake, I'll have the names actually refer to some dummy object that I'll just call A or B. So what this is doing here is saying I'm going to let the name A refer to some object A, and I'll let the name B, it refers to some object B. And both A and B are objects in the domain. The fourth step is that for every name interpreted in terms of some item in the domain, we need to explicitly indicate what those items are, or we need to explicitly indicate that those items form a part of the domain. The idea here is that we're saying that the interpretation of the name A refers to some object A, and the interpretation of the name B refers to some object B. And so we'll need to specify that A and B are part of the domain. If you had A refer to the number 1 and B refer to the number 2, then you need to specify that the numbers 1 and 2 are part of the domain. If you had A refer to your favorite movie and B refer to your least favorite movie, whatever those movies might be, then you need to specify that in terms of the domain here. The last step involves the interpretation of the predicates. And there's a couple ways of doing this, but I think one way is to simply write out the literals or look at the literal well-formed formulas And so we had PA, PB, and not QB. And then we'll develop an interpretation of the predicates that would make each of these formulas true. So PA true, PB true, and not QB true. And so when we go to interpret PA, we need to make sure that A is found in the interpretation of P, because if it's not, then PA won't be true. And B is also found in the interpretation of P, because if it isn't, then PB won't be true. With respect to not QB, we need to make sure, or we need to have an interpretation of Q such that B is not found in its interpretation. And so we could do something like say, okay, Q, the interpretation of Q only has A. It refers to the object A. A is the thing that has property Q. What's important here is that the interpretation of Q does not contain B. It can contain the object A, or it might refer to nothing at all. So our second interpretation over here is, again, we have the interpretation of P refer to A and B, but here we have the interpretation of Q just refer to nothing. It doesn't refer to any object in the domain. Another way of writing that is using the empty set symbol. We simply indicate that the interpretation of Q contains no items. So now let's put all this together and look at a concrete example. So suppose we have done the work of translating our English argument into the language of predicate logic. And so we have something like PA, not RC, QB, therefore not AXPX. We then take all of that and put it in the truth tree. We decompose all the formulas in the truth tree. And what we find is that we have a truth tree with one completed open branch. What this indicates to us is that we can construct a model that would make all of these particular formulas true. In other words, it would make this particular argument invalid, or a case of non-entailment. So how do we do this? Well, first we can just kind of simply state that we're going to construct a model, and that consists of two things: the domain of discourse and the interpretation. Next, we'll start by listing out all of the literal well-formed formulas. So we have all of these particular formulas written out. That's PA, RC, QB, PA, PB, and PC. You'll see that PA is found twice in this branch, but it's we only need to kind of write it down once. With the literal well-formed formulas all written down, we'll take a look at how many names there are. There's A, B, and C, and we'll want to make sure we give an interpretation of those names. Again, I'm going to let the name A refer to some object A. You can let the name A refer to something else if you want. You can have it refer to numbers, people's, favorite movies, so forth and so on. But just to kind of keep things abstract and general enough, I'm just going to have A refer to A, B refer to B, C refer to C. The next thing we want to make sure we do is indicate explicitly, since we're constructing a model that consists of a domain and an interpretation, that the objects A, B, and C are part of this domain. So I said that the name A refers to the object A. And so here I'm writing that there is an object A, object B, and object C in the domain. The last part of our model involves writing all the literal well-formed formulas down and constructing an interpretation of the predicates that would make all the literal well-formed formulas true. And so I'll start with PA, PB, and PC. I see these particular formulas all contain the predicate P, and so I want to construct an interpretation of the predicate P that would make each one of these literal well-formed formulas true. And so what I need is an interpretation of P that contains A, B, and C, that contains each one of those objects. And so I'll write the interpretation of P contains A, B, and C. And once again, I know I said this a couple times, if your A referred to a number like 1, B referred to 2, C referred to 3, then you'd write 1, 2, and 3, the objects that the names refer to. Next, I want to make sure that not RC is true. I want to construct an interpretation of R that makes sure that not RC is the case. Well, that would be any interpretation that does not contain C. It could be, we could interpret R in terms of A and B, or interpret R in terms of A, or interpret R in terms of just B. Or we can have an interpretation of R where it refers to no objects in the domain. What's important for making not RC true is that the interpretation of R does not contain C. And this is an example of such an interpretation. Lastly, we have QB. This is another literal well-formed formula that we want to make sure our interpretation of Q is makes this particular formula true.
And what we'll need is an interpretation that has B inside of it. So we interpret Q as having the object B. But we could develop a more expansive interpretation here. We could have Q refer to A, B, and C. So long as it contains B, then QB will come out as true. So here we've cleaned everything up. What we said was that if you have a completed open branch, like we have here, we can construct a model, at least one model that consists of a domain and interpretation. And that model is an illustration or a configuration that would make all of the formulas in the completed open branch true. And so our model consists of a domain that contains object A, B, and C, an interpretation of each of the names that are found in the completed open branch, which is A, B, and C, an interpretation of each one of these names, an interpretation of all of the predicate terms in terms of objects that are found in the domain. So what the model does is provide us an explicit example or configuration or way the world would be, or a way something could be that would make the premises of the argument true and the conclusion false. So in this video, I showed how from a complete open branch you could construct a model. Now, obviously, this would look different if you were testing a real life English argument. If you're interested in such an example, let me know in the comments below, and I'm happy to provide a more fleshed out example of this. In this video, I want to introduce predicate logic derivations, or sometimes called predicate logic proofs. Predicate logic proofs aren't terribly different from propositional logic proofs. There's a lot of overlap. So if you're preparing to do predicate logic proofs, you might want to brush up on propositional logic proofs because there is a lot of carryover. The significant or meaningful difference pertains to the need for some additional derivation rules to handle quantified well-formed formulas. That is, in predicate logic proofs, we have formulas where the main operator is the universal quantifier or the existential quantifier, and we'll introduce some derivation rules that allow us to reason with or to these types of well-formed formulas. In this video, what I'd like to do is just to go over some terms that are important for understanding what's going on when we talk about predicate logic proofs. The first part is the deductive apparatus for predicate logic. The deductive apparatus for predicate logic refers to a set of rules of derivation. These are rules that express which well-formed formulas can be written after which well-formed formulas in a derivation. One way of thinking about the deductive apparatus is it's the set of rules of reason or the permission rules that allow us to move forward in a proof. The notion of a deductive apparatus makes reference to a derivation. I've covered the notion of a derivation before, but I just want to briefly cover it again here. All a derivation is a series, a finite series of well-formed formulas. And we talk about a derivation from a set of formulas, let's say gamma, to a formula, let's say phi. And all this is a sequence of formulas beginning with gamma, and each kind of step in this series is a predicate logic well-formed formula, and this series ends in a formula phi. But this series has certain constraints on it. The first constraint is that we begin the series with this set of formulas gamma, and this gamma might contain 5 or 6 or 7 formulas. The formulas of gamma are sometimes thought to be or referred to as premises of the argument. So we're reasoning from these premises that are found in gamma to the formula, the conclusion, which is phi. So derivation, it begins with gamma and terminates with phi. The final constraint on this series is that each one of these well-formed formulas between gamma and phi is either a premise, an assumption, or is the result of preceding formulas and the deductive apparatus. That is, each one of these formulas in the sequence from gamma to phi is justified by our deductive apparatus. In other words, each of the rules is justified by one of our derivation or proof rules, or you can think about it as each one of these formulas is justified by the rules of inference or reasoning that we make use of. Just a couple things to keep in mind. First, the deductive apparatus is simply the rules that allow us to write well-formed formulas on a line. The deductive apparatus essentially justifies why the
new well-formed formula can be put at the line it's found at. The deductive apparatus for predicate logic consists of the deductive apparatus for propositional logic, along with the new derivation rules for quantified expressions that we'll develop in future videos. That is, we take all of the rules from propositional logic and we bring them in or import them in to our rule set for predicate logic. The last thing with respect to this, let's kind of note about the deductive apparatus is we adopt a lot of the same conventions for displaying proofs. So we'll display the proofs vertically. So rather than simply writing each of the formulas out one right after another in a horizontal row, we'll display them vertically. We'll number each well-formed formula so we can refer back to it. We'll make use of vertical lines as well as indentation to indicate the scope of assumptions. We'll also explicitly indicate when we make use of a particular rule from the deductive apparatus. In other words, at each line in the proof, we'll develop some conventions for saying that this line in the proof is here because of the first line and the second line, as well as this particular derivation rule. The last thing I want to mention with respect to predicate logic proofs is the notion of a syntactic consequence. And all the notion of a syntactic consequence is that if there is a derivation from a set of well-formed formulas gamma to phi, then we can say that phi is a syntactic consequence or is syntactically entailed by gamma. The idea here is that if there is a derivation from gamma to phi, then we can say that gamma syntactically entails phi. So just to repeat this definition one more time, this notion of a syntactic consequence, we say that a formula phi is a syntactic consequence or is syntactically entailed by a set of formulas gamma, just on the condition, so if and only if, there is a derivation using the rules from predicate logic of phi from gamma. And we can express this by writing gamma entails phi. So in short, if there is a derivation from gamma to phi, then we can write gamma syntactically entails phi. In the next set of videos, I'll go through some of the derivation rules in the deductive apparatus for predicate logic. The first rule I'd like to talk about with respect to the derivation rules, or the rules found in the deductive apparatus for predicate logic, is the universal elimination rule. The universal elimination rule states that from a universally quantified formula, so this universal quantifier here is operating on this formula phi, we can derive a well-formed formula phi which is the result of removing the universal quantifier here and replacing in phi each instance of x that is bound by the universal quantifier with a name a, where this replacement is uniform. So the idea here is, let's say we had a universally quantified formula ax px. We would make use of universal elimination by removing the universal quantifier and replacing each instance of x with any name of our choosing, provided this replacement is uniform. So here we could replace the variable x, which is bound by the universal quantifier here, with say a. And we could apply universal elimination again and replace each instance of x with a different name, which is b. So again, the idea behind universal elimination is we reason from a universally quantified expression to a formula that the universal quantifier operates on, but we replace each bound variable x with a name of our choosing. The idea behind universal elimination is pretty straightforward. It corresponds to how we reason using universal propositions. Someone might say everything in this cage is a butterfly, or is going to be a butterfly, or in the future will be a butterfly. And from this, we can reason to any specific item in the cage that we have a name for. So let's take a look at this particular butterfly that is very prominent in this slide and call this particular butterfly tech. So we can reason from everything in this cage is a butterfly to the statement tech is a butterfly. We represent this in the language of predicate logic by saying for all x, bx, that is everything in the domain of things that we're talking about is a butterfly. Therefore, tech is a butterfly. And what we've done is simply to replace, again, remove the universal quantifier and take the formula that the universal quantifier operates on and replace each bound variable with a name of our choosing. And in this case, we pick T because T refers to tech here, this butterfly. Let's look at some further examples. The basic idea behind universal elimination is you start with a universally quantified formula, and you can move forward a step in the proof, move forward a step in the derivation by removing the universal quantifier and replacing the bound variables with any name of our choosing. So just to look at a quick example, here we have AXPX at line 1, and lines 2, 3, and 4 are results of using universal elimination on line 1. At line 2, we used universal elimination and replaced X with A. At line 3, we used universal elimination on line 1. So we're reasoning from this universal quantified expression, and we replaced the bound variable X with B. And at line 4, we made use of universal elimination once again on line 1, replacing the bound variables X with E. So one thing to kind of note about this example is the name we pick is completely up to us. And then 2, you can make use of universal elimination more than once on a particular universally quantified formula. One mistake I sometimes see is that the replacement of variables with names is not uniform. So the idea is that when you make use of universal elimination, this replacement of variables with name needs to be uniform. So let's look at an example of this. Here at line 1, we have for all X, RXX. At line 2, we make use of universal elimination, and we replaced all of the bound variables with a name, and that name is the same name. At line 3, we have use of universal elimination again on line 1, and we replace the bound variables X with the same name. But line 4 is a case where we've taken those bound variables, and in one case, we replace the X with A. In the other case, we replace the X with B. This is not an acceptable use of universal elimination. To see why, suppose line 1 says everyone loves themselves. So for any X in the domain, that X is in the relation of loving themselves. It would follow that from line 2, when we make use of universal elimination, we'd see that it would follow that Alfred loves himself. And this would seem to intuitively follow from line 1. If everyone loves themselves, then Alfred loves himself. At line 3, we say that we have RBB, and let's say B stands for Bob. Line 3 would say Bob loves himself. And again, this doesn't seem problematic to say if everyone loves themselves, then it would follow that Bob loves himself. Line 4 is the problematic line though. If line 1 says everyone loves themselves, then line 4 would say that it would follow from line 1 that Alfred loves Bob. But that doesn't follow intuitively from the sentence everyone loves themselves. So to summarize, when you replace the bound variables with names, you want to make sure that the replacement with a name is uniform. The next rule I'd like to look at with respect to the derivation rules for predicate logic is existential introduction. Existential introduction says that from a well-formed formula that involves a name, and let's just call this name A, we can reason to or derive in the derivation an existentially quantified well-formed formula. And that existentially quantified well-formed formula is the result of consistently replacing at least one name A with an existentially quantified variable. A basic example would be, let's say you had PA. You could, making use of existential introduction, reason to an existentially quantified formula, EX, PX. And here what we've done is taken this A, this name A, and replaced the A with a variable X that is now existentially quantified. Similarly, let's say we had QBB. Were we to make use of existential introduction on this particular formula, we would replace at least one of the names with a bound variable. We're going to replace each B with an X, and that X is going to be existentially quantified. So the idea here is we're reasoning from a particular formula to an existentially quantified expression, and we're replacing each of the names with an existentially quantified variable. Existential introduction corresponds to how we reason with various propositions.
That is, if I say Tech is a cat, or if I name an individual and ascribe that individual a property, I can reason to this statement that something is a cat. So if Tech is a cat, then by existential introduction, something is a cat. More formally, we might write CT. And so what we're saying here is Tech, right here, Tech, has the property of being a cat. And if that's the case, if Tech is a cat, then something or someone is a cat. So in short, existential introduction allows you to derive or reason to or write in the proof an existentially quantified well-formed formula. We reason from a well-formed formula with a name in it to an existentially quantified expression. Let's look at two examples. In our first example here, we start with two formulas, PA and RB. Line 3 is the result of applying existential introduction to line 1. We reason from PA to EXPX. And you'll notice what we've done here is taken the name A and replaced it with a variable and added an existential quantifier that quantifies for that specific variable. We reason from, let's say, Alfred is a person to someone is a person. At line 2, we have RBB, and line 4 is the result of applying existential introduction to line 2. Here we've replaced each one of the B's with existentially quantified variables. You'll note in each case we reason from a formula to an existentially quantified expression, and our reasoning only relied upon one line prior in the proof. At line 3, we only required line 1 to reason to this existentially quantified expression, and at line 4, we only required reasoning from line 2 to this existentially quantified expression. There are a couple extra things to note about existential introduction. The first is that the replacement of variables must be uniform, but you only need to replace one name. That is, if you're planning on replacing more than one name with an existentially quantified variable, you need to make sure it's the same name in each case. Let's look at an example. So here's a number of instances of existential introduction. Some are acceptable, some are not acceptable. In the case of line 3, we applied existential introduction to line 1. And what we've done here is replace the name B with an existentially quantified variable X. And so this is an acceptable use of existential introduction. We're taking the single name B and replacing it with the existentially quantified X. Line 4 is also an acceptable use of existential introduction. But in line 4, we're replacing the name A with the existentially quantified variable X, and we're leaving B alone. Line 5 is not an acceptable use of existential introduction. Here, we might say that line 1 says that Alfred loves Bob, and we're reasoning to a formula that says someone loves themselves. Well, in virtue of the fact that one individual loves another distinct individual, it doesn't follow from this particular proposition that an individual loves themselves. But what we've done here is we've taken two names, two distinct or different names, and replaced it with the same variable. And this is not acceptable according to existential introduction. When we replace more than one name with a variable, then we may need to make sure it's the same name and not a different name when we do the replacement. When we look at line 6, what we have here is the same name, B and B, and so it's acceptable to make use of existential introduction on this and replace each one of the B's, if we're going to replace more than one, with the same variable. But you need not replace all of the variables when you make use of existential introduction. Take a look at line 2. We have two B's right here, but at line 7, we're reasoning to there exists an X, RBX. So we've taken the rightmost B and replaced it with an existentially quantified variable, and we left the leftmost B alone. This would follow, let's say 2 says Bob loves himself. Well, it would follow from Bob loving himself that Bob loves someone. That someone just is himself. So this is something to keep in mind if you're planning on using existential introduction to replace more than one name with a variable. In this video, I'll introduce universal introduction, a derivation rule for predicate logic proofs. Universal introduction basically is a rule that says that we can reason to universally quantified formulas.
these types of formulas can be derived from formulas that contain names, provided we meet certain restrictions. These restrictions are that the formula that contains the name that we're using universal introduction on, so that name does not occur as a premise or as an assumption in an open subproof, and the name does not occur in the resulting universally quantified formula. Essentially, universal introduction states that we can reason from a formula like PA to a universally quantified formula like universally quantified PX, where here we're replacing this A with an X and putting a quantifier in front of it, provided we meet these two restrictions. So let's look at this rule in a little bit more detail. So the first thing to note about universal introduction is that it's an introduction rule. What this means is we're reasoning from a formula to a universally quantified formula. So we're reasoning from a formula with a name to a universally quantified well-formed formula. At first glance, this seems really strange and it doesn't seem like a legitimate rule. How can you reason from a formula that says that a particular item has the property G to everything having that property? It seems akin to reasoning, my cat is fat, therefore every or all cats are fat. This looks like a case of hasty generalization, where we reason from the fact that one or a limited number of individuals have a particular property to all the things having a particular property. The reason why universal introduction is acceptable has to do with the fact that the name we generalize or that we turn into a universally quantified variable could be any name. That is, when we're reasoning from PA to for all x, px, this name has to have special properties. It has to meet certain conditions. And the general condition is that this name could have been B or C or D or E or any name. And since that it could be any name, that is, since this name could refer to any item in our domain, this allows us to generalize. So one of the reasons that universal introduction is acceptable has to do with certain restrictions we place on when you can use universal introduction. And the core of that restriction has to do with the fact that the name that we universalize is arbitrary. Let's look at an example of this in the context of a proof. Suppose we're talking about a domain and I say everything is a leaf. And then I also say all leaves or all the leaves are golden. Therefore, everything is golden. This looks like a valid argument, and we might represent this as follows. For everything is a leaf, we could write for all x, lx. For all of the leaves are golden, we can write ax, lx, then gx. And for everything is golden, we would write the universal quantifier ax, gx. In the context of a proof, we would reason as follows. First, we have the premises, ax, everything is a leaf, ax, lx, then gx, all of the leaves are golden. And then we could reason from ax, lx to la using universal elimination. We're reasoning from everything is a leaf to a named leaf that we name with A is a leaf. And also from ax, lx, then gx, the second premise, we could reason using universal elimination. If a particular item is a leaf, then that particular item is golden. Next, from the fact that we have a particular item that we named A is a leaf, and we said that if that thing is a leaf, then it's golden, we could reason to using conditional elimination, also known as modus ponens, to that item is golden. Now the last step here is the use of universal introduction. That is, we want to know whether or not it's acceptable to reason from a particular item being golden to everything is golden. Like in our example up here, we reason to everything is golden. One of the reasons that we might say that this is acceptable, that in this instance, it's acceptable to use universal introduction, replacing the name A with a universally quantified variable X, is because that this A here could have been B, it could have been C, it could have been D,
It could be any name that refers to any item in the domain. And the reason for that is because this universally quantified LX and this universally quantified LX then GX, we could have used universal introduction to derive B or C or D here, or we could have used it to derive A or B or C or D here. So given the fact that this GA right here, this A could have been any name, and those names could refer to any item in the domain, it looks acceptable to use universal introduction. So we need restrictions. These restrictions are necessary to prevent hasty generalizations. That is, we put restrictions on when you can use universal introduction to ensure that on a proof where we have a well-formed formula phi, and we want to use universal introduction upon it, it's the case that for any name A occurring in that formula phi, it's such that that name A, so where's this name? This name A could have been any name, A or B or C or D. Another way of putting this is that while A, the name A, might pick out a specific individual in the domain, certain features of the proof make it such that A could have picked out any individual in the domain. That is, there's nothing intrinsic to the proof that makes A such that it picks out a specific individual. A could have instead picked out any of the items in the domain. So let's take a look at some of the restrictions associated with universal introduction, and then we'll walk through a number of examples showing you how to use this rule and how not to use this rule. So whenever you're thinking about using universal introduction, so you're reasoning from something like PA to for all x, px, you want to make sure that you don't violate either of the two restrictions. The first is that this A here that we're reasoning from, it cannot occur as a premise in a formula that's found in a premise, and it can't occur in an assumption that's found in an active or open subproof. So for example, if we reason to PA by making an assumption, we couldn't immediately write AX PX. This would be like saying, assume Alfred has a particular property P, therefore everyone has that particular property. So the A that we're reasoning from cannot occur in a premise or an assumption in an open subproof, and also the name A does not occur in the resulting universally quantified formula. This would be something like, let's say we said Alfred loves himself. We could reason, of course, to for all x, LXX, assuming A is not found in as a premise or as an assumption in an open subproof, we could reason from A loves A or A loves him or herself to everyone loves themselves. But we couldn't reason from a particular individual loving themselves to for all x, LXA. That is, everyone loves one single individual. So we need to make sure that the name A does not occur in the resulting universally quantified formula. So provided we adhere to these two restrictions, we can make use of, so now let's look at some examples. This is an example where we make use of universal introduction and everything is fine and dandy. At line 1, we have a premise, which is AX PXX. At line 2, we reason to PAA using universal elimination on line 1. Then at line 3, we take line 2, which is PAA, and make use of universal introduction on it. Here, since A could have been B or C or D or E or any name, and those names could refer to every object in the domain, it's acceptable to make use of universal introduction. In other words, A does not occur in any premise or assumption in an active subproof, and A is not found in the resulting formula at line 3. We don't see any instance of the name A. This is another acceptable use of universal introduction, but it's fairly more involved. In this example, what occurs is first there's an assumption of RAA. Then at line 2, there's an instance of reiteration. At line 3, we have a case of using conditional introduction, using the subproof that begins at line 1 and ends at line 2. And this allows us to reason to if RA, then RAA. And at line 4, we make use of universal introduction, taking the entire formula at line 3 and replacing every instance of A with the universally quantified X. You'll note even though A is found in a subproof, this subproof is no longer active. That is, when we make use of conditional introduction at line 3,
this subproof is effectively closed. In addition, one of the things that you'll note is that A is not found in the resulting formula. And so neither of the restrictions are violated. Furthermore, if you notice, this A could have been any formula. We could have assumed two B's up here, or C's, or D's, any pair of names. We could have derived our BB, then RBB, or RCC, then RCC. Next, let's look at some violations of universal introduction. That is, cases where we use it incorrectly. First, if we had a formula like LAA and use universal introduction on it, we would be violating the first restriction, which says that you cannot use universal introduction if the name that you are transforming into a universally quantified variable, that is, the name you're generalizing from, is found in a premise. Another example of a violation of this first restriction is this example here, where we have LAA, and this formula is found as an assumption in an active subproof. Here, essentially, we're saying Alfred loves Alfred, or Alfred loves himself, and then we're reasoning from this instance to the formula that everyone loves themselves. Since A is found as an assumption, or in an assumption in an active subproof, we can't make use of universal introduction upon it. Finally, here's an example where the second restriction is violated. At line 1, we have AX, PXX. Then we make use of universal elimination on line 1, replacing each instance of X with A. And then at line 3, we violate the second restriction because A is found in the resulting universally quantified formula. So returning to the formulation of the rule for universal introduction, the rule states that we can reason to a universally quantified formula from a formula that contains a name, provided the name that's found in the formula does not occur as a premise or as an assumption in an open subproof, and the name A does not occur in the resulting universally quantified formula. What we also saw was these restrictions are put in place to ensure that the name A that we're universalizing could be any name, and if it could be any name, then it could refer to any item in the domain of discourse. In this video, I plan on discussing existential elimination, a derivation rule for predicate logic. I'll start the video by explaining what existential elimination involves. Then I'll talk a little bit about some features of the rule, and finally I'll end with some examples of how to use existential elimination and how not to use existential elimination. Let's talk through the formulation of the rule, and then we'll break it down a little bit further in the following slides. The first thing to note about existential elimination is that it's an elimination rule. This means that we reason from an existentially quantified formula to another formula. So how existential elimination works is we begin with an existentially quantified formula, and then we make an assumption that is based upon this existentially quantified formula. That formula involves the removal of the existential quantifier and its replacement of existentially quantified variables with names. But the names that we pick have to meet certain restrictions. Namely, the name A, let's say we picked A, cannot occur in any premise or any active part of the proof. So a somewhat simplified way of thinking about this is when we make an assumption based upon the existentially quantified expression, this name here needs to be foreign or arbitrary or not already found in the proof. Once we've made this assumption, we can reason to a formula, let's just call this formula psi, and then relying upon the existential quantifier and the subproof, we can reason to psi. But this formula psi also needs to meet certain restrictions, namely the restriction that the name that we assumed in the subproof is not found in psi. So in short, existential elimination allows us to reason from an existentially quantified formula and using a subproof that's initially based upon this existentially quantified expression, reason to a formula psi. Let's take a look at this rule in a little bit more detail. The first thing to know about existential elimination is that it's an elimination rule again. So this means we always need to have an existentially quantified expression in order to start the process of using this particular rule. If you don't have an existentially quantified formula, then you cannot make use of existential elimination. Next, existential elimination doesn't allow us to reason from formulas like someone is a murderer to John is a murderer. If this were a valid form of reasoning, then we wouldn't need to do any type of investigation in order to solve murders or anything like that, we could just say, well, someone did this, well, it must be this individual right there at the scene of the crime or something like that. The reason for this is because the existentially quantified expression, such that, for example, EX, MX, this formula is true provided at least one individual in the domain has the property M, or has the property of being a murderer. But we don't know which one of those items it is from the domain. We just know that if this is true, there is one, but it doesn't specify which one. In contrast, a statement like John is a murderer picks out a specific individual. It says this individual right here, John, he has the property of being a murderer. So one way of thinking about the existentially quantified formula is its reference is vague or indirect or unclear, whereas the use of names picks out a specific individual. However, even if we don't know the exact referent of someone in someone is a murderer, we might temporarily give a name to that individual and reason from that. That is, we don't know the referent to someone is a murderer, but we might use a name temporarily, let's say John Doe, that has the role of picking out some random individual that we don't know anything about, other than the fact that we are ascribing this individual has the property of being a murderer. This use of a name that temporarily refers to an object, one of the features of existential elimination. What occurs is that we assume a well-formed formula that's based upon the existentially quantified formula, and that formula contains a name. And this name temporarily refers to the same object that's picked out by the existentially quantified variable. Then we reason from that particular formula. So for example, let's say we had a statement like EX, MX. We make an assumption and say, well, let's say A. The object picked out by A is the murderer. Now what A is doing here is not picking out a specific individual, but one of the things that we need to be careful of is that this A, this name that we make use of in our assumption right here, this A doesn't do more work than it should. That it doesn't do more than just simply pick out some random item in the domain. We don't want it picking out a specific individual that we know the identity of. Because we don't want the name A to do more work than it should, this is why we need restrictions on the use of existential elimination, particularly on when we make the assumption and when we reason to a formula and derive that formula out of the subproof. We'll put restrictions on both our assumption and the formula that we reason to in order to ensure that the name A doesn't pick out a specific individual. Let's walk through an example use of existential elimination. First, every use of existential elimination starts with an existentially quantified expression. So you can see at line 1, we have the existentially quantified expression EXPX. Second, we can't reason directly from EXPX to PA. Instead, what we'll need to do is make use of an assumption that is built upon or based upon the existentially quantified expression that occurs earlier in the proof. Here we assume PA. What we're doing is letting A temporarily refer to the object picked out by the existentially quantified variable at line 1. But you'll remember that there are certain restrictions on which name we can pick. We can't pick a name whose object we already know the identity of. Instead, we need to pick a name that is foreign or new or not already found in an active part of the proof. Since there aren't any names found in this proof already, we can pick A, but we could have easily picked B or C or D. So the key thing to note is since we don't know what X refers to, we don't know what the existentially quantified variable X refers to, the name A cannot already have a determined referent. Remember, when someone says someone is a murderer, they aren't telling you who exactly is that individual. They're still simply saying there's at least one individual from all the individuals that we might be discussing that has this particular property. So we're letting this name A refer to that individual and nothing more. The next step is to reason in the subproof to a formula that does not contain the name that we assumed at line 2. And so that occurs at line 4. At line 3, we make use of disjunction introduction to reason to PA or QA. At line 3, we make use of existential introduction to reason to the formula EX, PX, or QX. And then at line 5, since line 4 does not contain the name A, there's no A found in this formula, we can make use of existential elimination, relying upon line 1,
and the subproof found in lines 2 through 4 to reason to this final formula found in the subproof. So again, there's a couple things to remember when we make use of existential elimination. Remember that existential elimination is a fairly involved rule, and we can't reason directly from an existentially quantified formula to a specific individual. It requires that we have an existentially quantified formula, and it requires a subproof based upon that existentially quantified formula. The second thing to keep in mind is that there are restrictions associated with existential elimination, and you want to make sure you pay attention to these. The first is that the name that we assume is not found in any premise or any active part of the proof. So essentially, you want to make sure that the name that you use to replace the existentially quantified variables is completely new. The second is that any names that you assume aren't found in the formula that you're discharging from the subproof. In this first example, we see that we begin with an existentially quantified expression at line 1, EXPX. Then we make an assumption based upon this first formula, this first existentially quantified expression, and we replace each existentially quantified variable with a name. And since there's only one, we pick the name A. The key thing again to remember is that this name A is not found in any active part of the proof. Then at line 3, we make use of existential introduction to reason to there exists a Y such that PY. And then at line 4, we make use of existential elimination, relying upon line 1 and the subproof contained at lines 2 through 3 to reason to the final formula in the subproof. And this is an acceptable use of existential elimination because we didn't violate the restriction that the name cannot be found in the formula that we're discharging from the subproof. Let's look at some violations of existential elimination. Here we start with a proof that has an existentially quantified expression in it at line 1. And at line 2, we have a formula MB then AC. And we might understand this MB then AC as if Bob is a murderer, then Kathy is Bob's accomplice. At line 3, we make the assumption based upon line 1 that Bob is the murderer. So we're making this assumption because, as you see later in the proof, we plan on using existential elimination. Now, this is a violation of that first restriction. First restriction says that when we make this assumption based upon the existentially quantified expression, that name B cannot already be found in an active part of the proof, and specifically can't be found in the premises. Line 4 is acceptable. It's an instance of conditional elimination. And then at line 5, we make use of existential elimination, relying upon line 1 and the subproof lines 3 through 4. But ultimately, this is not an acceptable use of existential elimination because we violate this first restriction that this B, the name that we pick, needs to be foreign. And intuitively, we could see that were we to translate this into English, the conclusion would not follow from the premises. That is, if we have premise 1, which says someone is a murderer, and premise 2, which says if Bob is a murderer, then Kathy is Bob's accomplice to murder, we are able to reason using the incorrect use of existential elimination to Kathy is Bob's accomplice to murder. But we haven't already established that Bob is the murderer. We simply just assumed it at line 3 that he is, and then made use of existential elimination to derive this conclusion incorrectly. Finally, let's take a look at the violation of the second restriction on existential elimination. Here you'll note at line 1 we have an existentially quantified expression. At line 2 we make an assumption based upon that existentially quantified expression, replacing the existentially quantified variables with A. And this is okay. This isn't a violation of restriction 1 because those names A are not already found in an active part of the proof. At line 3, we make use of existential introduction, and this is an acceptable use of existential introduction. We're replacing one of the names with an existentially quantified variable. The problem with this proof is at line 4. At 4, we take the formula that we derived in this subproof and pull it out of the subproof. That is, we reason from line 1 and lines 2 through 3 to line 4. But what we haven't done is ensure that this formula does not contain any names that we've assumed. And so this is a violation of the second restriction right here. We want to make sure that the formula that we derive out of the subproof does not contain any names we've assumed. And you can see how this would not be an acceptable way of reasoning. Just from the fact that someone loves themselves, it wouldn't follow that Alfred loves someone. So going back to our formulation of existential elimination, what existential elimination states is that from an existentially quantified expression,
and a subproof where the assumption of the subproof is built upon the existentially quantified expression by removing the existential quantifier and replacing all of the existentially quantified variables with names, and those names are arbitrarily introduced, or to put it in another way, those names do not play an active role in the proof. So from this assumption, we can reason to a formula. Let's say this formula is psi, and if this formula psi does not contain any of the names that we've assumed, then we can, using existential elimination, derive psi from the existentially quantified expression and the subproof. This video aims to give you some practice with predicate logic proofs. What I'll do is 5 proofs that focus on existential introduction and universal elimination. The 2 Intelim rules that I consider to be the easier 2 of the 4 Intelim predicate logic proofs. One suggestion I have for you is to pause the video now, work through these proofs, and then proceed to watch the video. Watching me maybe do the proof will give you a model and it will allow you to kind of check your answers.
Let's start by setting up the proof. So the setup involves writing the formulas to the left of the turnstile down and then working through the proof to derive the conclusion. So let's set up the first proof by writing out the premises or the formulas that we're going to reason from to the conclusion. Now that we have the proof set up, the goal is to reason from PA and QA to the conclusion that I've written over here just as a helpful way of remembering what the conclusion is. So we'll start by reasoning from PA and QA and using conjunction introduction to form this conjunction, but here we can't take the PA and QA and replace those names A with X. All we can do here is reason to PA and QA, taking line 1 and 2 and forming a conjunction out of those 2 formulas. So this is by 1-2 conjunction introduction. But now that we have this conjunction, we can make use of existential introduction. And in using existential introduction, we can replace at least one of the names in this formula at line 3 with an existentially quantified variable. And if we replace more than one name, then we need to make sure the replacement is uniform. That is, we're replacing the same name with the variable. So we can write EX, PX, and QX. So we're replacing these names A with the variable X, and this variable is quantified by the existential quantifier. So this is from line 3, existential introduction. There's a couple things to note about this particular proof. Let's say we had PA and QB instead. So rather than having A and A, we have A and B. If we were to use existential introduction on this formula, we could reason to EX, PX, and QB, or we could reason to EX, PA, and QX. So since this is not the same name, we can't replace both of the variables with a single existentially quantified variable. In addition, going back to 4 right here, another formula that we could reason to would be EX, PX, and QA. So we're not required to replace all of the names with an existentially quantified variable, but whenever we want to replace more than one, we need to make sure it's the same name with the same variable. So let's look at a proof that focuses on the use of universal elimination. So here I have our entailment set up here. We have AXPX, or everyone's a person. We have AYLYY, or everyone loves themselves. And then we want to reason to, let's say Bob is a person and Al loves Al, or Al loves himself. So we'll set the proof up by writing out the 2 formulas. So let's do that first. Now that we have the proof or derivation set up, the goal will be to reason to the conclusion. So we'll start by taking the first formula, which is AXPX, and reasoning to PB. And the way we get PB, the way we derive PB is by using line 1 and the universal elimination rule. The universal elimination rule allows us to reason from a universally quantified formula to an unquantified formula, or to a formula where we're removing the universal quantifier and replacing every bound variable x, every universally quantified variable that's bound, with any name that we want. And the replacement, again, must be uniform. So now that we have PB, we can use line 2, which says everyone loves themselves, to reason to LAA. We could pick any name that we wanted, BB or CC or DD, but the reason we pick A here is because it's in the conclusion. And we also need to note that the replacement must be uniform. So if we are going to replace these two universally quantified variables, y, then we need to make sure it's BBCC, not AB, not BC, not a different combination. They need to be the same name. And so we have line 2, and we're reasoning to line 4, and this is by 2 universal elimination. Now that we have these two formulas, we have the two ingredients or two formulas that are part of our conjunction, which is in the conclusion. We can take line 3 and line 4 and put those two formulas together using conjunction introduction. And so what I'm doing here is taking line 3, which is PB, line 4, which is LAA, and reasoning to the conjunction of those two formulas. This is 3 for conjunction introduction. In this next proof, we'll reason from AXLXX to EXLXX. That is, from the formula that everyone loves themselves to the formula that someone loves themselves. The first step in this proof is to set the whole thing up. And so we'll set it up by writing the formula to the left of the turnstile, and then we'll try to reason to the formula to the right of the turnstile. So we'll write AXLXX as a premise, and now the goal will be to reason to EXLXX. We'll start by using universal elimination, and we'll replace each x with any name of our choosing. And here I'll pick A. And this is by 1 universal elimination. Now we can make use of existential elimination, replacing each one of these A's with any name, replacing each one of these A's with the existentially quantified variable x, EXLXX. And this is by line 2, existential introduction. In this proof, we're reasoning from AXLX, that is, everyone loves themselves, to the formula that someone loves someone. It's important to note about this conclusion that this sentence does not say, that is, this formula does not say that an individual loves another individual, in the sense that this other individual is distinct from the first individual. It would be true provided you have at least one individual that loves themselves, because that's one individual, let's just call them Al, who loves another individual, and that person just happens to be Al. So we'll reason to, or derive the conclusion from AXLXX. We'll start by setting up the proof, which is AXLXX, and we will next reason to LAA. We're replacing each one of these universally quantified variables with any name that we want, and we're making sure our replacement of those variables is with the same name. And this is by universal elimination. Now, in looking at our formula, which is the conclusion, we'll notice that we want to add 2 existential quantifiers here. And when we use existential introduction, we're only required to replace one of the names and replace it with an existentially quantified variable. We're not required to replace both of the names. And so at line 3, we'll reason to EY, LAY. So we're replacing just this second name here with the existentially quantified variable y. And so this says something like Al loves someone. And so this is by line 2, existential introduction. Now that we have this existentially quantified formula at line 3, we can use existential introduction on this formula, replacing this A with a existentially quantified variable. And so we can reason to EX, EY, and here we're replacing this A with an X, so it'll be LXY. And so from line 3, we reason to line 4 using line 3, existential introduction. In this proof, what we have is the universally quantified formula AX, AY, LXY, and the conclusion is EZ, LZZ. To think about this in terms of an English argument, we might say that this particular formula says that everyone loves everyone. And we might think of a concrete example of this by imagining a domain of 3 people, and each one of those individuals is in this loving relationship to everyone else in the domain, including in being a loving relationship to oneself. So not only does, let's say, Al love Liz and Liz love Tech, and Tech love Al, but also Al loves Al, Liz loves Liz, and Tech loves Tech. So every individual in the domain loves themselves as well as everyone else in the domain. And we want to reason to the conclusion that someone loves someone. We'll start this proof by simply setting up the proof, and since we have only one formula, we'll start the proof by simply writing this particular formula at line 1. Now that we have this formula at line 1, we'll reason to the conclusion. And the way we'll go about doing this is by removing these universal quantifiers using universal elimination. We'll start by removing the universal existential, the universal quantifier that binds for x. And so we'll use 1 universal elimination, and we're removing this outermost quantifier here. We're removing the universal quantifier that's binding this x, and so we'll need to replace every instance of x with any name that we want. And so I'll write AY here, and now I want to make sure I replace this x with a name, and here I'm going to pick A. And so I'll leave the y alone. Now that I have this universally quantified expression at line 2, I'm going to reason using universal elimination again to a formula. And I want to make sure I replace this y, not with b, but since I ultimately want to make use of existential introduction here, replacing each of the names with an existentially quantified variable, and I want it to be the same variable, I will replace this y here with the name that I've already used, which is A. So I'll reason to Al loves Al. Now at line 4, I can use the existential introduction rule, which allows me to take each one of these names and replace it with an existentially quantified variable. So I'll write EZ, LZZ, and so this is by line 3, existential introduction. So what I've done here is reason from everyone loves everyone, this kind of state here, to the sentence someone loves themselves, which is this state over here.
Here's another video where we practice with predicate logic proofs. This video will focus on the use of universal introduction and existential elimination. One thing to note is that I encourage you to pause the video now, try these proofs yourself, and then watch the video to kind of get confirmation as to whether or not you did the proof correctly.
In this proof, I want to reason from everyone is a person, or AXPX, to everyone is a person or a queen. And so I'm using reasoning from a universally quantified expression to another universally quantified expression. I'll start by setting up the proof. I'll simply write AX PX. And my goal will be to derive this universally quantified expression over there. The first step is to make use of universal elimination, replacing every universally quantified variable with any name of your choosing, but the replacement must be uniform. So I'll use one universal elimination here. Now, since I see my conclusion has this disjunction in it, I'll make use of the disjunction introduction rule, which says that if you have a formula, then you can reason to a disjunction where the formula that you're reasoning from is one of the disjuncts. So this is by line 2, disjunction introduction. Now that I have this disjunction PA or QA, I can use the universal introduction rule, which says that I can replace each one of these names A with a universally quantified variable, provided certain conditions are met. And those conditions are things like that the name is not found in an assumption of an open subproof, and A is not found as one of the premises. And so since this formula meets these restrictions, that it doesn't violate any of those restrictions, I can use the universal introduction rule on it. And so this is AX, PX, or QX. And this is by 3 universal introduction. There's a couple things about this particular proof I want to note in terms of some common problems I see people make. Sometimes people will try to reason directly from line 1 to the conclusion, AX, PX, or QX. And they'll try to do this using disjunction introduction. This is not an acceptable use of disjunction introduction. You could reason from line 1 to say a formula like AX, PX, or I don't know, QA, using disjunction introduction. But it's important to note that when you're using disjunction introduction, you're actually forming a disjunction. You're introducing into the proof a disjunction. Whereas this formula, this AX, PX, or QX, is not a disjunction. It is a universally quantified formula. In contrast, an acceptable use of disjunction introduction would be this AX, PX, or QA, because this formula, AX, PX, or QA, is a disjunction. In this proof, we'll reason from existentially quantified X, PX to existentially quantified X, PX, or HX. The idea here is we're reasoning from a sentence like someone is a person to someone is a person or a horse. We'll start by setting up the proof, and that involves simply writing the formula EX, PX, and indicating that this is a premise or a formula that is provided for us. So we have this EXPX, and there's no way to directly reason from EXPX to EXPX or HX. We'll have to make use of the rule existential elimination. And this rule starts with an assumption. We need to make an assumption that is based on the existing existentially quantified formula in the proof already. So what we're doing here is that if this says someone is a person, we're making an assumption that this individual that's going to pick out, or this name that's going to pick out an individual that has this property. We're just assuming temporarily that this name is picking out the same object that EXPX is. There's an important thing to note though, that when we pick a name here, the name has to be completely foreign to the proof itself. So if you had PB or PC in the proof already, you'd want to make sure you pick a different name, not PB if B is already found, or not C if C is already found. So now that we have PA, which is assumed at line 2, we can use disjunction introduction to reason to PA or HA. So this is by 2 disjunction introduction. At line 4, we can now use existential introduction to form this EX, PX, or HX. So EX, PX, or HX by 3 existential introduction. The idea here is that since this A is a name, we want to make sure we remove that name from the proof. We don't want to reinsert it into the proof because we don't want it to convey that there is an individual who we know specifically that has this particular property. We're saying that someone has the property, not an individual that we're naming.
In this assumption here, we're only using the name temporarily for the purpose of proof. We're not going to ultimately reason to a specific individual has the property of being a person or being a horse. So another way of putting it is that the formula, the name that you've assumed at line 2, needs to be removed before you derive a formula from that assumption or subproof. So now that we have this EX, PX, or HX at line 4, we can reason to EX, PX, or HX from the subproof and the existentially quantified expression at line 5. So we can reason to EX, PX, or HX. And this is derived from lines 2 through 4, as well as 1. 1 and then 2 through 4. And this is by existential elimination, this EE rule. So what we've done is we started with an existentially quantified expression. We then moved to a subproof that was based upon that existentially quantified expression. We reasoned to a formula that does not contain the name that was originally assumed. And given that it doesn't contain the name, we can reason to this particular formula directly from line 1 and the subproof. In the following proof, we'll reason from AX, PX, EX, QX to the expression EX, QX, and PX. We'll reason from, let's say, everyone is a person and someone is a queen to someone is both a queen and a person. We'll start by setting up the proof, which involves simply writing both of the formulas that are to the left of the syntactic turnstile. So this is AX, PX, as well as EX, QX. The next step will be to try to introduce into the proof this existentially quantified expression here. And while we might try to reason from line 1 to PA or PB, that won't give us this existentially quantified expression. We really need to leverage this existentially quantified expression at line 2. And so the way to start is by at line 3 making an assumption based upon line 2 for the purpose of using existential elimination. So line 3 involves an assumption where we simply replace the variable x with a, and it's acceptable to use this if we ultimately plan on using this subproof for existential elimination, because this a right here is not already found in the proof itself. So now what we can do is use line 1 to derive PA. And this is by one universal elimination. We're taking that x and replacing it with a. Now that we have PA, we at line 5 can take those two formulas and put them together. If QA is the case, then PA is, and PA is the case, then we can reason to the conjunction QA and PA. So this is by lines 3, 4, conjunction introduction. We're simply just taking lines 3 and 4 and forming a conjunction out of them. Now that we have QA and PA, we want to somehow pull this formula out of the subproof. We want to reason from the reasoning we've done in this subproof to the main line of the proof. But we can't simply reason directly to QA and PA. What we'll need to do is sort of clean QA and PA up by making sure that the formula that we're reasoning to doesn't contain the name that we've assumed at line 3. And so we'll make use of existential introduction here, replacing the a with x. So this will give us each of these a's with x. This will give us EX, QX, and PX. And this is by line 5, existential introduction. The thing to note that this is actually our conclusion here, so it's desirable to derive this formula. And we can at line 7 using existential elimination. In using existential elimination, we're reasoning from 2, which is the existentially quantified expression that on which everything is built, and this entire subproof 3 through 6. So this is 2, 3 through 6 existential elimination. Existential elimination allows us to write this last formula outside of this subproof, given that we have a subproof that is based upon an existentially quantified expression at line 2, and we meet the restrictions associated with existential elimination, which is that
this A is foreign to the proof itself, and the formula that we're reasoning to does not contain the name that we assumed at line 3, which is the assumption. In this fourth proof, I want to take a look at solving a proof with 0 premises, that is just reasoning directly to a particular formula. A lot of times people have questions about how to do these particular proofs, particularly because people like to reason from premises to a conclusion, but when you don't have any premises here, it's unclear what to do. So what you'll need to do is to start the proof by making an assumption. And so we'll start this proof by simply assuming PA. The idea here is that ultimately we want to reason to the conditional PA then PA, and then we can make use of universal introduction to derive the universal quantified expression here. So by assuming PA at line 1, then we can reiterate PA at line 2. So this is by one reiteration. The idea here is if PA is the case, then PA is the case. And so we can rewrite this formula. At line 3 now, we can derive the conditional if PA then PA. So this is by the subproof 1 through 2 conditional introduction. The idea here is we're just rewriting the content that's found in the subproof. In the subproof we said assume PA is the case. Well, if PA is the case, then PA is the case. And so we're just deriving this conditional based upon this subproof. That's something we've proven in this other subproof here. But now that we have PA then PA at line 3, we can use universal introduction on this particular formula, PA then PA. We can replace each of the names with the universally quantified variable x. And so we'll replace this first A with x and the second A with x. This doesn't violate any of the restrictions because A is not found in an open subproof, A is not found in a premise, and so we can use universal introduction on it using from line 3 universal introduction. So we are able to derive this entire formula, AX, PX, then PX, simply from making an assumption, reasoning to this conditional, and then using universal introduction to complete the proof. In this last practice problem, what I want to derive is the existentially quantified expression EX, not PX, or PX. Again, this is a zero premise deduction or zero premise derivation, and so we'll have to start by making an assumption. My thought process in looking at this particular proof is to say, well, what I would ultimately like to derive is something like PA or not PA or PA. And then if I have this formula, I can use existential introduction on it to derive my conclusion. So in thinking about trying to derive this particular formula, that's how I'm going to base my initial assumption. And so I'll say, well, this is a disjunction. One way to try to derive this particular formula is to assume the opposite of what I want, and then use negation introduction or negation elimination, or sometimes called proof by contradiction, to derive this particular formula. So I will make the assumption not PA or PA. So here's my assumption, and my goal here will be to try to derive a contradiction. And looking at line 1, I'll use De Morgan's laws on this to derive not PA and not PA. So this is by line 1, De Morgan's laws. Then I'll break the conjunction apart, which will allow me to derive not PA and not PA. So this is by 2 conjunction elimination. So now that I have a formula in its literal negation, what do I have here? I've made this assumption, and I've shown that from this assumption it follows not PA and not PA. And so I can use the negation elimination rule from the subproof 1 through 4 to derive the formula not PA or PA. So I've shown that this particular assumption leads to what we'll call it absurdity, a formula in its literal negation, so the opposite must be the case. Now that I have not PA or PA, I can make use of existential introduction to complete the proof. I can replace each one of these A's with the existentially quantified variable. So I'll reason to EX, not And here again, I'm replacing the A with the existentially quantified variable, or px. And this is by 5 existential introduction, because I'm introducing into the proof this existentially quantified expression.